And good morning, everyone, or more like good morning, good afternoon, good evening, wherever you are. I think our friends in the Asian and Pacific hub are just starting their wrap up. Actually, I think that's what I've seen in the chat, right?
Yeah.
So we're getting a bit of overlap here. I was listening to the end of their session on brain visualization. The session we'll be having tonight. This afternoon, sorry, in a few hours. It sounded pretty interesting. I am looking forward to that one, definitely.
Yeah.
Anyway, how are you, Salim? How are
Fine. Thanks
things?
for asking. How are you?
A bit tired. I will not lie about that point. This has been tons of fun, but this has been very tiring. It's a lot of stuff to keep track of at the same time, right?
Yeah. It's quite fun to be at this, being at the stage and feeling like interacting with people. But at the end, the collapse is really real.
Yeah,
Yesterday,
no, definitely.
I tried to check the gather down, and it was quite fun.
Oh,
To
Gather Town? Yeah. It is fun. Actually, if there is anyone watching, I'm not so sure because we don't have like very high numbers right now. It's I think the people from the Asian and Pacific are gonna have a get together around like in an hour and a half from now, after their wrap up, to sort of get together and just possibly meet people from the other hubs. So if you want to see people who were in Taiwan, in China, in Singapore, and in Australia, and just have a chat with them, highly recommend you just drop by there around 9:30. Sorry, 9:30 Brussels time. So that should be interesting.
Yeah.
I couldn't catch you yesterday, but that app is great. Was it? You talking about the? Oh, you mean GatherTown? Yeah. GatherTown is great. Yes. And I think if we had known about it a bit earlier, we would have I think made a better use of it. Like we have planned things around it accordingly. But we really became aware of it very late in our organization process. So it was like, oh, we're just gonna try this. I think that's pretty much what we expected. Like, okay, we're gonna have different options, see what works, what doesn't work. But it seems that that sort of virtual reality is actually a good way to do it. It's interesting. As always, you guys will have to keep me posted on what's going on Mattermost, because I am not keeping track of that. I'm a tad too busy being with you. And I also have, just like yesterday, let me get it. I also have sort of an agenda for the announcements for the beginning of the day. Let me post that. I'm going to put a call to action.
Yeah. It's really helpful to catch.
Yeah. For day 3. Okay, we have an agenda for day 3. And show. There we go. Cool. And you can tell I'm getting more and more tired because
Okay.
the layout of my agendas is getting more like poorer and poorer, and I'm just like, by now it's almost, they're like very, very quick copy paste, and it's like, oh, we just need to talk about this and about this and about this. So, and I think that I've also added a couple of things for our team as well, so that they're aware of what's coming, where there might be, where we might expect some delays or some technical stuff we should be aware of, so that the attendees and all our team knows what's going on or what to expect. So we'll see how that goes.
Yeah. I'm really curious about hacking, how the hacking track went yesterday. And
Yeah. No, I was about to say that actually. I'm just like, oh, I'm really looking forward to hear to what I've been doing and what I've been up to and so on. Um, like crazily enough, I still had a bit of energy left, and I was helping someone on a project that I know in the Americas hub at the end of the day. It felt good actually to sort of like be able to like forget about the organization for a couple of seconds and just to focus on like one small problem and go like, okay, how do we solve this? Yeah, I'm really looking forward to what has been going on. I know some projects have done a lot of progress. I'm looking forward to that. Yeah, it's going to be fun. Let's see what they have in store for us.
Yeah, I don't want to give spoilers, but I look forward to continue later, because during the organization, I really couldn't try to just check the projects. I know some, and I really want to join some of them in some point, but not now.
Yeah, no, it's the same. Yeah, same idea. I think some of those projects I want to sort of like, you want to go to their GitHub repository and just like start it and then watch it and just like get the updates. That's what I do for a lot of repository. Like some people sometimes ask me, how are you just on top of like all those new things? They're like, you just like start watching the repository and then you get updates when there's just, an issue or a pull request, and somehow you go like, oh, there's a lot of activity there. Yeah, so it's something I do recommend to people, just to sort of know what projects are active. Definitely. Well, unless you join one of that project that's uber active, and then your email, your mailbox just starts just like expanding. I have a couple of projects I'm following on GitHub, and it's just, I literally have a filter in my emails just for those, just to like, okay, just put them in a different folder, because this is just going to flood your main inbox otherwise.
There's other settings. You just opt out from getting emails, but the issue is you just forget that project.
Oh yeah, no, exactly. Yeah. No, if I don't have an email, it doesn't exist.
Yeah.
Like I never go through GitHub notifications on the website, because it's not the most convenient, I would say.
Yeah. I did that. I lost the track of something, and
yeah, exactly. Yeah. No, exactly. Yeah, no, definitely. I think it's much. I know some people say like, email is like so old school, but I'm like, nah, there is still a good use for it for certain things.
Yeah.
Though I am trying to slowly tell more and more people about how to use like Slack or Mattermost or equivalent things. But it seems that not everyone is easy to convince about that. It's like some people go like, oh, what's the point? I'm like, when you've spent 3 hours looking for that email, you'll know.
That's the best explanation I've ever heard of. I'll use that. Can I use it?
Oh yeah, of course. Yeah, there's absolutely no copyright on this. Usually I even just call that, actually that's an expression from someone else. It's not even mine. I call that email archaeology, right? You have to like start digging into like the graves of and the tombs and old monuments that are built by your old mail like folders. That's usually something you don't want to do. It's like, no, please. So yeah, definitely do not recommend that.
Numbers are
sorry?
People are coming slowly, very slowly.
Yeah, I think that compared to the 2 previous days, we clearly don't have as many people on the first few minutes of the chat. I think on the first day it's like, yes, let's see how that's going to be. And now people are like, I'm tired. Can I get a break? Definitely. It's just yes, we feel you. It is a bit tiring, definitely. How much sleep have you been getting, Salim, actually?
I need to check my Fitbit. I feel like it's kind of 5 hours, but it's not accurate, I know.
Oh, yeah, I'm not even asking for an accurate. It's like even just like the ballpark. It's just like, is it more than 3?
Yes.
Yes. Okay, that's more than me. That's pretty much how I'm going by now.
Oh, must be so hard.
Yeah, we had a couple of things to fix last night late with Lisa. We might actually use it in the end. We shot a video, a thank you video that we are planning because obviously the two, Lisa and I were not going to be awake for the Asia Pacific wrap up. So we're like, okay, let's shoot a video, and we send them the video so they can play that. Both of us were super tired. We had put together the slides a bit at the last minute, to be honest, because it was like, oh yes, we had like a list of all the people we wanted to thank. It was like, yeah, it would be better if we actually had slides with pictures and so on. Yeah, I don't think it's the most professional video we have ever made, but okay. So, but we might end up using it here because I don't think Lisa will be up and ready to just like do a thank you for this hub. So we'll see. Yeah, that was one of the things we had to fix late last night, and then I asked our wonderful streaming team to just edit the video for me, because I was like, I need to get a couple of hours of sleep. Otherwise, tomorrow is not gonna go well.
Yeah, I just saw the Annibal's editing tips, but I don't know what was it for. But now you
right, yeah, no, exactly, yeah. It's no, it was not a lot of work. Good morning, everyone. You look great, guys. No worries. Well, you haven't seen the video yet. I mean, actually, the problem is that it was so rushed. We actually ended up using Crowdcast to shoot the video. So it's just, but the problem is that we have slides. So the slides take the whole freaking screen, and you have our two faces at the bottom. So all the sort of like human, just like interaction and that you can get on a chat like this are just confined to the little corner there, and you don't see anything but the slide. So I don't think it's going to be the best video, but we'll see. We're trying our best in sort of like last minute rush. Sorry about some of the exactly, Johannes. Like, we try. Sometimes it works, sometimes it doesn't. Oh well. It can't always be perfect. Yeah. No, but it was. It's been a bit intense, but it was fun. Let's see how today goes. Yeah. Once again, if any of you in the chat or in the people watching want to just come and join us on stage, please, by all means, make yourself at home. This is pretty much like open mic time. Let's call it like that. Definitely. Wait, someone just pinged me on Mattermost. What is going on there? Sorry about that. Actually, I'm not sure I can do that because I could be actually on the wrap up for. I could be present on the wrap up for what's the in an hour? Oh, yeah, exactly, for APAC. There's no way you can. Can you take over from me, Salim, just here?
Okay.
Like if I close the window.
Let me just set it up for you, and there will be some echo for that. Okay, I'll just close that. I'll go and take over and disappear and come back. Would it be okay?
Sure. Yeah, sure. Oh, you change accounts, right? Pretty much.
Kind of. Yeah.
Okay, cool. So you close that one, change accounts, and then you come, and then I will close my window, and then you'll be back. You'll take over, right? Well, we're going to be trying a few things here. Is just to make sure. I'm going to be trying to be saying hello to the people in the APAC hub when we are. When they're wrapping up, right? Just so that they have a face of some of the organizers from the lead organizers, quote unquote, because they've been doing most of the work over there. Wait. And Camille was saying that that she is apparently might just join with you, Selim, to actually be on stage there for coffee. Okay, we're trying things here. Okay, so I'm gonna say bye-bye and see how that goes.
Hello, everyone. I hope you can see me and hear me because I'm not able to do that. Yay! I'm not sure if people could hear me. I don't know. Because I did some settings and I'm not really sure about it. Hey, great. So this is the coffee and breakfast and lunchtime or the open mic time of the EMEA Hub, and we are just starting our day. And any of the project leaders want to come up to stage and talk about whatever necessary, or I'm removing myself. Should I just randomly invite you all? We are five people here. I'm just randomly inviting you, starting from Johannes. It's not the best way, I know, and it's not the most inclusive way. I also know, and I'm sorry about that, but being on the stage alone and losing track of the things you're supposed to say could be so alarming for my brain. So my fight and flight response is to just a freeze on the screen, and I know you don't want to watch that. Okay, Johannes is invited, but not sure. Yeah, okay. It's great.
Hey, I'm back. I'm back as myself. Crazy.
Great.
Yeah. So I'm just gonna try to set things up so that I can actually go and jump and I can teleport to China and Singapore to just be there, and then I'll try to come back here. I'm not sure how I'm gonna do that. This is gonna be interesting. We'll figure it out.
You need a special effect of teleporting while you are doing that.
That would be so freaking awesome. Okay. Multitasking is not good for your mental health. Don't try this at home, kids. Seriously.
But when a neuroscientist tells that, it doesn't, I want to believe it. I know it's correct, but you are researching on this and you know this is correct, but you are doing this. It's not that convincing.
Yeah.
I'm not blaming you, but we all do that.
Yeah, well, it's... Wait. Can I mute this thing?
I'm sure you
Now
can.
I'm getting the audio feed from the Zoom from APAC. This is really confusing. So I'm like, I have two things in the same time. I'm just trying to mute their Zoom so I don't go completely insane.
Yeah, that's crazy.
Cool. Okay, I've muted them. Now I can actually listen to you. Let me finish organizing a couple
I'm
of
just
things.
inviting Camille.
Hey, cool.
Okay, so
Hey.
share something
Hello.
with you. Hi. I
What
was
happened?
just, and this is very silly. I was just on the coffee morning of day 2, and I was wondering, why are they ignoring me? Like, looking at me.
It's like, hey, hey, hey. Oh, like were you playing the video of day 2? Or what was going on?
Yeah, for once I had to click play, but I thought, okay, Crowdcast is a bit weird today. That's okay. And then I was just like, you were asking if people were hearing you, and I was just yes. And you said someone else said yes, and I was just okay. Well, why not? I couldn't see that message, and after some time, I was just okay. What's wrong? Oh my god. I think we're a bit tired now. Maybe.
No, we're not. We're fine. We're completely fine.
Yeah.
Everything is okay. Okay, I'm gonna try to sync with APAC to see when I can come on stage.
Okay.
Yeah.
I'm not sure what's the best way to do that. Drop a message in the Zoom directly.
I did ask Kelly, and she said you can come anytime.
Okay.
As they are wrapping up. So wrapping up.
Okay, cool. So I'm just gonna drop a message in the chat saying that I'm around.
Okay.
And I will let you handle it might just be more than just the coffee because I have no idea how long their thing is going to be. So it could be that you will have to do the intro without me, but you're all grown-ups and you know how to do this.
Thank you. Thank you. I feel like grown-up.
Well, you never know. I might go to another recorded video and just try to talk there. So, I mean, Selim, be ready to do everything by yourself.
I'm not that grown up yet.
Yeah, no, I've put the link to the agenda in a call to action we have at the bottom, so you should be good with this.
I know, but there might be slight things that you know, and you just it will be good for the ones on the organization side or who knows everything more than me take over.
I think that for the organization things, I would be able to then tell everyone how we're going to be running the things in the back. So don't worry. I don't think we should worry too much about that. Well, and we have a very skilled team that has shown that they're able to improvise on the fly and come up with solutions just like this. So even if I'm not here, I'm sure you gang would wing it, no problem.
Thanks for calming words. Hoping it will work because
I'm sure it will. Definitely.
It will work.
Also, there is this feedback form, not the Framer form that we mentioned yesterday. There's the pluses and delta thing. I'm going to put the link here. No, actually, I'm going to put it in the agenda for the day.
That will be really nice.
Better. Yeah, that will be better because it will be more appropriate. And I'm not sure. Yeah, I'm going to put it just at the end. Hot takes feedback form. That's what we're going to call it. And I think the people who were at the hackathon last year might remember this. The idea of it is that people just type comments of like, oh, this was great, I liked it, I didn't like this. And you put a plus if you agree with the comment next to it, and you put a minus if you disagree with it next to it, so you don't have to retype the same thing. Sort of a way to crowdsource things very quickly. Everything is in a markdown document, so it should be fine. And it's in the. I've just updated the agenda thing, so we should all be good to go.
Organization question: do I need to relog as Open Science, or Selim, are you logged as Open?
I'm Open Science, and I'm chatting as Open Science with very casual manner. I don't know. I hope it's okay.
No, it's fine. It's just one of us has to be with that account, I think. So
yeah, I'm that person.
Okay, perfect. So then we can just let Remy.
Hey.
Okay. I will disappear now. I am around. Okay, I'll stop typing because this is really distracting for everyone. I will let you guys handle this, and I will talk to you later.
Say hi to APAC.
Yes, I will. This is really exciting. Okay,
you-
so we gotta pretend we are in Star Trek, and I'm gonna like be teleported somewhere else. So
Yeah.
I'm just gonna go energize.
Wow. He needs a special teleporting effect, but I couldn't
Yeah.
manage to find that.
I think it's time travel as well, right? Because
Yeah.
they are this afternoon, so time travel.
Yeah, it's time travel, and it so lucky to live all the experience and come back.
Yeah, exactly. Yeah. But he's gonna miss our great morning coffee, and that's sad for him.
And I don't have coffee.
Me neither. I always miss that. It's just you have to get up and everything, and the coffee is just the thing I drop. But yeah.
Coffee is the thing I just woke up for, but I don't have it. So yeah. Oh, you can still hear us. So yeah. Okay, no gossip. Okay.
Oops. So what can we say about Remy?
I learned a lot, so I can only say thanks.
Yeah, me too, actually. Because it has been a busy few months.
I just jumped for very lately. I think I've been knowing you for 15 days or something like that.
Yeah, we were pretty late. That's very true. Yeah, it has been a bit of like rushing everything, but we've been so lucky to be connected with you. And for that, we need to thank Ishol.
Thank you.
Yeah. No, really.
Yeah, we can just, I don't know, Ishul is not awake. Yeah, not yet. I just disturbing her in private chat, but no, not awake. We can just call her, talk about what the complaints or the recommendations of the organizers on the GitHub.
Yeah.
Do you know the feedbacks, and do you want to talk about the hack track? How was it? I'm really curious.
I don't have the feedback from the hack track, but I have the feedback from the form we had, so I can look into this really quickly now. You know, the mid hackathon form.
Yeah.
Just see. There are things.
Meanwhile, I'll be trying to invite people to screen if they want to come up and talk about things. I'm seeing Matthew, and I don't know if he wants to join us. Let's try that. It's so random, but I like some randomness. Okay, just invited and waiting for the connection. And Remy said there are so many active projects, and the ones who are just figuring things out, and it's so totally fine. It's not a competition. And it's a sharing of learning experience under the name of hacking. Okay, I invited, but no accept, so just reprompting. Yep, I'll just type here as well. It's been really great experience for me to know the kitchen of everything, how it's going, how to stream, and how to get things done. It's been really amazing, and I know most people are familiar with these things because they need that for their daily job or their lab's requirement. But you are currently watching my lab, so I'm always all alone. So being interactive with you was one of the greatest learning experiences for me. I think it could be one of the things that I should say on the wrap up.
Yeah, I think it was really nice to work as a team. I think even in my lab, we don't do this kind of things like using Crowdcast. You can see I'm still not an expert, and the streaming part. But yeah, there were so many moving pieces where different people have joined and just helped, and that has been extremely useful. Like the streaming in particular, I think can be challenging with Crowdcast. So we were so lucky to have Annabelle and Ishil and you looking into that.
For the technical part, I understand the point, but apart from Crowdcast and all the settings, the intuitive collaboration without getting directions and getting some clear instructions, just as if you were in a room and doing things together in a very different environments, is a great experience for me.
Yeah, the organic part then.
Yeah.
I think the Brainhack group, so the Brainhack group joined us, the Brainhack Global, I think they are very organic as a group, usually. Yeah. But yeah. And Brainhacks in general, I guess.
Yeah.
Just the fact that we're called Brainhack.
True.
Yeah.
No one wants to come to stage. I don't know why.
People are sleepy and it's the last day, so I can relate to that. It's
okay. True. They've been hacking so much and they can be tired.
Pretty lucky.
Yeah. And there's things are going on Epic Hub and it must be fun.
Yeah, they're wrapping up. So last day is, it's like the end of something. But yeah. But tell us a bit about what you do. Like normally when you're not sharing Brainhack, like what's your research about?
Oh, thank you. Actually, I try to focus as a PhD student. I'm kind of a very bad and distracted PhD student, and it's not a good thing to say at streams, sorry. I'm working on the diagnosis of Alzheimer's disease and the dementia in general using deep learning methodology, and I'm trying to making things more explainable. And it didn't work for my side because I need to learn things continuously, especially for the neuroscience part. I have background, my background is so confused, so I don't mention that, but I took basic neuroscience, chemistry-related neuroscience classes, but no imaging classes, and no one around me knows the imaging part. But I was lucky enough to be able to select it the last year's Neuroacademy, and I was just really amazed by the fact that I struggled for 2 years just to handle very tiny piece of code, but those are the people who are writing that and managing that. It simply changed my life in many ways, and that also made me get involved with you eventually at the end. It's adding up, and it started to change that. So soon enough, I'll be coming with my very first thesis paper. Other than that, I have many side projects related to mostly deep learning parts. It's not good for a student to have so many different projects, and they are very, very unrelated, but I'm trying to make things connected and just focusing on thesis.
Yeah, well, you need a balance, right? Because curiosity is really important as a PhD student. So having many projects probably means you're interested in many different things. Yeah. And that's probably helping with what you're doing. I really like what you shared about your experience and your academy. It really relates to like when I went to my first Brainhack in Paris, I had this feeling like you could discuss with people about these, I don't know, these tricks, these little details that are so important. Like just sometimes when you do research, you get stuck on like things, and this is part of the process. But being able to like discuss with other people who are stuck at the same time or who experienced that maybe a few years back and can help you is just so much help. Like I really like the idea that we can work more together rather than each of us completely separately.
Yeah, And I also wasn't really aware of the structure of the institutions because I'm based in Turkey and I'm doing things on my own, and my department is so new. My PIs are just there for the registration part, and they just say, okay, do what you want and get this done, but no feedback, no constructive or destructive feedback.
Respective.
And no, I have online PI like people I can interact with, and I can just ask if I'm doing things wrong or correct, because it's really necessary for a student. Routing all alone is a waste of time. So yeah.
Yeah, it's part of the process, like iterations, and yeah. I think I've learned it now. Initially, it was a bit hard, like that thing that it takes so much time to get something that you're happy with, and you feel you understand finally. Like, yeah, had that feeling of being lost for quite some times, and then at some point, you say, okay, that little part I understand well, and that's a good feeling.
Yeah.
So no one of the people who are here are doing a PhD. This is why the first PhD is to warm up. There must be a second one. Oh, wow.
Okay. I'm just calling you to stage for about doing second PhDs because I was really interested about it. But someone convinced me not to do that.
Yeah, I think Remy is doing a second one. That's what Johannes is saying. But yeah, I know about Dr. Remy. Yeah, I know one other person, I think. Hey.
Hello.
Hello.
Well, yeah, I was just joking about the second one. I am not doing a second one, of course. One is enough. My name is Jamal. I am doing my PhD in Italy. And yeah, like Selim, I also like some guidance, like lacking some strategy. So you learn things as you do, as you practice. So actually, yeah, it feels like it is just the phase to learn how to do a PhD. And I was thinking maybe I just do a proper second one later, but I don't think I will have enough patience for that.
Yeah, I don't think I could do a second one either. Like, this is enough.
No, maybe if they pay me well, I can think about it.
Oh, yeah. I'm unpaid PhD student, so I don't mind.
Look, I know that there must be at least some, I don't know, scholarship or something. I don't know how we can go on without any proper payment, but
that's what family is for.
Yeah.
Yeah, unfortunately, not all families can do that. And
yeah.
If PI hires already, I think I don't think it's illegal in France, but I haven't. Sorry. So Johannes is asking whether it's legal in all countries to hire someone to do a PhD when they already have a PhD, which I don't really know. It's a really good question.
Yeah, I researched that because I was really interested about it. And in US, some really good programs prohibit you to apply.
Okay.
I didn't know.
Yeah, just they mention on the application site, but if you want to do, you should pay.
Yeah, Robert is saying that it doesn't optimally serve the university who's here to whose mission is to educate people, but it would be allowed. I see. Yeah, so probably different rules depending in different place. Just like so many things, like even a PhD itself is so different from one country to the other. The way you do it, the way you do the defense. I was so surprised. So I did my PhD in France, and then I was a postdoc in the UK. And so in France, when you do your defense, it's kind of, I don't know, a work party if you want. You have this formal presentation, but then usually your family is here, like your friends are here. Then you have questions, and then you have like maybe a dinner with your friends and everything. And it's very like it's not relaxed, like the question part and the presentation are really formal, but then it's a happy time, like you're happy to share with everyone. And in the UK, it's very different, at least in Warwick, where I was. Basically, the PhD student who's defending goes into a room with the reviewer, and they keep asking questions for as much time as they want, but there is no one else there. So I think it's more stressful. And then there is the going to the pub part and everything, but there is no this public facing, like.
Yeah, it sounds very scary.
Yeah, it sounds scary. I agree. But I haven't done it. But yeah, well, it's so different countries have different ways, I think.
We adopted the UK version of that.
Okay, so you have that as well.
Yeah.
Yeah.
Because we adopt things that we are really hard and pushing the students. So UK sounds the hard one and sounds similar to our version.
Yeah. I mean, if you made up until to the defense, I think you are able to answer any kind of questions, actually.
I hope that.
Yeah, in front of any audience, shouldn't stress you.
I hope that.
Yeah, and I remember I saw some ads for the PhD positions. If you have, for example, if you have a PhD before, you are not eligible for the scholarship.
I see.
Yeah. And they still accept you, but you don't get anything.
Yeah.
Whereabouts in Italy are you? Can I ask?
In Lucca, small city in Tuscany.
I know Lucca. I'm from the southeast of France, so I used to, like, when I was in school, we were just like every year go to Italy and have like pen friends. So Lucca was one of those places. So
this small boutique medieval city. It's very nice, cute.
Yeah, very cute. So do you enjoy living there?
It is very small though, but it is nice and very relaxing city. But right now I am back in my hometown in Turkey because of all this contagion virus thing.
Of course.
Where is the hometown?
Yeah, now you know maybe.
I am in Mersin right now.
Ah, great.
Where are you?
Ankara.
Ankara. I studied in Ankara in my bachelor's degrees, but it was nice. But Lucca is better.
Obviously, I can imagine.
I don't think you can compare city and rank them. It doesn't work like that. Come on.
There's certain thing about Ankara. There's nothing in Ankara. You just focus on your thing. The city is designed like that, so I can imagine. Everywhere is better than. Not in even in touristic way. We have just maybe 10 or 20 touristic places, and you all can end up in one day.
So. And yes, some of them are like political tourism. Yeah, so foreigners wouldn't be interested.
Yeah. That's why
I think that's a lot. That's a lot of touristic places for a single city.
Where are you from?
So right now I'm in Rennes in Brittany, so in France. Way too much rain over here. That's my only complaint. I like the city, but the rain is just too much. Ooh. It can rain even in the summer. Well, I hope there is no one like originally from Brittany, because usually they just say this is not true, but honestly, this is very true.
It's a measurable fact.
Yeah. But I was in the UK before, so maybe it's slightly better.
Yeah. Maybe you should come to Lucca next year.
Yeah, maybe.
We are hiring, actually. There is a PhD call ongoing. You can apply.
No, done with that part. So what have you been working on during the Brainhack or looking at or discussing?
Actually, I'm very interested in all the coding part, and I was trying to improve myself by myself. But for my current project in PhD, I was stuck with MATLAB only. So I missed everything going on in Python, in GitHub, Docker. So this was a very good opportunity for me to practice those. For example, I spent my yesterday trying to figure out how Git works. And finally, I managed to send my pull request.
Wow, congratulations.
It is, I think it is more complicated than it is supposed to be, but it's fine.
Yeah, I had that feeling too at some point, like, why so many steps? But, yeah.
I just need to make some changes and send it to the publisher.
Just let me do these changes, come on.
Yeah. So it was a good opportunity for me to practice, at least start learning about all the things that I have been missing. I think that once I am done with my current project, I will just change everything to Python. I think it's getting more popular every day.
Yeah. No, it's not about popularity, but as a person started with MATLAB, I could say that I don't want to say anything bad about MATLAB because it's good tool. But in Python, things start to feel natural, as if you just
that's great.
Do the things without do the things as if you were speaking or similar. So when it feels natural, you don't struggle with the language and you just focus on your problem very basically.
I see, because in MATLAB, sometimes it feels like it's a language that is spoken by a very small community and you are trying to understand it to make things work.
But each language has his strengths, though I don't want to end up in a MATLAB versus Python fight. No. I find like MATLAB really useful when sometimes you want to test something really quickly, and it's really powerful in for some specific aspects like matrices and so on. And of course, there is SPM in MATLAB, which I used a lot. And
I was going to say that matrix-wise, it is very useful, but I am also using SPM, and the problem is you cannot just use another software or use another thing when you are using SPM. Sure. You cannot just change tools. But if you're, for example, using FSL, you can use AFNI's, like whatever tool you are interested. Yeah, so I am stuck with SPM more specifically.
Well, you can do system calls, but it gets a bit messy. That's right. Yeah.
Since you are using SPM, what are you working on?
So I do mainly fMRI, task-based fMRI, and these days I'm really interested in like pipelines and how when you change a pipeline to do roughly the same thing, you get different results. So why is that? Is that okay? Is that not okay? How different they are? Because right now we don't have much visibility on that. So
I see.
So there are different projects going on, but that's really what
I see. No, I ask because I am doing the. Hello.
Hi.
I want to jump in because I think it's very interesting what Camille talked about. So can you talk more about the stop project?
Sorry, we don't hear you very well.
Let me see.
Yeah, I was invited Usha, and I just saw on the chat, unable to connect.
Oh, Usha, are you using Firefox? Because for me on Firefox, it's just signal issues. I see. Yeah. Oh, that's too bad.
You muted yourself, Johannes. Yeah, Crowdcast is best working with Chrome. I think we should be adding that for the first day. So switch to Chrome, people.
Yeah, but I like Firefox.
I also like Firefox, but Crowdcast loves Chrome.
Yeah, but I like Firefox, so I'm going to try again.
Okay.
Yeah,
okay.
You know some of these people, you shouldn't.
I know. I use Firefox for everything, but Chrome for Crowdcast.
Yeah, but I agree with you. I think it would be nice to maybe have a document.
Yeah.
Just having these little details that
Yeah,
are
yeah,
quite
yeah.
important to get in.
Yeah, I know we should start the document and I need to look for it, but I wasn't really fully energized to look for it. So
Yeah.
I'll take a look after this. And I also had some statements about diversity, and I completely forgot about it. And I'll do that. I'll write about it because it's necessary.
Yeah, I think it's very necessary, and that's a very important topic. So maybe something we should have. I'm happy. Sorry, cooking and typing. I'm happy to say on stage for you. So I was just saying, yeah, diversity. We've tried quite a few things for Brainhack this year, but it's. I think I really care about diversity, but I think it takes time. Like it's a process that requires to put many different things in place so that we can have more people, like more different people coming from the community. And what we've noticed with the team is that when you rush everything, then usually that's the thing that unfortunately is going to drop. So we tried quite a few things, like we had the mini grants. We reserve part of our seat to underrepresented groups and other things, but it's not enough. Like it's always like the connection issues. I think is something we should work on. Like make it easier for people to connect, because right now, well, there was the issue with the email being lost. But even beyond that, I think making it clearer how you actually connect. The fact that myself, I was today on day 2 instead of day 3 means that it probably could be easier. But doing things easy for people is something that is hard on the organizer. Like it's hard to do easy. And this is true with code as well, actually. Robert is saying, for future events, perhaps also share that there are also Chrome-based alternatives that do not require. Oh, sounds great. And have you tried this, Robert, with Crowdcast? Do they work? I like that.
I can just invite Robert and discuss about it.
Yeah,
sorry,
sounds
Johannes,
good.
we can't hear you, and I'm just closing your video. Sorry.
But maybe he won the chat. No.
He just muted and
Okay.
had some issues. So it sounded like a good thing to talk about.
Yeah. So we have just to make sure we stay on time. We have 5 more minutes. Hey, Robert, how are you?
Hey.
We can hear you now.
Yeah. You can hear me.
Yeah.
Yes.
Okay, good. No, I think it's good to share these experiences that we're now building up with, like what works, what doesn't work, or what works like halfway. I've been successful with Firefox over the last few days with Crowdcast.
Okay.
But when you were saying this, I thought let's switch to Vivaldi, because I'm like on principle grounds I'm not using Chrome because I don't want to share my data with Google all of the time. Like I'm already sharing too much data with Google.
Yeah.
And Vivaldi works fine as well.
I see. Yeah, it's interesting also what you're saying about Firefox, because for me it was working, but going on the stage was just impossible. So I don't know what. So I could watch, but not be here and talk.
So that's something that I have not tried. So I'm now in Vivaldi, and it works smoothly.
Okay. Yeah. So that's probably that's good experience we should share. Yeah.
By the way, nice to meet you with all of you. I think I will grab a coffee before the next session starts.
That's a good plan. I like one. Maybe I'll do the same thing. William. No. Oh yeah, I'm a few minutes. So my time on my computer is not right. So it might be almost 9 now. But let's leave a few
minutes. We have 2 minutes.
Okay, cool.
If you have anything to remind me, because I'll be just trying to read the contents of the introductory.
Yeah.
And I don't Hello, everyone. This is the introduction, day 3, and it's really incredible. We are at the last day. Hello, Camille again.
Hello.
We
Hi.
are at the introduction part of the 3rd day. Is it 3rd day? I'm really lost in track of time, and it feels like 10 days.
It depends how you count. Like if you count 3 days per day, if you count the 3 hubs and each hub is 1 day, this is the, so we had 1, 2,
9.
3, 4, 5. Well, the 9 is America, so we're on the 8th day.
Oh, okay. Okay, we are on the 8th day.
Yeah.
Oh, it's been really amazing.
I think that's how it feels, right? 3 days in one.
Yeah.
Yeah, I think it was pretty nice before we get started, like actually seeing the morning session for you. So I'm in Europe, you're in Europe as well, but seeing the morning session in Europe and then being able to see a little bit of Americas in the, like at the end of my day, I thought that was like nice to see that flow going. Even though, yeah, not attending the whole thing because you have to sleep and that's very important. But
Yeah. And sometimes listening again on the Americas app and following the issues, like, don't do that. We did it didn't work.
yeah, and the chat as well. I like the Mattermost OHBM hackathon chat because you arrive in the morning and you see, wow, APAC has been so active and everything. That's really cool. I'm going to paste the link in HBM hackathon now so that people can comment they want. But if you want to start with the agenda, that's all good.
Today's train track is starting with the introduction of the containers like Docker, and we will be learning about in detail, and we will be setting up our Docker, and it's really exciting because I did that once, and for me it's not really necessary for my research because I do everything in one computer, but there will be times I need to share my settings with people because it's not necessary to say people, it worked in my computer. No, it's not confusing. So you need to share those computer settings with real people, and so they can test. And Docker is fun. And there will be machine learning and scikit-learn and nylearn tutorial. I got the video very recently, and it's really cool. And I'm in machine learning field, and it was one of the things that I thought that I should have learned and discovered very earlier. It's really cool for me. And there's brain visualization. We split that part to 3 videos. Found that it would be fine with one stream, but okay, it's not it's too much detail for people.
But maybe just saying that the brain visualization tutorial on train track is done by the OHBM brain art special interest groups. I'm really looking forward to that. We've been like working as another SIG of OHBM. We've been working with them a little bit, and yeah, looking forward to that. I think it's going to be great.
The theme is neurodiversity at the Brain Art Spatial Interest Group, but I'm not really sure about the meaning of neurodiversity, like being autistic or...
I think it's the way I understand it, and I might be wrong, and I'd be really happy to get someone on the stage who wants to explain that.
Yeah, please.
But I think it's also assuming that all people are different and we do things in different way, and not assume that there is a single typical way of being. Your definition of neurodiversity, and I think this is their theme for this year OHBM. Each year they have a theme around which they build their exhibition. They're going to have the exhibition. So for those of you coming to HBM, I think they will have a room, and some of their artwork is going to be presented on the main stage as well. So yeah, and they had good morning, Stephanie.
And they did also competition, or is it going on? I don't know.
I don't know if
it's going on. It's going on. The deadline is the 20th, so there are some days to do some art with brains.
Yeah, and so every year they do these competitions where they ask the community to just like submit their artwork, and then they have the ceremony I think usually it's during the Neurobureau party, so that there's this big party with like organized by the student and postdoc SIG, and they just announce who is the winner. And they usually have several categories. I don't know what they are this year, but yeah, it's a fun part, and beautiful artwork as well. Hi, Remy.
Are you back? Do you want to come to the stage again?
I think he said hi from APAC, so
yeah, not available, just listening, or I don't know.
I'll ask to join us, or
there is BrainSpace, a toolbox for analysis of microscale gradients in neuroimaging and connectome datasets, and it's mentioned on the today's schedule, but I don't know what it is for.
Sorry, I don't see that. Is it?
You can just click the agenda.
Yeah, so I'm going to it now.
So we can go through together, because otherwise it will be confusing for me. We mentioned the brain art, and it's fun, and I really want to join that because I did some art using generative algorithms, and why not brain data?
Yeah. Brain data can be really beautiful, and I think it's probably inspiring.
Yeah, it is.
Okay, so
the render slide part, the third part of the art. I'm not sure.
Oh, these are the slides of the speaker. So we have 3 speakers, and he just probably linked to the slides. Yeah.
Okay. So
yeah. He's one of the instructors, and then we will have TAs available on the day, as usual, for the train track.
Yeah.
So we're good about that. Oh yeah, and then so it's midday. We can say midday. Well, mid. Well, I don't know how we call it because it's different time for different people. But we have a session with INCF as well. Do you want to say a few words about that?
I know people from INCF, and I watched the video, but I don't have any correct words to describe. But I know they're one of the biggest initiatives encouraging people to do open science, open neuroscience, and it's really important, especially for people like me.
Yeah, I think so. INCF stands for International Neuroinformatics Coordinating Facility. It's an organization that works towards, as you said, open science. They are very involved in standards, so they were really active to the initiation and the development of PIDs in particular, but also NIDM, which is a standard based on semantic web technologies. And they have these they also have these. It's not special interest groups, but they have these small groups that people can create to discuss different topics they are interested in. And they are a truly international organization. So it's people coming from all around the world to work on these different topics. And so today we'll have a discussion session with them. So they've been sponsors of the OHBM hackathon, I think, since its beginning. And today they want to discuss with us building maybe more links between the INCF and the OHBM community that we have here today, and how we can work together. And I think a lot of what they do is very applicable to what we're doing here, as you said. So I'm looking forward to that. And it's a discussion session, so it's going to be live as well, which is always nice.
Yeah, and all the settings are done, so fingers crossed for the settings. Yeah, for the hack track, I'm really curious about the feedbacks, and I think people would be talking about it at the wrap up more. There will be more awake or more joining us.
Yeah,
I don't know what to say then. That's all for me.
Yeah, I think so. Probably we should say now that tonight there's going to be a longer wrap up because it's the last day, and we're going to invite project leads on the stage to give us a status of what was done during those 3 days. It's perfectly fine if you haven't followed what you had planned. This happens all the time. I think the most important part is just discussing with people, but we'd be really, really happy to hear what you've achieved and maybe your struggles as well, if there are some, and you're happy to share them. So that's going to be, we have I think a 1 hour and a half session to wrap up tonight. So there's going to be a few presentations. I think there is a video from Remy and Lisa, but also those like project wrap up, which are so important for the hackathon. So please all be ready for that. I'm looking forward to see all the good things that happens.
Yeah, good and bad, because it's all experience.
Yeah, it's a path. It's a path. And when you fail, then next time you won't do the same mistake.
Yeah.
Should we share the feedback form as well?
Yeah, please. And then I'll be jumping to the streaming.
Okay, so I'll just say a few words about the feedback form. For those of you who were here last year, this is very similar to what was done in Rome. So it's a free text document, so you can type in, and it would be great if you can share your pluses, the thing you really liked, and your deltas. What do you think could be improved? And of course, if you have suggestions, that's very welcome. But just saying like, this could have been done better, and that's so important to build these events. The document is open all day, so you can type at any time you want, and I think will be covered again tonight during the wrap up.
Haha! It's one of the first feedbacks nobody complained about. I see.
Yeah.
Yay! I'm just inviting Remy because he said.
Oh, cool.
So just for the introduction part, maybe he has some words to add.
Yeah.
Yeah, no AC complaints. It's really great.
Hello,
Hello.
everyone. Good morning, you all. Sorry, 2 seconds ago I was I was in the Asian Pacific hub wrap up, and now I'm with you. Technology is freaking amazing. I'm loving this.
Fast
People
travel,
say,
huh?
man, it's insane how quickly things go. Cool. What have I missed? I'm sorry. Where are you?
We're almost done. We were talking about the plus and deltas document. I don't know if you want to say a few words again. We said people could contribute throughout the day, and then we'll probably go through that a little bit tonight during the wrap up.
I just introduced it to the Asia Pacific hub, but that's I'm sure. Yeah, and when I was introducing it, I saw you gang typing in it, and I was like, oh, okay, this is very just organic and interactive. I like this. I mean, that was the idea. Like, people can just contribute from wherever they are. How was the APAC wrap up? I could not attend their project because I would switch, because teleportation is quick, but not that quick. So I was just a bit too late. So I just arrived for like the thank you session that I wanted to do there. So I did not see it. Feedback for EMEA or in general. I think they loved it. Also that it was, a lot of the people were new to the format, so they had never done or never organized a hackathon even in real life, and a lot of these people didn't even know each other, right? So it was just like piles of not problems, but just obstacles or difficulties that they had to overcome, and they winged it super well. And the question was pretty much, when can we do this again?
Oh wow!
I'm like, can we have just like 1 week to rest, please? No, it was also more general. Just like, do you think that this should be part of any hackathon that's organized in the future? Right? Should there always be a virtual side where people can just jump in, even if you have like in a real life version? And yeah, I mean, I think that's something to figure out, but I think that there are clearly some good sides to this, especially, I mean, and for the people in Asian Pacific, a lot of them were based in Australia, and they say, yes, for us, just the carbon footprint of going to a real life thing that's not local is just huge. So for them, they were like, no, it makes total sense for us to do this. Yeah. So they were really enthusiastic, and
Sorry.
Go for it.
Beyond that, I think it makes sense for a lot of people who just thinking carrying responsibilities, for instance, like going to OHBM for a week and then staying 3 more days for a hackathon is a very long time away from home. Also, people who just cannot fund these travels, like those travels are really expensive to go travel another place of the world. So I'm really interested in how we can make more content available online. Of course, this year everything was available online, but if we go back to in-person meeting, how can we sustain some of that? Because I think it's very important so that we can reach out to a broader community.
Yeah, no, definitely. No, I think that was pretty much it. We had a bit of a chat on a few things. Oh yeah, I realized that at the very end we had forgotten to mention the brain web to them, so I quickly introduced that to them to tell them that there is a virtual space when projects can keep on going. It doesn't have to end now, and you can easily add yourself as an individual to the brain web or add your project to the list of projects, and do not hesitate to make good use of that. So some of those things that we had mentioned here earlier, but sort of forgot to just tell them about. So I was trying to just get all our ducks in a row.
Yeah, I think so. We had missed that actually from your agenda. So I think we should say those three things you had for project leads. So when you prepare your wrap up, if you can tell us about what you did. So we've covered that, but also if you have any plan for the futures, how do you see this project going on? Is this just over? Like it could be you had something very specific to do, it's done, but most likely you might want to do to work again on it on the future. If you have any plans for that, that would be really nice to hear. And also, the brain web you've just mentioned, Remy. So that's one way the projects could continue.
Yeah, totally. Yeah, definitely.
We are 3 minutes late for the...
Okay.
And I think it's okay. So we have Stefan and Tom Shaw, who should actually also be teleporting from the Asia Pacific hub to be our train track instructors. Well, they are the instructors on the video, but they'll be in the chat answering questions.
Great.
But we might need to brief them on Crowdcast, because I think it's their first time they've used it, so they might just be like, how does this work? But they'll be in the chat to answer your question, and there will be a Q&A after that where they can come on stage and answer questions. So that's how it's going to roll for that one.
Yeah, thanks for the introduction then. I'm just closing this and starting the broadcast.
Okay, let's do that. See you later, everyone.
Hello, everyone. No. Hello, everyone. My name is Tom Shaw, and today I'm going to be going through with Stefan Bowman the Containers for Science train track talk. But before we get started, I'd just like to acknowledge the traditional owners of the land on which we're situated, which for here us in St. Lucia is the Turrbal and Yugara people. So today we will be going through containers. What are they? Why are they useful? How to use them and how to build them. If my slide will advance, which it will, great. So as I said, my name is Tom Shaw. I'm a PhD student at the Center for Advanced Imaging, which is here. And those are my handles if you want to contact me at any point.
And my name is Stefan Bowman. I'm a National Imaging Facility Fellow at the Center for Advanced Imaging. And if you have questions, you can ask them in the Mattermost channel and also in the Jitsi room. So let's get started. What are containers? So just to get started, I thought we'll prepare a little poll. First, are containers a different name for simply a virtual machine? Or B, are they plastic boxes to store food in and keep it separated? Or are they a collection of tools to keep programs from interfering with each other? So as you probably guess, it's containers are very much related to what virtual machines try to do. So I think I will show a little bit about that later. And yes, it's obvious they're not plastic boxes to store food in. Yes, so they're actually a collection of tools to keep programs from interfering with each other. So what does that mean? So let's look a bit into this. So containers are meant to isolate software from its surrounding operating system. And container images include code, the runtime, system tools, system libraries, all the settings. And we can store this image and we can distribute this to our computers. And then we also have something that's called resource management, and it's provided by the Linux kernel. And the technical concepts are namespaces and C groups, but we will not go into more detail. But basically what they allow us to run like a little virtual machine on a computer. And just for terminology, when we talk about an image, what we mean is an image describes everything we need to run. So these are basically the files of this little computer that we're building. And a container is the instance of that. So when we are launching a little container, then we're basing it on the image and we're starting it, and then we get software in there. So I hope this will become a lot clearer, but just to explain what are the technologies out there to do this. So the first big one was Docker. Docker started the container hype, and it basically made tools that were already available in Linux, made them really nice and user-friendly. And it provided packages to do this on Linux, Windows, and Mac. And it's widely adopted because when the cloud basically took off, it was really useful to package software in containers to be able to shift these containers quickly around on different computers and different data centers in different places in the world. And also, when you read about Docker, there's something like Kubernetes. So Kubernetes is an orchestration tool, so you can manage all these little containers. So they call them microservices. And in science, you will not deal so much with Kubernetes. But what's the problem with Docker? For us, we run a lot of graphical applications, right? So we need FSL View and MR View, all these little tools, and that's not so easy with Docker. And Docker requires elevated privileges, so root privileges, and that's why there was a different tool for the scientific community. The tool is called Singularity. It's very similar to Docker, does basically the same thing. But it's simple to install. It runs on high performance computing systems, but it allows something very nice. It allows to run untrusted users running untrusted containers, which means that you're the same user inside the image than outside. And because of this, you can run it in a shared environment, which you can't do with Docker. And also Singularity is built for data science. So GPU is much easier to work with. Graphical applications are very easy to work with. You don't have to do any wizardry to do this. And we'll show later how to do this. And also the container format of Singularity is a little bit nicer for us scientists because it's just a single file. So we can easily move this file to different computers. We can archive this file with the data that we have, for example, and can keep the environment that we analyze the data with the data, which is a fantastic feature. And yeah, that's enabled by Singularity. Next slide. Okay, here it is. Oh, okay, I was too fast. Oh. Sorry, the slides are a little bit delayed for me. So because I already mentioned, containers are something like a virtual machine. So what's the difference between a virtual machine and a container? So we'll start at the hardware. So we have a workstation, for example, a Dell Precision, but it could also be our notebook, it could be our MacBook, it could be also a high-performance computing system. On top of that, we have usually an operating system. So in this case, I just said CentOS 6 or Ubuntu or something else. And then in the old days, so before containers, what we did is we installed a hypervisor, for example, VirtualBox. In this hypervisor, we installed a guest operating system. So one example, Ubuntu 16.04. And then in this whole guest operating system, we installed the libraries that we need to run, for example, Qt4 to run graphical applications. And on top of that, we installed our application, for example, ITK Snap. And then we were able to give this whole virtual machine to someone, and they could just run our analysis. The problem of this is it takes a lot of storage because you need to install the whole operating system. You need to install everything, even stuff you don't need. And also you pay with performance because these virtual hypervisor systems in the beginning, they emulated hardware. So you were actually not directly running on the hardware below. You are actually adding another layer in between. And that made things pretty slow and not good for computing, really. Today, the hypervisors got a lot better. So virtual machines are better today, but still they require a lot of storage. Also, they require a long startup time. So because you have all the stuff in there, it takes 15, 30 seconds to start a virtual machine, which is not great. And because you have a lot of stuff in there, you need a lot of memory. So if you just think about you want to launch IDK Snap and you have to wait 15 seconds and it takes 10 gigabytes of an image file, that's just too big. And that's why containers try to solve this and make this a much slimmer thing. So you still start on the hardware, you have your operating system, but then you have this Docker daemon. And what Docker does is it tries to reuse a lot of the things that are in the operating system below. And you only add the stuff that you don't have in your container. Also the libraries you don't have, and then the application. And because you only add the stuff that you don't have yet, you end up with a much smaller image, so 0.1 gigabyte, for example, for this ITK Snap image. Also, because you don't have any other stuff, it's very fast. You end up with a 0.2 second startup time. So it feels like you have this application installed because there's nothing booting. There's no operating system. You're using the operating system that you're already on. And because of this, you don't need a lot of memory. So it's great if you want to analyze data. You're actually not consuming more hardware than you need. So that's what the difference between virtual machines and containers are. And I hope this now makes a little bit clearer what containers are, and you can already see hopefully some applications. But before we move on, are there any questions? So since this is a recording, there might not be that many questions, except Tom has a question.
No questions here, I don't think.
Okay, that was all good. Awesome, cool. Well, then I hand over to Tom, and he will take you through some more things.
Great. So the next part that we're going to be talking about today is why are containers useful? And I'm just going to give you, from a user perspective, from a neuroimaging user perspective, a lot of reasons why I have found containers useful throughout my PhD. So the first thing that we'll talk about is the reproducibility crisis in neuroimaging. So this paper here talks about glibc and some of the problems that Linux has when there is an update in these libraries that Stefan was talking about just before. So what this paper described was that when the version of this particular library changed, the floating point precision actually changed within these different functions that would be happening. So what you can see on this slide is that it's exactly the same function, but it gives a different output. Now you may say, this doesn't make too much of a difference. It's just a floating point precision, that's just a couple of decimal places. But this adds unnecessary computational noise. Yes, this is actually a big problem within neuroimaging. It does cause some error, but sharing your pipeline and making it reproducible is actually very important for us. So it can lead to significant differences in long pipelines, as we say. Okay, so I'll just give a couple of use cases. So for example, in my master's, I was asked to rerun a FreeSurfer analysis from 5 years ago using FreeSurfer 5.3. So what would you do? You go to FreeSurfer, you download and install FreeSurfer, you want the different versions, so you go to the version page, you find 5.3 wherever it is, down here somewhere. First of all, which one is it? There's 5. And then you click on the one that you decide. And then you look in here, what have we got? So we've got one on Mac OS, and we've also got one on CentOS 4 and 6. The problem with these now is that some of these actually won't run anymore on some of these older systems. Or if you have a Mac, Mac or Apple forces you to update your system at some point, and you will have to update from OS Lion. So it may be impossible or very, very difficult for you to run a FreeSurfer analysis from 5.3. Which is why containerization can be very, very useful. FreeSurfer 5.3 also causes a library error, which was the same library, I believe, that we were talking about before. So it may be very useful for you to use containers in this example. The next use case I wanted to talk about was scalability. So for example, you want to run fMRI prep on your pilot data. So you've got a bunch of fMRI data. This is you, and this is your scanner. This is Eamon, our radiographer at CAI, and this is our participant that we just got. So we've got a pilot data, and we want to run it through fMRI prep. So what happens then is that suddenly Eamon goes and scans 100 different people. And we've got all of this new data that we have to include in our pipeline. Now, thankfully, scaling with containers can make things very, very easy because you're using exactly the same code as you did in the first instance with your pilot data as you were with 100 participants. So what you can do is you can use the same software on different platforms. For example, now you're using a HPC instead of your crappy laptop. And you're using exactly the same code, exactly the same software, and it's all containerized within, say, a Docker or Singularity container, and you're running exactly the same code and the same input, which is why some of these things are so useful. So you can run the same thing and scale it up infinitely, depending on your compute systems. So yes, you can run the same pipeline with no changes, hooray. The next thing, running things on different operating systems. So example, you've got your terrible laptop here and you're not looking very happy, and you go away and you spend $2,000 on a brand new Alienware computer. Now what do? You've got a new operating system, for example. Let's say that you've changed from Mac over to Windows. Now what do? Well, with containers, you can run Linux software on Mac and Windows, and you can run Linux software on Linux as well, obviously. But containers will make your work reproducible and robust to operating system changes. So it doesn't matter what your underlying host operating system is. With containers, you can run the exact same sort of light operating system on your computer that you are using and the operating system that you're using at the moment. So that really helps in the previous example where you go from using your local computer up to a HPC, which will usually be Linux, and you don't have to change any of the code. Great. Our next use case is sharing. So here you are, you want to share with all of your friends. Next thing, in this example here is a paper that we recently published looking at segmentation of the hippocampus subfields. And what we wanted to do was actually share our pipeline, our analysis, our software, and our code, and all of our data all at the same time. And so one way of doing this is via Singularity and Docker through containers. What we could do here is actually publish an instance of our code, of our software that we use, the operating system that we used, and also all of the data, push it all into a single container, and then anybody who wants to use it can now reproduce the entire pipeline, including the data and including the code and including the software at the moment that it was run, and reproduce it exactly, which is a very, very powerful tool in the time of this sort of so-called reproducibility crisis. Okay, so what are some benefits of containers? So longitudinal stability of software we've already talked about. So for example, upgrading Ubuntu 16.04 breaks FSLView, which is why they developed FSLIs or fossilize. Reproducible. In my previous example with the reproducing all of the code and the software, if I go in and change my image, for example, if I change one of the underlying software packages, it's no longer reproducible. So yes, containers can be reproducible, but if you change something about the container, it's no longer reproducible. As Stefan has mentioned, containers are portable, which is great, and they are isolated, so they're not exposed to the host system. On top of that, they're quite easy to use. So the example that I will give here is that if anybody here has tried to install ANTs, advanced normalization tools, on the HPC or anywhere for that matter, it can be quite tricky without sudo access. When you're using containers, and particularly when you're using things like NeuroDocker, which we'll be talking about a bit later in the talk, it can be very, very easy to use and install software in a container. On top of that, some software is actually easier to use in containers. For example, fMRI Prep, MRI QC, and the BIDS apps and their integration can actually be very, very easy to use in containers because there are all of this documentation that surrounds using it in the container. And if anybody's seen the fMRI Prep website or any of the BIDS apps websites, they would know that a lot of it runs really, really well within the container rather than having to install SPM, AFNI, Ant, FreeSurfer, and all of the other Python tools that surround it, NiPipe as well, for example. So it can be really, really easy to use in these examples. So what are some challenges or some headaches that you can have? It can be hard to use at times, so it's a steep learning curve, and we will kind of see that in this talk. The syntax of the commands can be quite difficult as well. Docker generally won't work with high-performance computing systems, so if you have a HPC at your university, Docker generally won't be on there. As I said before, versioning of containers comes with no guarantees. Images may just disappear if I decide to remove my own image from my analysis pipeline. It's just gone, and there's nothing you can do about that. Things can just disappear or change. There are also licensing issues. So as many of you would know, for FreeSurfer, you need a license file in order to run it. The same with FSL, you need to actually sign a license in order to use it. MATLAB as well is also proprietary software, and the license is very expensive. You can run the MATLAB runtime within containers, but again, it does need a license for these other programs. The other challenge is mostly that it is a black box, so you don't really know what's inside the container when you use it. You can build a Singularity or Docker container on your computer and have no idea where it came from, who made it, or what's inside of it. So it's always good to check. And as we said before, the version of Singularity in Docker changes as well. Okay, so if there are any questions at this point, I would say not, because we're in the talk. So we'll just kind of continue on and say, how can we use containers? So in this section of the talk, we're going to be using the BIDS data structure, so brain imaging data structure, which you should be familiar by now if you're in the train track sessions. There was a BIDS talk, I believe. So BIDS, just quickly, and BIDS apps, neuroimaging tools and workflows in Docker containers, for example, FreeSurfer, SPM, etc. So all of these different tools run on the BIDS data format. So if your data is in BIDS, then you can easily run all of these tools and run all of these analysis pipelines very quickly. Okay, so we're going to be going through how to use containers at the moment. So the first one that we'll talk about is Hello World. So this is kind of an interactive type of session. So all of the code to this will be on the HackMD website, which we would have sent to you via email. It'll also be on the Mattermost channel. So the first one that we're going to be going through is the Hello World example, which is the easiest version. So if you have Docker installed on your local computer, you can simply type this command, which is docker run hello world. And hello world will show you that hello from Docker. This message shows your installation appears to be working correctly. So that's the simplest example of just running a Docker command. The next one that we'll be going through is just that Docker does cache these images. So what happened with the Hello World example is that Docker pulled a container called Hello World from Docker Hub, which is where all of these containers are stored. And it pulled it down into your computer. It's very, very small, only a few megabytes, I believe. And then what it did is run a program within Docker called Hello World, which printed that text to your screen. Once you try and rerun Hello World, it won't try and pull that container down again. So it already knows that you have the container. So this can be very useful if you're rebuilding containers with slightly different options, because it can actually cache the different parts of your container that are being built. Okay. If you want to show the images that you've downloaded, so in this case, we've got a few different Docker images in our system. Here we've got an Ubuntu, we've got Hello World here, which is the one that we just downloaded, and it's not even megabytes, it's a few kilobytes even. So what can end up happening is that it can fill up your computer quite quickly, and you can remove these, pardon me, you can remove these images if you want to. So in order to remove them, you can just use a command like docker rmi, which is remove image, and you can actually remove that hello world example that we were just looking at before. So our hello world one here, docker remove force is -f hello world, and what we end up doing is deleting that that image from our computer. And then if you want to re-download it, you just run docker run or docker pull, the same as before. Okay, so now what we can see here is that that image is now gone. So it used to be down here, and now it's gone from our system. Okay, so the next one, which I would say is probably the most practical or useful example that most of you will want to use, is using fMRI prep. So as many of you will be aware, fMRI prep is a general purpose pre-processing pipeline that uses for fMRI data, that uses the best parts of many different tools. Maybe saying the best parts isn't a great way of saying it, but good parts from many different tools in order to make a sort of standardized pre-processing pipeline for fMRI data. So these are all of the different steps that are performed within fMRI prep, which includes outputting some confounds at the end, storing nuisance regresses. It's got the works. It's got everything in it. It's got free surfer reconstruction if you want that. It's got AFNI. It's got spatial normalization using SPM. It has everything. So there's about 6 or 7 different software programs that are actually used within fMRI prep. Now, if you wanted to use this normally, you would need to have free surfer, SPM, MATLAB, AFNI. You would need to have all of these different NiPipe dependencies installed as well. But with containers, they contain all of that software and all of the necessary components for it within a single image, which can then be run, which is quite powerful. So let's go through a quick example of how to run a Docker image of fMRI prep or Docker container for fMRI prep. So the first thing that you would need to do is, of course, download the container. And if you'd like to go to the fMRI prep website, you can see how to do that. But it's simply just docker pull direct lab fMRI prep latest, and that will pull the container for you. So the main command to kind of understand here is that you need to use docker run. And that's the main thing that we'll be going through today, is running the Docker image and including all of the different variables that you need in order to make fMRI prep run. So we won't be going through all of these different variables today because we want to keep it nice and simple. But if you do have any questions about what the different variables mean, how they work and how they interact with the container and the operating system, please ask on the Jitsi room or on the Zoom channel here. On any of the Mattermost channels as well. We're also on the help desk. You can see here that this is the name of the container. So after we've put a few of our different variables, we put the name of the container. And then these are the different parameters that you'd need to make fMRI prep run. So these ones here, for example, that's our data directory, our out directory, for example, and our work directory. Once we hit run and once we hit enter, what fMRI prep will do is actually run through the bids validator first to make sure our data is in bids, tell us a little summary of everything that's going on, and then it will start running fMRI prep version 20. So what we can see here is that it's running free surface subjects directory is here. And the really interesting thing here is that if I then kill this job and go outside of the container, and I try and run recon all outside of the container, I'll get an error thrown. Recon all, of course, being the reconstruct pipeline from FreeSurfer. So you can see that recon all isn't on my path and it isn't held anywhere within my computer, but it is within the container. So that means that I can run recon all and FreeSurfer from within the container, but I can't do it from without the container. Okay, so our next example here is pulling the image to a HPC, so a high performance computer. So here you are sharing all of your results from project to your friends after you've run all of that data on the HPC. So our next example, we've done our 1 participant, and now we want to do 100 participants on fMRI prep with our HPC to impress your boss. So Docker doesn't run, first of all, because the HPCs don't allow us to use Docker. So what we need to use is Singularity. Or we could install all of the software, which would just be dependency hell, basically. So what we want to do here is push, well, we can do one of 2 things here. We can either push our Docker image that we've just made to Docker Hub and pull it on the HPC using Singularity, so you can run the software without root access. Or we can just pull the image directly from Docker Hub. And in this case, because we're using fMRI prep, what we're going to do is just build the image directly from Docker Hub using Singularity. So this may seem a little bit confusing at this point, and we kind of recognize that. So if you do get kind of mixed up between these 2 things, just kind of think about Singularity as the one that you're going to be using on the HPCs, and Docker is the one that you can use locally. And generally what I've found in my experience anyway, is that I mostly use Singularity these days anyway, because you can build Docker images from Singularity. And that's exactly what we're doing here. So what we're doing is building a Singularity image, which we're going to be calling fMRI prep latest.singularity image. And we're going to be building that from this website. And what we can see is that's just telling us that it's Docker Hub, Poldrek Lab, fMRI prep, and latest. And then with that single command, after we've made our images directory, it will start the build and it will copy all of these different things. And we don't really need to worry about all of this different stuff that's happening. But at the end of it, it will actually complete the build with a file called fMRI prep latest.singularity image. And that Singularity image can be used in basically the same way as our Docker image from the last step. It can be used to run fMRI prep. So now we can actually do fMRI prep on the HPCs using Singularity, which is really, really powerful because now we can parallelize our jobs across hundreds of nodes or whatever your system is on your HPC. Great. So I think that's a good place for a pause, but we're going to be going on now to what a simple Docker container kind of looks like. So this next part of the talk, we're going to be going through how to actually make your own Docker containers. So if you're fine with just using Docker and Singularity for fMRI prep or other BIDS apps, this would be kind of the advanced section of the talk. But for those of you who want to do your own things and put your own software into your own Docker containers and Singularity containers, this is the section for you. Okay. So these slides and these code are all on the GitHub and also the HackMD site. So if you do get a bit lost, you can go through all of the code. It is a little bit, it can be a bit difficult to look through, but it's also all commented. And again, if you do have questions, feel free to ask us. So what we can see here is that this is VS Code. And when we do create a Docker file, which we just call Docker file, a cute little Docker whale appears as well. So we know that we've got a Docker image. And this is our headachy Docker file. Oh, we've got a headache. So for this, I'm not going to go through the syntax of how to create your own Docker image. But what you do need to understand is that in order to make a Docker file, it needs to have the Docker format. It needs to have all of the different things that you want to include in your Docker image in different lines, on single lines even as well. And the syntax is all kind of readily available online if you want to have a look through how to create your own. We've got some examples on the GitHub as well. And we're going to be showing you how to simplify this with NeuroDocker in just a moment. So for the moment, this is kind of the structure of a Docker file. And what you want to do is you want to build that Docker file, right? So you want to create your own Docker image now after you've decided what type of software you want to put in it. So in our example on HackMD, what we use is ITK Snap. But in this example here, we're not going to go through exactly how we're doing it. But the point that we made here is that we have this folder, which is called build ITK Snap Docker, which contains that Docker file, which is here. So we can see build ITK Snap Docker, and the Docker file lives within that container, so within that directory. And what we want to do is, in its simplest invocation, just use docker build and point to the directory that contains the Docker file. And this may all just look like garbage, but it's actually building each step, which is each line from that Docker file. And it's doing it one by one and using the case for each time because we're already built in this case. Okay. So now that we've built our Docker container, and there are plenty of examples of how you can create your own Docker containers, so we probably won't go into that in too much detail. But what we're going to try and do now is actually use the Docker container interactively. So we're going to go into the container. So we're entering the matrix here, guys. What we're going to do here is run a graphical application, which does require some wizardry using Docker, but we're just going to keep things simple and actually run the Docker container interactively by going inside of it. So what we can do now is actually enter inside the Docker container. So what we can see here is that we're sitting within my C users Thomas file, and then we go inside of the container, which is called ITK snap, and that's the name of the container. Then we're inside of the container here in the next line. And then what we can do is simply run the command that we normally would after exporting our display variable. Don't worry about that too much. What we can find here is that when we run ITK snap from inside the container, we get basically we can run ITK snap, and it's a graphical application. So this is really cool because I don't have ITK snap installed on my computer, but it is installed within the container. So then I can view images by using the container quite successfully. Yay. This would be another question slide. So if anybody has any questions at this point, I know that was probably a hard one to get through, but if you do have any questions, let us know. Okay, for those of you who tuned out because that was all too difficult, we're going to make it nice and simple for you now. So what we'd like to do now is distribute the pipeline that we've made or distribute our own software and do something a little bit more advanced, but use simple tools. So we don't want to actually create our own Docker. Well, we do want to create our own Docker container, but we don't want to have to write our own Docker definitions file for everything. So NeuroDocker is a project that helps building imaging pipelines in Docker, and by using this project called ReproNIM, Reproducible Neuroimaging. So what we want to do here is basically create our own Docker and Singularity definition files so that we can create our own software pipelines very, very easily. So this is just a screenshot from the NeuroDocker website. And what we can see here is that there's all of these different software packages that we can use and actually install within a Docker or Singularity container. So we've got SPM, NeuroDebian, Mrtrix, FSL, FreeSurfer, all the rest of it. There's also NiPipe in there too. So using just a few simple commands with NeuroDocker, we can actually make our own Docker files and Singularity definition files in order to create our own bespoke Docker and Singularity images, which is really, really cool. So for those of you who just want to make a Singularity image with FreeSurfer and FSL on it so that they can do recon all, this is the part which is probably the most important bit. So here's what let's say we want to look at some images of brains. So we're going to generate a Singularity recipe using NeuroDocker. And the exact commands for how to do this are again on the HackMD website. Don't worry about this, this is the output, but this is the input. So this is all we had to do in order to make all of this. So it's a NeuroDocker generate, and we want to make a Singularity image. And what we might do here is, define the software that we wanted to use. So for example, in this case here, we wanted to use ITK Snap version 3.8. And then do a bunch of other stuff that might be important for making ITK Snap run. But here, NeuroDocker actually makes it really simple to create these types of definition files. So what's happened here is that with all of this, this short few lines of code, we've created all of this Singularity definition file, and we can make a Docker file as well, so that we can build our own Docker files from NeuroDocker very, very easily with just a few lines of code. So for those of you who are just looking to make a really simple Docker file or a really simple Singularity file, NeuroDocker is really a good place to start. Okay, so the last couple of things that we're just going to go through today are building Singularity containers as well. So let's say that we just created our NeuroDocker image that has FreeSurfer on it, for example. We want to now use that FreeSurfer container on the HPC. So what we can do now is actually build that, that container on the HPC itself using the latest versions of Singularity. And what you actually do is build the container online and then pull it down into the HPC. So with just a few lines of code here, what we can do is take that Singularity file that we have created from NeuroDocker and use it on a high-performance computer or even on your own computer and build it remotely, which is quite useful if you want to make your own analysis pipelines with different bits of software from all over the place, or even your own software and your own data. And you can build it all online. Cool. So what you'd have to do is just follow along with the code that we've put online, but basically remote log into Singularity, create this API key is what it says here, just follow the instructions, it's super simple. And then what you can do is build your image using the Singularity ITK Snap Singularity definition file that you made with NeuroDocker. So your steps here would be create the NeuroDocker Singularity definition file and then build it remotely on the HPC, and then you're good to go. You've got your Singularity image that you can use, and it's got all of the different software that you required thanks to NeuroDocker. So it should be a fairly straightforward process. And yeah, if you do have any questions, of course, let us know.
Can I add two little things to this? If you quickly go back, I just wanted to, we don't have it in the slides, but there's two comments I want to make. So the first one is ITK Snap. We added this to NeuroDocker for this example. So if you're running NeuroDocker playing from the repository, ITK Snap might not yet be in there because it might not have been merged. So if you run into an error, the problem is we added that. The second thing is this remote building, as Tom said, is really, really cool. I ran into one problem yesterday where it said there's not enough storage available. And the thing is, if you have this problem, you can only build an image that's 11 gigabyte in size. So if you store images in your Singularity library online, and your library is basically already full, you can't build a new image. So it will not tell you that this is the problem. It will just tell, oh, you don't have image. You don't have any space for a new image. So I just wanted to say that because I noticed that yesterday, so we hadn't added to the slides, but I thought it's an interesting one.
So the image can only be under 11 gigabytes or 11
Correct.
gigabytes in total? Okay.
So exactly, so every image, exactly, the maximum size of an image is 11 gigabyte. And then if you keep your images in this library, you decrease this thing. So I had built multiple images and I basically was filling up my storage online. And I didn't know that I have to delete them if I want more space. So I thought probably people run into the same problem. So I just mentioned it.
Definitely people will run into the same and many other problems, I'm sure. Okay, so yes, here we are, happy that we've got our Singularity image. At this point, there'd be more questions, but we'll just move on. And I'll hand it back over to Stefan at this point, who'll be talking about transparent Singularity.
Yeah, so that's basically now, if that was the advanced part, now we're going into a bit the geeky part. So when we started with using Singularity for our analyses, we wondered, okay, do I now always have to type Singularity, exec, ITK Snap, something, ITK Snap? Because I hate typing personally. So we thought, no, we should make something that makes this easier. So Tom and I were thinking about it, and we came up with let's just build a tool that automatically writes wrapper scripts around it, so that basically it ends up that you don't even you don't even have to type all the singularity stuff around it. So you just type IDK snap and it just works. So that was the goal. And that's how this project was born. And we call it transparent singularity because ID, you feel that that singularity is not even there. It just makes your stuff work on the HPC. So how does it work? So we'll just show a quick example. So in order to have it to work, you need to clone the transparent singularity repository, and then you already give it a folder name. So I'm just taking example FNI 20.106. So it will pull that thing, will create a folder. Then you cd into this folder. And then you can run the script. So we call it run transparent singularity. And then as the argument, you give it the container name. So there is a list of containers that we have made available already, but you can also just add your own container there. You just need to, you build your singularity file, you put it there, and then you just call that name. And then it will not try to pull it from our registry, but it will just use your local container. So, and when you run it, what it will say is I'm installing the container into your system. And for this stuff to work, you have to set up bind paths. So we described this in the repository. But after doing this, it will be really easy to use. So what it has done now is it has created for every binary that's on a certain path. So that's why we had in the recipe that we showed earlier, we had this variable that we call it deploy path. So we introduced that in order to make transparent singularity work. So it basically looks at the deploy path, and you can have multiple deploy paths. It will look for executables inside the image. And what it will do is it will automatically create a shell script for every executable in the image. So, and these wrapper scripts are very simple. They will basically say, okay, I want to work in the current directory, and I want to call singularity. I want to execute this. I want to work in my current directory. Then I want to call a certain container, and then I want to call a certain command in there. And I want to pass on all arguments that I gave this thing. So it also what we do in addition is we create a module. So lots of HPCs use the LMOD module system. And when you then hit module avail and you have your module path set up to the folder where we create these modules, you see suddenly, oh, now I have FNI and FreeSurfer in your module system. So you can extend your own HPC with your own modules, and everything runs from inside the containers. So the beauty of it is that now when you run module load FNI, you get FNI on your path, and then you don't have to type singularity or anything. You just type summa, and the viewer of FNI will just open, and if you're lucky, it will show you Humor Simpson. If not, it will just show you a plane or other things. So it always starts with random thing, but it shows that we can run graphical applications. Again, we actually logged in remotely into HPC, and we just have mobile XM, which provides a local an X server, and we can actually render stuff on our Windows system. And now we can just continue using NiPipe without actually changing anything in NiPipe, because it feels for NiPipe like if these tools would be installed natively. And because we combine with the module system, you always are in control of what containers you want on your path and what you don't. So we're using this since, I think, 2 years now, and we're pretty happy with it. And for us, it just made our life a lot easier, because what this basically allows you to do is you can start with your analysis locally on your computer, then you move to a bigger workstation, then you upgrade your workstation, and then you move to different HPCs. And everything is very, very movable, very portable. And this is pretty much what we had planned for today. So we thank everyone for their attention, and now we're looking forward to questions in the question and answer. Thank you.
Thanks.
Hey, we are live, and I'm inviting As far as I can see, Stefano, and please say hi to the chat so it will be easy for me to find you and invite you. Hey, we are live and I'm inviting. And I'm hearing myself at another browser. As far as I can see, Stefano, and please say hi to the chat so it will be easy to form. Okay. Hey, I can. It's creepy to hear you from other computer. So I just invited Tom and Remy. Yep. I just noticed one question and I copied it and I know it's answered. But if there are other questions, feel free to ask. Hey again. Hey.
I think we can invite everyone on stage. I mean, Stefan and Tom, because I want to talk to them live. That's
they are
much
accepted and connecting. You were
cool. Awesome. Hello, Tom.
Hey.
Hi, how you doing?
Good, and you?
Can you hear me?
Very good.
We can hear you. Fantastic.
Oh, okay. I can't hear you, so I need to check my sound settings. Oh. It's the first time crowdcast for me, so.
Yeah, first time experience. To be like, you lose your what is going on here?
Okay, good. My browser found my headphones. So, okay, I'm good. If you can hear me, I can hear you.
Yeah, we can totally hear you. Good,
awesome.
Good. So how is Crowdcast?
It's good. Yes. The stream broke for me halfway a few times, so I had to restart my browser, but then it was working. So
okay,
yeah,
that is interesting. Not sure that happened before. What did I want to say? So if people have questions, feel free to ask them. I think one way we can also do this is that I can, for example, just leave my space on Crowdcast screen, and then someone can come and ask the question live. Otherwise, we can have a bit of a chat. Just because how are we doing in terms of time? I'm so hard for me to keep track of all the things because we're trying to be on schedule.
We are good.
We are good. We have got
we have time because the earlier session, the video was shorter than expected, so we have time.
Cool. Okay. I mean,
right.
if
so
no one has.
In the Australian session today, we had a lot of questions about the images in the slides. So people were asking what animals we showed. So we had, I think we went a lot of overtime because we were guessing, okay, that's a barking owl and that was a swamp wallaby and things. So if people want to ask questions about the animals on the slides, you're very welcome.
Yeah, actually, I was right before coming here. I was with the rest of your team in Gathertown, chatting with them, and they were asking where's the wallaby from or something like this, and I had no idea. But apparently, that's one of the questions I'm supposed to just like pass on.
Yes, I think it started because I was confusing a question from someone in the chat because they were asking, okay, what is an image? And because they were asking about a Docker image, and I thought they were asking about the images on the slides. So I was explaining what the animal is they're seeing, but they're actually really interested in the Docker images.
Wow. One question is about how to build a container and how to share the receipt, as I understood. I'm really paraphrasing the question, but you answered that, I know.
In the previous chat?
Yeah, at the previous chat. I had a discussion with a colleague of mine, sharing receipt versus build container. Sharing receipt is easy, quick, and lightweight, but it's if there's a software update and installation without specifying the version, reproducibility might actually be lost. What's your recommendation about it?
Yeah, exactly. So we try to answer it a bit in the chat already, or in the question. So it's tricky, exactly. I think it depends on what you want. So the recipe files, they are very easy. They're just text files. You can host them in Git and you just archive them there. But the problem is that building a container today and building a container tomorrow will result in different containers because the underlying package infrastructure will change and you will not get a bitwise reproducibility. So I think if you want reproducibility, you have no other way of archiving the images in a repository and in these registries. So the Docker registry does this already. And they provide you, I think, infinite storage. So I haven't found the limit on the Docker repository. I found a limit on the Singularity registry. So that was easy, 11 gigabyte. But so far, and that's why we still build everything in Docker and then convert to Singularity, Docker gives us the way of archiving all our images we ever build, and we can always pull them back to Singularity. And also another reason is Singularity changed quite a bit from 2.4 to 3 version. But it was always able to pull Docker images. So by archiving all our images in Docker, we were always able to port the new containers into the new Singularity version, which was always quite helpful.
Mm-hmm.
A problem we have a little bit in Australia, I think it's not a problem in Europe, is the connection to the Docker library is slow because I think it's mostly hosted in the US, and I think they don't have a CDN in Australia yet. So I actually built up our own Singularity registry here because we're pulling a lot of containers on our HPCs. And the problem is that as soon as we do off-net traffic, the admins ask, what are you doing? Because someone has to pay the bill in the end. We basically host our images on net, so they're really fast to pull them into our different HPCs, and no one has to ask us questions while we're pulling terabytes of images around.
Yeah, that could be an issue in the long term, definitely.
Yeah.
I guess one of the questions that we had in the chat in the Australian version was the difference between images, recipes, and containers. Maybe Stefan, you can talk to. We added that in this morning as well. So the question was, what's the difference between an image, a container, and a recipe? So Stefan, you want to take that one?
I can, yes, exactly. So the recipe is a text file that describes, that has the things in there that tell it, oh, install that package, download this thing. So really the instructions for building the image. So the result of taking the recipe file and putting through the build process is an image file. And the image file really contains the binaries that you created with this. And then if you take this image and you launch it, with a container and be Singularity or Docker, then you end up with a container. So that's, I think, how we define these terms. Mm-hmm. And I think people understand that concept then quite easily because it can get a bit confusing with recipes and images and containers. And, so we refer to container. That's the running thing in the end.
Yeah. And I have a question because it's something I often run into. What would be your advice to minimize the size of the containers? Because sometimes they can grow pretty big. I'm not sure whether it was addressed in the video because I've been too busy multitasking to actually check. So please.
So I was seeing you edited the website, yes. So there are different ways of dealing with it. So I think the first one is by making sure that you're chaining commands as much as possible. So basically run everything in one line because every command you put in a Docker file will create a layer and every layer will create space. So even deleting something will create another layer and you will actually not get rid of this layer. So that's one thing. By creation, you can make already sure that you try to be as efficient as possible. So then there are things like NeuroDocker does this very, very smartly. They have a lot of things in there to save space. So they do -no install recommends. So you don't install libraries that you don't need, for example. And they clear caches during building. You can do multi-stage builds where you build something. Let's say you want to build something from source. So you pull all the source code down, you build a package, and then you store that package outside the container. And then you have a new container that you launch where you then just pull in the package and install the package that you just built in a previous container. So these are staged builds. That's one thing you can do. And then there is something very sophisticated that, again, NeuroDocker does. If you look at NeuroDocker, they have a way of minimizing an image. So what they do is you can say, I want an image that can only run recon all. So they go in the image and they trace everything that gets executed and touched in the image. And then they remove everything that hasn't been touched by the process. So you end up with a 100 megabyte free surfer image that can do recon all. And it will run everything that recon all needs, but nothing else, which is sometimes exactly what you want on an HPC. So if you look at these minimized free surfer images on NeuroDocker and see how they do it, it's 2 elements. So that would be my recommendation. And then if you have a Docker image, that works with Docker images. And then if you minimize Docker image, you simply pull the Singularity image and you have it on the HPC.
Okay, yeah, I tend to point people in general to NeuroDocker and how they do the minimization because then you don't have to think about the details and they just. They've done an awesome job there, definitely. Yeah.
So we have a new question. There is one, while creating a new pipeline, is it better to create one container or multiple containers called in a main script? So that is an excellent question. And I think the answer is probably longer than you're hoping for. The short answer is it depends, like a lot of things. So basically, what we do the project we presented in the end, Transparent Singularity, the aim there is that we have every tool in a little container. And what we do is Transparent Singularity is basically a layer that allows us to combine different containers. And the good thing is we can then use NiPipe, for example. So what we do is we install NiPipe in Miniconda in our HPC, and then we have Transparent Singularity, and then this calls into multiple different small containers. The advantage of this is I have small containers. I can easily update the containers, and often I try out different things. So I need FSL 6.03 or FSL 6.00, and sometimes you just want to change the version of things. And this makes it really nice and flexible. But then when you're done developing a pipeline, I think it does make sense to put all the tools that you needed. For example, so Tom just published a paper where we released the pipeline in one big container just for reproducibility of the results in the paper. I think this makes a lot of sense. This would not be the container we would then use on an HPC because it's like 7 GB, but it is the container that did the paper. So I hope this explained it a bit. And Tom, do you want to add anything there?
Yeah, I think for that specific example, we actually have two containers. We have one container that's specific for reproducing the entire pipeline and reproducing the results in the paper, which, as you said, is 7 GB. And then we have a separate container which just contains the software that we used, which would be useful for actually if you wanted to go and use the pipeline somewhere else. So it does, again, depend on what you're doing. And I think with fMRI prep, they include every single dependency in NiPipe and all of the rest of it. And that is, I think they've got it as minimized as they possibly can, but it is still a very massive image. Yeah. It's a big chunky boy, yeah.
Yeah, definitely. Yeah. Just pulling that one is always a bit of a trouble, definitely. Yeah. I have a question, and once again, because I've not watched the video, it's going to be just like, I mean, mostly you already addressed it. Containers and MATLAB. Discuss. What's the easy way around?
Tom, you or me?
Well, I'll start and you can add to it because there's always more to say. So I guess the first thing to discuss is the MATLAB runtime. So you can run the MATLAB runtime through Docker and Singularity, and so the first way that you can do it is through NeuroDocker, which works quite well. And it's very, very simple to install the MATLAB runtime, which you can run SPM, which is a program that runs through MATLAB. Compiling your MATLAB code and use the RC. Yeah, so you can use the runtime environment in order to run things like SPM in Docker or Singularity, and that works quite well. However, there are a few other things that can't be done within the runtime environment. So I think, Stefan, you could talk about Octave, or what's the other?
Yes, exactly. I think a few things are hard for users. I mean, the first thing is, I think not everyone can compile MATLAB code because this is a license that not every university has. So I had people who could not compile stuff. And the reason was that the university didn't purchase this plugin. Maybe they got something wrong, but that was one thing I saw. So yes, I think Octave is certainly an option. If you're developing code on the HPC and you want to change things, then Octave is good. And I know, for example, the SPM guys, I think Guillaume is, for example, in the chat, he spent a lot of time on making SPM work in Octave. And the way he did it is he fixed a lot of things in Octave. So if you're using SPM, then I think Octave is a really, really good thing to use. And I think it will help there. Otherwise, you could, if you really want all the MATLAB thing, you can install it in a container. You can make it work. You put your license file in there, and if the Docker container can see your license server, you can run MATLAB in a container. There is nothing wrong with it, except that you end up with a 16 GB container. And then there's the other thing. You could also say, well, okay, maybe I look at the different languages, right? Of course, that's also another way. You could say maybe Julia is something really cool as well, and start doing things in Julia. If you want to run on HPC, it might be not a bad idea at all in the end, because you actually might get much better performance than in MATLAB, and it might be just much better suited. But yeah, legacy code is always an issue. So I think it's, yeah.
Yeah, definitely. So you're not saying we should rewrite SPM with Julia, right?
I'm not sure if I think I would love it. I would love to see SPM rewritten in Julia. And we'll see, maybe that happens. And yes, so there's two thumbs up for that. Yes, but I think as of now, I think it runs really well in Octave. So yeah. But yeah, if you're using fancy object-oriented programming in the newest MATLAB language features, Octave will just cry and run.
Yeah, that. Usually my recommendation is just run things. I tend to maybe run things on Octave just by default, just to make sure they're not broken. So that, that's like my rule of thumb in general.
Yeah. Also, there was another thing in the... Who knows? Maybe there is a Julia version one day. Who knows? Exactly. There's also another thing. Exactly. MATLAB license and HPC are a big problem. I think we had this problem in Zurich very often. You tried something running on it on a normal day, and you would run out of statistic toolbox licenses. It was just always problematic.
Definitely.
Yeah, but yeah, exactly. They updated this so you can actually run it out. So yeah, so on our HPC here, we have actually local licenses that don't have that problem. But
okay. Yeah, I don't want to turn that into a MATLAB discussion. So if there are any other more container-related discussions, because otherwise we're going to start a war, and we don't want that.
Yeah, I mean, maybe just another topic if there are no other questions. So we had a question today: can I use a container like a virtual machine? And I think the answer is yes. And we actually had a Brainhack project on this. So it's called VNM, the Virtual Neural Machine. And what we did, and it's kind of working, is we're launching a Docker container, and then we just launch a browser. And then in this browser runs no VNC. So you have VNC in the browser connecting to a real desktop session that's running in there with LXDE. And we have all the graphical applications in there running in Singularity containers. So we run Singularity in Docker containers. Yeah, it's really cool. So have a look at the project if you're interested in this. The idea is, again, yes, you could start on your little notebook in this little environment, and then if you're happy, you shift to an HPC, and you can take this environment with you. So I think there's a lot of potential there, and we're looking for people who would like to contribute to the project. So if anyone is keen on playing with containers, getting their hands dirty, then that's, I think, a perfect project to get started. So we need people building containers, testing containers, building applications for it, integrating things. And yeah, that would be really cool. And I think there's a question, is there something beyond MATLAB and Julia? I would say, I think, C++ is great. So yeah, if you want to spend your day coding and not getting anything done, then I think C++ is awesome. and you get really fast code, right? There's nothing wrong with it. I did that the whole last year. And it was a fantastic learning experience. And I really appreciate higher level languages now.
Nice. That's a nice way to put it. I've posted a link to once again to the Turing Way book, which has a chapter on environments, and it's a good overview on not just containers, but like virtual machines and this type of things, and how they all relate each other. And in general, the Turing book has plenty of good resources, so I highly recommend that in case you're still confused about a few things. Yeah, I think we are almost out of time. I have one final question, and it's an animal-related question again. Did you decide to put all the animals after having seen Adina's video with her rabbits in it, or not at all, or was completely unrelated? Yes. Because now I'm starting to think that there's something in the train track this year where there's a theme. We have to have animal-related content. So I'm like, was that just by chance?
Exactly. So I'm subscribed to the Darlight channel on YouTube. So I think last week a new video popped up, and I thought, oh, cool, a new Darlight video. So I saw it and I thought, oh, cool, it's for the train track. So we were just building our dogs, and I thought, okay, their animals are cool. And also we thought the talks are quite dry, and when we're streaming them, we need a break. So we thought just adding some light things in the middle is really, really good. So I just looked through a few photos I had. So that's why there's a swamp wallaby in there. So I put some Australian animals in there. And also the barking owl is a really cool bird. And the first slide is a really cool one. That's a tawny frog morph. So it's it's also some kind. It's not even an owl, I think. So it's a really cool Australian bird.
Okay, cool. Okay, so there was a connection there. I wasn't sure, but I was like, this is just too good to be true, to be random. So there must be something
exactly.
there. Brilliant.
And also
awesome.
the GIFT talk that we made, I tried to refer to Adina's talk by if you want to get into the rabbit hole of data-led and things. I'm not sure if anyone got that reference.
We didn't get your talk here, so that was that was amazing. Oh no, wait, we did. I don't remember. I'm losing track. What did we do? I'm sorry. I'm just confused by now. But I like how just things were getting cross-linked between each other. It's really cool. Okay, maybe should we wrap up and introduce the next one? But I'm not sure who. Yeah.
Cool. Thanks, everyone.
Thank you, everyone.
Yeah, there should be a cross where you can just leave the stage if you want.
Awesome. Thank you.
Thanks for coming. Thanks for traveling halfway around the world.
And reach out if you play with containers and you get stuck. Let us know. We're happy to help. Awesome. Bye-bye.
Really great.
Ciao.
Ciao.
So next one is scikit-learn and nylearn, and I think we should have, I'm not sure who is on stage with us, or who should come on stage with us to answer the question after the session. I think it is, yeah, Michael. I'll try to figure out where he is so that he's ready for the Q&A. And okay. I think in the meantime, we can just wrap this one up and move on to the next one.
Yeah.
You're good with that?
Yeah. For the nylearn streaming, question answering, I won't be there. I'll be just rebooting everything for the session.
Okay.
Yep. Just ending this one and see you in minutes.
Exactly. See you later, people.
Hi everyone, my name is Michael Dayan. I am from the Foundation Campus Biotech Geneva in Switzerland. So I'm very happy to be here today to present this introduction to machine learning with scikit-learn and nylearn for the application to neuroimaging. So first of all, I would like to congratulate the OHBM Brainhack committee for pulling that off remotely. And special thanks also to Lisa and Remy for organizing this training session and for the invitation. Thanks a lot. So the content of this session is on GitHub here. So I guess you already have the Jupyter notebook and the data, but if not, you can quickly get them at this link. So I will present both an introduction theoretical to machine learning, just an overview, and then we'll see the application with sklearn and nylearn. These packages are all written in Python, and they are embedded in a very strong community of open source software. And what is particularly amazing with these packages is that they have an excellent documentation with very rich examples, which are very well made. And actually, there were a few talks during the nylearn days a few weeks ago with Gaël Varrocco, Bertrand Thirion, Elisabeth Dupré, who was core developers of nylearn. And they explained that it was actually the way they code is documentation driven development. So they really put the user at the center, thinking ahead of what would be needed to be able to start using the packages. The examples are very well made, and that's why I'm going now to present an overview of machine learning and the typical framework of scikit-learn, but I'm not going to go in the details in the machine learning algorithm, especially considering we have 90 minutes and it will be already quite busy. And for those who are in EEG, because NaiLearn is more focused on MRI, for those who are in EEG, there is also the MNE package, which has the same mindset. So example driven for easy access by the users to the package with very well-made examples as well. And it's not a coincidence because the core developers actually overlap in between these different packages. Many are from Inaria. Okay, so let's start. So before going into the machine learning details, I often like to take a step back. And so I would like to have an understanding of why machine learning is useful for scientific research, at least some aspects of it. I would say that one of the core hallmark of science is to have testable predictions. So, for example, for Aristotle's theory of gravity, his theory was that objects fall at a speed proportional to their mass. So if you take two objects, the one which weighs 10 times more than the other will fall 10 times faster. Galileo's theory, in contrast, was that the objects fall at the same speed. So obviously you know which theory could be tested to be right. And one experiment was done actually just a few years before Galileo's in Netherlands, showing that two objects of different weights actually fall at the same speed and there is not much friction. And another fundamental aspect of science is generalization. So you want findings to apply in other contexts, at least in other experiments than your own. And obviously Galileo's law was found in found to be true in many different contexts, including in the moon. So there was David Scott as part of the Apollo 15 mission who reproduced this experiment with a feather on a hammer. And he shows that they actually fall at the same speed. So now let's keep with this falling objects idea, and I would like you to do a thought experiment. So imagine you are still in this 17th, 18th century period, and at this time the problem of shooting weights, objects, was really a big issue to solve. So imagine you are a scientist at the time, working at university, and to make ends meet as a side job, the only thing you could find was to throw cannonballs with cannons. Maybe you look like more the picture on the right in the 18th century. And your mission was to try to predict the range of the cannonball according to the angle of the cannon. And that was actually not easy at all, because at the time there was still Aristotle's idea of trajectory in every scientist's mind. And this idea was that cannonball would just shoot straight and then suddenly fall on a straight line, a bit like the coyote in Roadrunner. So obviously with this scientist's idea, it was very hard to predict if you could hit the target according to the angle of your cannon. So there was some efforts toward the end of the 18th century to have this table, to be able to have some ideas of if you were going to hit or not according to which angle you should choose. But there was not really any good model. So to do your mission, you actually need three things. You need to take measurements, to find a way to make predictions, and to assess the generalizability of your prediction. So to know how much your prediction will vary in different situations for new data sets. So let's start with the measurements. So typically what you will need is a set of observations, also called data points, samples, or examples. And in this case, it will be shots. And with these shots, you will need a set of features. So features is a characteristic of your observations, like the angle psi of the cannon, the initial speed of the cannonball, its mass, its radius, etc., etc. And then you want to predict if it hits the target at, for example, 100 meters. And that's your outcomes. They are called labels. And all this information is a data set. So you need a data set of observations. These observations are characterized by features, and you measured your desired outcomes that you want to predict later, which is if it hit your target or not. So actually, the choice of outcomes and features is extremely important and is really fully part of your research design. So in our field, typically the observations could be the subjects, and the features will be characteristic of the subjects and the experiment. So the age, sex, maybe some values in the region of interest in the brain, so RI1, 2, etc. And the outcomes could be if the subject has a disease or not, or if he's a normal control. But you really have to think of what your outcome should be. Actually, 10 years ago, there was this initiative, the Research Domain Criteria Initiative by the National Institute of Mental Health, who tried to push for a different approach. So instead of having this binary diagnostic outcome, trying to have something else, because this binary outcome can actually impair the understanding of the disease if all the research studies are too much focused on this approach. Because people with the same diagnostic can actually have very different symptoms, and people with given symptoms can be likely to have an additional disorder, which will not be even considered. And the difficulty of having a clear diagnosis may actually cause researchers to exclude patients because they will not fit the gold standard of the diagnosis criteria. Actually, this criteria can be quite arbitrary sometimes. So the idea is really to choose, instead of this binary outcome, to choose biological, physiological, and behavioral dimensions. And in this way, you can explain different diseases with the same outcome. They are more general, and you can better understand the link between your neuroimaging biomarkers and the disease or other diseases. So in a case, for example, instead of having as outcome if we hit our desired target at 100 meters, a better outcome could be the range, because this way you could generalize to different situations and better understand your system. Okay, and now we need to find a way to make predictions. So imagine your original data set is this one. So it's not a trajectory, is on the x-axis you have your experiment angle, cannon angle, and on the y-axis you have the range, so how far your cannonball went. For example, for around 48 degrees, it went 75 meters. So if you have this data set, you have different model, for example, you could propose. You have just a straight line. You could have a parabola, so a polynomial of degree 2. You could have even a polynomial of degree 5. And all these models, they match your training data, your data set, I mean. So the question is which one to choose. So we have to find the least bad model, let's say. So we have to define what is bad. So bad is the error you make. So this error, you can measure it simply by looking at the difference between your dataset and what your model will predict for this dataset. So let's zoom in to understand it more clearly. Imagine you have this data point x3 here. So for this point, the error will be the difference between what your model will have predicted for this data point and what your dataset actually is. That's your error term. So then your total error, how do you define it? So if you just sum the errors for each data points, there will be a problem because you have both positive and negative errors. So they will kind of partially cancel out. So you could take the absolute value of all these errors, and that's actually the absolute error. It's called the absolute error. Or you could take the squared error, which has nicer properties. So you just sum all these squares, and for your error not to depend on the number of data points you have, you take the mean, and that's your mean squared error. A very common metric used in machine learning. So to have the least bad model, you need to have the least mean squared error. Okay. So the equation of this line is just a simple line depending on the angle psi of the canon and the range r. So you have these measures, but what you want to compute is these two parameters here, the intercept and the slope. That's your two betas. So how do you compute them, these parameters of your model? So there is a general approach in machine learning which consists in using the derivative. So here you have your error function, actually it's called your loss function, and you want to find the minimum. What is the parameter beta psi, which will give you the minimum error. So you know that the derivative gives you the direction of your curve, and the gradient will indicate the increasing values. And by taking the negative gradient, you can go towards the minimum. So you just do that iteratively. So you can see here that the curve, you start from any random point, and you just follow the direction of minimum error to arrive at the global minimum. And then that's it. You have your model is trained. You have fitted your model. It means you have found the two parameters. And this method of least square error was actually already used at the end of the 18th century. That's why we set this problem at that time. It was used by Legendre and Gauss, who was just 18. And actually Legendre was a professor in ballistics. So it's also fit in this problem. So that's why I chose this theme. So now your final mean square error is this number. So that's the performance of your model on the dataset you have, on the training dataset. So in case you have two parameters, for example, for the parabola, the error function, the loss function will have this kind of shape, and it will be exactly the same principle. You start at a random point, and you just follow the opposite of the gradient to go down. So it's a gradient descent. Okay, so again, so we have these three models. So this one is only two parameters. We know the mean square error. The parabola with three parameters, one more parameter for the psi squared angle, and a polynomial of degree 5. So the question again is which one to choose. So if you look at the mean square error of each model, you can see that it's this one which is closest to the dataset. But is it enough to decide which one is the best model? Obviously, you feel it's a strange model to use. What you really want to know is how this model will perform on new data, on unseen data. So a way to do that is one way, if you have access to a new data set, you just use the model you just fitted and you apply it to the new data. So you take the angle psi, you put it in your model, and you predict your range. And that gives you a vector y. And you just compare this vector y with the measurements, the true measurements you had. By comparing the two, your prediction with what was measured in this new data set, you can have, again, a performance score, a test score, again with a mean square error, for example. So the error, the sum of square difference between these two measures, and that will help you understand how good is your model for new data. So in this case, you can see that for this new data set here, this model, the polynomial of degree 5, the error is massive. So it didn't generalize well at all. The linear fit is, the error is worse, but it's relatively reasonable. Whereas this parabola is almost the same error, even a bit lower, maybe due to noise, but it's almost the same performance. So it's very important to assess the generalizability of your predictions. And here you can see a question is also how variable is your model. If you have a new training, if you have a new data set and you fit again your model, is it going to change all the time or is it going to stay constant? And this is a very important question. It's a fundamental concept actually in machine learning called the bias variance trade-off. So if we look at data points, let's say 40-degree angle, we want to know every time we fit a different model, is the prediction going to change a lot or not? So knowing the ground truth is around 75 meters for this angle here. For each model here, I simulated 1,000 data sets and look at how the prediction change. And you can see that for the straight line, actually, so on average, there was a systematic error compared to the ground truth, but the variability was not that big. In contrast, so one with degree 5 had a very high variability, although on average, it has almost the ground truth. And the parabola was in the right in the middle. So you had reduced variance, but on average was also very close to the ground truth. And that's exactly the bias variance trade-off. So the total error is the sum of the variance and the bias, and it's a trade-off. So models with relatively low variance has a high bias. It means even with an infinite number of data points, it will be far from the true function. In contrast, with infinite data points, this highly variable model will fit perfectly the true function. But when you have a limited number of data points, it will vary a lot. And what you really want to do is to be in between. So to have a low bias, low systematic error, but also a low variance. And that's all the goal of machine learning practitioners, to choose the right model with this kind of optimum trade-off. And you can see that the variance is directly linked to the model complexity. So the more parameters you have, the more closely is going to fit your training data, but the worse is going to be on unseen data, on test data. And when you increase complexity, you also reduce the interpretability of your model. It's harder to interpret. So it's really, better to have a low complexity model, which also is not much variable. So this bias variance trade-off is often represented as this kind of target, since that's from the Elements of Statistical Learning book by Hastie. But typically, either you have a high variance with a low bias, or you have a high bias with low variance. If you have high variance and high bias, there may be a problem with your model. I mean, that's for sure. You really need to do something else. And if you have low bias and low variance, you may also double check your results to check you indeed have a very good targeted solution. So to make a very simplistic analogy, maybe for humans, it's if you consider someone having having opinions on a topic which change every day depending on which person she or he met, we can say it has a high variance. But in contrast, if you have someone who is very conservative in his opinion on a given topic, she or he will have high bias and low variance if they never change the opinions. So in between will be to consider new data, to change or representation of the topic, to be able to have a better, more accurate representation. Okay, so time to practice. So let's go on the Jupyter Notebook to be able to analyze the data. So the first thing you will have to do, if you didn't do it already, is to download the data with the following commands. But it's much better if you open a new notebook for that, because the time it's downloading, you won't be able to execute the next cells. So if you could open a new notebook, that would be much easier. You open the new notebook, you run these commands, and you keep a notebook to follow along the commands we are going to run now. Okay, so I'm not going to download them because obviously I have them. So we'll start with a simple regression model. So the range of the Cannon angle we're going to investigate are between 20 and 60 degrees. And we are going to get simulated data already generated. So if you use a GitHub repository, you can find the data sets here. So we are just going to read the CSV file with pandas. So you have other cells I'm not showing here, but which is on the notebook to import pandas as PD. And we are going to read all our data in this one and take a light version just for plotting. So this command, this function is actually from the Python file also in the GitHub repo, which is simply to extract interspread data, just a small subset for plotting. Okay. So we are going to generate a single data set of 50 observations. So the data generated includes 100,000 samples. The idea is just to take one. So we'll initialize a random seed to be able to reproduce our experiment. If you want, you can change it to see how your results will differ from what I'm showing. That could be interesting. And so we're going to extract one dataset of 50 samples, 50 observations with this range of angle. So let's explore our dataset. So I need to run the commands, otherwise it's not going to work. Okay. So yeah, we're only interested in looking at a range of angle, and our datasets look like this. So we're going to ignore these true values, and we are only interested in this experimental angle measured on experimental range. So we're going to plot the datasets to have a better idea of what we have here. So that's our 50 data points. So here on the x-axis you see the angle, on the y-axis the range. So the idea is to find how to find the best model which according to our data. So for this purpose, we are going to split our data into a training set to fit a model, and then a test set to see which one is best. So we'll compare 3 models, the same ones as we saw in the slides. So standard linear model with 2 parameters, intercept and slope. The parabola, it's a polynomial of degree 2, sorry, with 3 parameters, intercept, slope, and this beta coefficient for the psi squared term, on a polynomial with of degree 5. So it has 6 features, and so 5 features, and so 6 parameters because of its intercept. So scikit-learn, sklearn has lots of very useful functions to facilitate your job. So instead of writing lots of commands, you have lots of utility functions. So this one, train, test, split, is once you give a dataset, here you have some documentation if you want to look at the detail, you will be able to split them into training and testing sets. So just to explain better, so our feature matrix X has only 1 column because we only have 1 feature, but if we add several features, we'll have all of them here. But in this case, we have only 1 feature, so that's our matrix X of features, and our matrix on our outcome is a single vector with all the values. In this case, that's the range. So from this set of features, we want to predict the range. And the train test split, simply take as inputs your X matrix and Y vector, and you just have to give the size you want for your test datasets. So in this case, it's 40%. So the size of your testing dataset will be 40%. And it's going to take that randomly. So you need to give a seed. I mean, if you want to reproduce your result, you can give a seed. So since we have 50 samples, and if we take 40%, that will be 20. We have 20 samples in our test side, and the rest 30 in our training. So we can check that by looking at the length of the X train and the X test generated. Yeah, it will be 30 for training and 20 for testing. And it will also generate the labels for training and the labels for testing. So even if it's a continuous measure, it's called a label. Okay. Yeah, let's have a look at X-train. So you can see it's all my experimental angle, but there are only 30 of them instead of 50. So let's train our model. So in this case, from all the linear models of scikit-learn, you can see they have many different ones. We'll import the linear regression one. And to be able to estimate the performance, we need a different scoring function. In this case, we'll use the mean square error and the R2. So it's the traditional correlation coefficient squared. Okay. So every time in sklearn, there is the same approach. And once you know how to use this approach, so seeing it only once, for example, with a linear regression, will be really helpful because you can apply almost exactly the same workflow to a different estimator, to a different model. So the way you do it is that you instantiate a model which is actually an object. So every model is an object. So I guess most of you are familiar with object-oriented programming, but once you instantiate this model, so here I call it LM, you will have function and attributes. So methods and attributes. So let's see right now what does it entail. So in Python, you can access these methods and attributes just by putting a point following objects. And here I can see I can fit, I can get the parameters of the model. The parameters actually, it's not the parameters, the betas, but it's more like the hyperparameters normally. I can check. Yes, so that's really, it's more like hyperparameters as we are going to see. What else? I can fit and predict. And that will be the main function we are going to use. So here actually we'll fit, so or train observations to labels. And actually we don't need to have the output saved into new variables, because internally when you call that, it's going to change the internal objects in this LM object. So the internal state, I mean. So now you can see there are new things inside this instance, including the coefficients. And that's actually the coefficient of your model. And here you just have one for the slope, and the intercept, actually it's in the intercept attribute. And what's interesting in scikit-learn is to differentiate what has been fitted. There is an underscore at the end of the attributes. So just to recap, I had I instantiated an instance from an object, from an estimator. Then it was empty. Then I fitted from this instance, and it changed the internal state. And now I have the different coefficients as well as the intercepts of this model. So I can actually print them, and you can see the intercepts and coefficients. So that's the two parameters of my model. Okay, so now we want to use predictions to compute the performance of our model on the train data and also on the test data. So just to show you how you use a predict function, you just give them, you can give a list of several features. So here, if I had 2 features on my feature matrix, to do prediction, I will need a data with two features as well. And here it's just a list of prediction. But in this case, I need only 1 feature. So I ask, can you predict me the outcome for this observation, that observation, and that one? So in this case, it will just give me 3 predictions for each of these different sets of features. And so the training score can provide an idea of the performance of the model. So it's very simple. Again, we just call the predict method of this LM object first on our training data, because we first want to know how well the model does on the data we just trained. So it should be kind of best possible outcome for the test data. You can very rarely do better than what you do on the training data. It will be like kind of an upper bound of performance if you want. So we predict the outcome from our training data, and then to obtain the performance, we use the R2 score between the true values, so that's the Y data in your training, and what we predicted. So if you remember, we need to compare the two to obtain the performance inside the training data. And we'll also compute the mean square error. So in this case, we see that the R2 is average, and we have the mean square error. What we really want to do is compare that with the test data. Yes, and your object actually have a score function, which will give you the R2 by default. So you can also use that to get the R2. But that's the same thing. So we'll save them. We'll save all those scores to have a plot at the end to be able to compare the models. And in this case, since for the mean square error, the lower is better, not to have plots going in all directions, I will take the negative mean square error. So that's the greater the better, like R2. It will be simpler to compare all the different metrics, performance metrics. Okay, so the most usually the most useful and what you really want to know is how good is your model on unseen data. So there are many different scores. Here I'm just looking at the mean square error and the R2, but you can see here all the different scoring function you have. So let's do it. So in this time, we fitted a model. If you remember, we fitted a model on the training data, and now we are just going to use it to predict this new data. And we are going to compare our prediction with the true values, which are the Y for the test dataset. So normally the R2 should be lower and the mean square error higher, because it should be worse on unseen data. And indeed, it's quite worse. We again save our results for the future plots. And now let's do exactly the same thing, but for the polynomial of degree 2. So the way it works for polynomial models is you just need to create your features, so different powers of your features, and then add it to a standard linear regression model. So you need 2 steps. First, we need to create the polynomial features here. I will call it polytransformer. Again, it's an object with methods and attributes. And I will call another linear regression model. I'm just going to call it differently to differentiate it from the previous model. So don't forget to run everything. Okay. So again, that's the same thing I just said. First, you transform your features, and then you fit the linear regression on the transform feature. So here we'll transform our features. Actually, we can look at what X-train was before and what it is now. So you can see that first you had only 1 features, and now for a polynomial of degree 3, you have 3 for each degree. Degree 0, so constant. Degree 1 is the same as the original feature, and degree 2, so your features power 2. And we're going to fit. So this time we fit our transform features. And we can look at our coefficients. So now, since we have 3 features, we have 3 coefficients. And 0 is for the constant term. We have an intercept. Here. We have the intercept. So there is the degree 0 term is not used. Let's compute the training scores as before. We just predict what our model will do on the training data and compare with the ground truth. Okay, so we have a quite high R2 in this case, and a low mean square error. And we'll save the results again with the negative of the mean square error. And now always the most interesting, how well it does on unseen data. So it's very important to remember you again have to transform your test data to have 3 features. So in this case, you may wonder why we called fit transform. So there are often 3 different methods for different purposes. There is fit, which is going to kind of compute the parameters needed to do the transform. And then you do the transform. But you can do both at once by doing fit transform. And that's what we do here, 2 steps in one. So we're going to transform our features and then use a model which has been fitted on the training data to predict unseen data. And we compare that to the ground truth. So this time the ground truth is while test, and it should be worse. So, but in this case, very surprisingly, it's the same. So that's the best case scenario. When you fit your model on training data, on unseen data, at best, in the best case, it's just going to do as good as what you do on your training. And actually, that's the case here. Again, we're going to save the results to plot them later. And last thing, we're going to do the same thing, but I will introduce you to something extremely useful in scikit-learn, which is a pipeline object. A pipeline will allow to connect your different steps together to avoid to have them to do it again at training, again at testing, etc., etc. And it's very common to use because often you have pre-processing steps. You don't want to have to repeat every time you reuse your estimator. Okay, so you already know what the pipeline is, because it's exactly the same as the degree 2 estimator. And what's very convenient is once you have built your pipeline object, you can use the same method fit predict, except it's going to do all the pre-processing steps. In this case, it will do the transformation into features at different powers, and then call the fit method of your estimator, which is a linear model. It will do all for you in one call. So you just call pipeline with a list of steps. You give them a name, and then you put the objects of the step to implement. So in this case, we call it polytransformer, and we'll do the polynomial features transformation with a degree 5. And then we'll use our linear regression model. So it's just a list of tuple with the name you want and the actual objects. And once you have created this pipeline, you just can consider it as a normal estimator, as if it was your linear regression, except it's going to implement all the steps you put in the pipeline. So we'll just fit our training data, model to the training data. And now we can look at our coefficients. So this time there are 3, 4, 5, 6. Again, 0 here because there is an intercept. So this feature to the power 0 is not used. We're going to have the get the performance on the training dataset by comparing, getting the prediction for the training and compare it with the ground truth. Okay, so it's quite better R squared than the one before, but it's on the training data, remember. And now we're going to apply it to the test data. So what's great with the pipeline here, you can see we don't need to do any transformation, because here, this one is a pipeline, and when you call predict, it's going to call automatically the transformation on this one, and then call the predict method of our linear model. So that's what's super convenient with the pipelines. So we'll have a prediction, and we'll compare it with the ground truth for the test. So as we know, the degree 5 polynomial is highly variable. On unseen data, the performance should be quite lower than the training. And in this case, well, it's quite lower, but not that much. So it did relatively well. So that's it. We can plot all our results. So I'm just using turning the list of dictionaries into a data frame and plot the results. Okay, so here we are. So here you can see the training score in blue and the testing score in orange, and it's always worse. I mean, that's to be expected. And what's quite impressive is that for the parabola, for the degree 2 polynomial, it did almost as well on both. And same for the mean square error. So remember, I took the negative, so higher is better. And you can see, again, it's better on the training than on the testing. And for the parabola, it's even better on testing, which is mostly due to noise in the dataset. So that's it. You saw the principal elements in sklearn, the main, let's say, functions. So using the fit and predict methods, and also how to score your model. And you also saw the pipeline object, which is extremely useful for including proposing steps, including transformations, for example. So now we'll go back to the slides to understand better how to estimate the generalization of a model. So the question now is how to assess the generalizability of our predictions. So as we said earlier, a hallmark of science is generalization. We want to derive findings that also apply to other experiments. So as the philosopher of science Karl Popper said, non-reproducible single occurrences are of no significance to science. Although I'm not sure what was his thoughts on the Big Bang. But in any case, when we apply that to our field, we want to derive neuroimaging findings that apply to other population samples. So when we study a sample or findings, when we take all the samples from the same population should apply as well. So it's very important to be able to assess how generalizable is our methods or findings. So in the case of machine learning, the workflow is typically to pre-process the data and then to split our data into training and testing to evaluate what is the performance of our estimator, of our model on unseen data. So should we select a model by testing several models on the training datasets and then applying on the testing datasets? Actually, we cannot do that because if you test many models, just by chance, one will perform well on the test sets, and it will not mean much because it can really be due to chance. So the way you do it is really you do your model selection only on the training set. The test set should be completely untouched, and that's actually how different models are evaluated. When you look at Kaggle, which is a website for competition in machine learning, they always keep a test dataset on their servers, and the best model will be evaluated without having ever seen the test dataset, obviously. And so participants have all the training set, but they don't see the test datasets. That's similarly for one of the dream challenges and trying to detect breast cancer on mammograms. There was a big $1 million prize, and the test dataset was obviously kept while all the different teams worked on the training dataset to try to improve the models. And in the biomedical imaging field, we have this MICAI conference, which has been at the forefront of this kind of machine learning challenges. I think one of the first challenge of the kind was by MICAI in the 90s for brain registration. And you have many challenges every year where you have to train your model and then the best models are evaluated on the test dataset, which is on the server. So obviously it's not a perfect system. For example, just changing a few samples in the test dataset can change the outcome. The scoring matrix chosen can also influence the results, but I mean, there's still a good system to evaluate methods, machine learning models. So you need to do the model selection really only within the training set. So how do you do it? You could split the training set into another training set and testing set we could also call validation. So we'll use the term validation and testing set interchangeably, but sometimes it's called validation set when it's internal. And we can do that, but that's not the best way. The best way is to use what's called cross-validation. So the approach is to split your training set into equal parts called folds. In this case, it's 5-fold cross-validation because we split it in 5 parts. One of these parts will be the test data set, and all the rest is training. You just repeat that again and again to have 5 scores. So once you have these 5 scores, you can evaluate the generalizability of your model, because you will get the mean score together with the confidence interval of this score. And this will be done every time on unseen data, because you only train on the trained parts and you test it on unseen data. So let's practice this. So now we are back to our Jupyter notebook and we'll use cross-validation. So in this case, we'll import kfold. How does kfold work? You just give the number of splits you want, so number of folds you want, your data arrays, and you say if you want your data to be shuffled or not. Sometimes you have the data in order, in some order, I don't know, by age or whatever. And it's very important to shuffle the data to make sure in each fold they are independent. And in case you use shuffling, then you can use seed to make sure you will obtain the same folds if you want to reproduce your results. Okay. So just for you to understand better, we'll just use a toy dataset. I'm just taking 10 random ints between 0 and 1000, and we'll see, so that's it, and we'll see what kfold will do on this one. So I will do 5 splits on these 10 observations, and here you can see what it returns. So the kfold will return indices for your training and your testing. So it's a 5-fold kfold cross-validation. On your indices, you can see the first 2 components of your data will be used for testing in the first fold, and then the rest for training. Then it will take the 2 successive elements for testing and the rest for training, etc. So in turn, it selects testing folds, and every time all the rest is for training. You can see there is no overlap in the testing indices and no overlap between the training and the testing. Okay. And now if I use shuffle, you can see that it will be random for the testing indices and training indices. So there is no order as it was here, in case your original data is not is ordered. You will need to remove this ordering for all the folds to be independent. So in our case, so here, just to confirm the size, if we use 5 split, let me see. Yes, we'll use a 5-fold cross-validation, and we'll compare different models. So we compare as before our linear regression together with the 2 pipeline with the transformation on the polynomial. Okay. So I will just, so what I'm doing here is cross-validation of the different models. So I'm calling here the kfold 10 split, so it's 10-fold cross-validation, and for each one, that's the index of the fold, and that's the training and testing indices. For each one, I will call my model, it's a dictionary here, you can see. So if I take the keys of the dictionary, that's the name of the model, and here I will call my model and call the fit function. And I'm calling the fit function on what? On the training data with the indices given by the kfold generator. And every time I will fit the training to have a training performance score, I will predict the training to have this score on training and predict the testing fold to have the testing performance. And it will be done 5 times. So for each model, I will have the mean and the confidence interval of the prediction. So let's do it. Up. Okay. We'll plot the results. And here we are. So that's the results for each of the tenfold. And you can see that often the testing is worse than the training, except it's not always the case, but sometimes it's very bad. You can see you have a negative R2. Negative R2, it means the variance explained by your model is worse than the model, which is just the constant mean of your observation. Degree 2 is doing actually quite well on the testing set. Whereas for degree 5, yeah, it can be pretty bad on the testing. And that's for the mean. For the median, for the box plot, we can see the spread of our scores across the tenfolds. And you can see that for the linear model, it's very bad, as the R2 on the testing. It's always worse, as I was saying, for the degree 2 and degree 5. But degree 2, here we can see a zoom on the same plots. Here, for the degree 2 is slightly better, and there is less variance. You can see again, the training is better for the degree 5, but for the testing, it's worse. But that's really the testing score, which is important. So again, we have confirmation that the parabola is better. Now, we know that sklearn has lots of these utility functions, and many are there to automate many of the operations. So instead of having this loop when we create the folds manually and compute the training and testing score, we have this cross-val score function, which do everything for us. So how does it work? You just have to get some metrics. The only additional step you have is to create a scorer. So you cannot give just the name of the metric or the function to compute the score. You need to call this make scorer function with a scoring function, and it will create a scorer that will pass to cross-val score. So it may not be super clear, so we are going to do it now. See what arguments it requires. We can see that you just give your estimator, the X, the Y, your scorers, and that's it. And it will do everything for you. For the CV, by default, I think it's 5 or 10, but you can also give it your cross-validation object, and it will do everything automatically. So let's see how it works. Here I have, again, all my models. And here I just have to loop on my models and call cross-val score with a model, my training data, my k-fold objects, and the name of the scorer I want. And jobs equal -1, it means I'm using all the CPUs to do this. And it's very useful because for cross-validation, you can parallelize everything because the computation of the folds are independent. So that's super useful. And then I put all the results in a data frame. Let's do it. Okay, let's plot the results. And here, you see how much easier it is. I just call cross-val score. I put the results in the data frame, and I just have to do the box plot. You have the confirmation that for testing, here the mean square error is much better than LM for the degree 2, but it's also it has less variance than the degree 5. And if you want to do even less code, you can use cross-validate, which can use not only several metrics, but it will also return the train and test score. The previous one only returned the test score. So it's the same pipeline. I call cross-validate with a list of scoring function. And this time, oops, I can have the same kind of plot as before, where I have the training and testing, but instead of doing a manual loop, it's just a few lines of code. Okay, we'll go back to the presentation. to go to our next chapter. So this is the last chapter before going into real neuroimaging data. So the question is how to prevent overfitting. So one way to do it with linear regression is with regularization on other models, but we're going to see it for linear models. So if you remember this plot of trade-off between bias and variance, you can see the variance is characterized by a high variability in the models depending on training data. And what you can do, because this variance is directly related to the model complexity, which can be caused by the number of parameters of your model, you can reduce the number of parameters. And you can do that with feature selection. It means you remove some of your features before training your model. Another way is to do regularization. So in this case, we can force the model's parameters to be 0 or to be small. Because if they are big, your model is going to vary a lot according to the data. So by having them small, you can regularize them, you can make it being more stable. So if you remember this loss function, in case you have two beta parameters, 2 parameters for your model, if you look at the projection here, we can see this projection on this plane here. So the more away you are from the minimum, the higher the value of the projected loss function. So here we can see the different values. So what you do with regularization in this case is that even though your true minimum is here, you can constrain your parameters to be only in this area, for them to be small or 0. So the way you do it is that in your loss function, in addition to the usual term, you just add a penalty term so that the higher the weight, the higher will be your loss function. So if you want to reduce your loss function, you will need to reduce these parameters. And here is you just have one parameter, one hyperparameter to set it, and the higher this penalty parameter is, the more reduced or the more zeroed elements you will have. So you have two kinds of terms, either squared or absolute value. So with absolute value, it's the lasso terms. In this case, you can see that this constraint will look like this. And when your loss function meets the first allowed value, it will tend to be very small or 0, more likely 0 with lasso. But with ridge regression, this penalty term is squared, so it will have this shape. In this case, it will just reduce the betas. Okay, so with lasso, because they meet, this loss function is more likely to meet the intersection with x or y axis, they're more likely to be 0. So it's a great way to reduce the complexity of your model and so to bring it closer to this optimum position. So lambda is called an hyperparameter and is not fitted. You can consider that for a given lambda, you have a given model, and different lambdas, different models. So you need another procedure to find the best value. So let's see a way to do it. So one way to do it, for example, you could try to repeat cross-validation for each possible lambda and then compare your models. The problem with this approach is the same as before, because you will compare them. If you compare many different values, you will just obtain a much too optimistic performance score, because it will be the best one after many trials. So one solution to that is to use nested cross-validation. Nested, it means you're going to do cross-validation within your cross-validation. So here you try your 3 different parameters, you get the best one, and you test it. And you do that again and again, and this way you will have 5 different evaluations of your parameters, first, every time you can not only see which parameter is chosen, is it always the same one, and what will be the score on unseen data. So you have an estimation of the performance of your model. You can also check if it's stable, because if you have a different answer of the best model in each of these nested cross-validation folds, you will know it's unstable. So we'll have a look at an application in neuroimaging data. So here we are. Okay, so in this example, we'll try both feature selection that you mentioned and penalize regression with lasso. So I already mentioned what is feature selection useful for, is to help prevent overfitting and obtain a simpler model. So also called parsimonious, because you have a simple model, it's much easier to interpret, and if you have fewer features, the calculation are faster too. So we'll use Notebook, which was actually, it's an example presented by Jack Vogel at Brainhack School. So the machine learning approach is quite different, but the nylon part is quite similar, very similar. So first we get the data. So normally you have already fetched them at the beginning of the session, as I was mentioning. And from the GitHub repo you got, normally this notebook is, the dataset folder is in the same folder as your Jupyter notebook. So normally this path, you don't have to do anything. Sorry, this one is for fetching the data. Voila, here, the offline directory is inside what you downloaded from GitHub. So we'll just use this one. Okay, and we'll also use the phenotype file. So this actually, this file is to have the connectivity matrices. I'm going to explain in a bit what is it. But first, I'm just going to get this data. So the data is in two parts. We are going to try to predict age from brain connectivity. So this X file is actually features of connectivity we're going to see in the nylon section, which characterize the connectivity in the brain with functional MRI. And what we are going to predict is age, and age is within this phenotype file. So for each subject, we have different values, and we try to predict the age value. Okay, so we are going to actually look at these connectivity matrices here. So here, what we can see is the number of subjects we have, so around 150, and the number of features. So the number of features you can see is massive. Why? Because the connectivity matrix is a matrix which is around 64 by 64, and each entry of this matrix will be used as a feature. That's why we have so many features. But one question I wanted to ask you, when you look at this data, do you notice something? So I just looked at this data 2 days ago, so it's really new for me as well. Actually, the first thing I notice is here, this region, which looks kind of dirty. And immediately, because it's so important to look at the data, I just plot it slightly differently. So just without interpolation, you can see indeed it looks quite dirty. And when you look closely, it seems that in between row 36 and 63, you have these dirty rows. So then I decided to have a bit look into it for this in the phenotype. What are these subjects in corresponding to these indices? And what I saw is that all the age group is for the very young kids. And it's not a surprise because, as you know, the very young kids, it's very hard to have them still in the scanner, and motion can really affect the signal. So it's I mean, it's just a demonstration why it's so important to always look at your data to understand what's going on. So I'm not going to remove this data yet. I will do an example with, but it will be very interesting to see what will be the results without this data. So here I decided to do just a quick investigation of the standard deviation of these features according to the subjects. And we can see here between subject number 36 to subject number 63, all these high standard deviation of the features correspond to all the subjects having an age less than 5. So in red is all the subjects with age less than 5, which I overlaid on the plot of the standard deviation of the features. And you can see that indeed there seems to be an issue with children less than 5. So as I say, I just got this data 2 days ago. I mean, I just looked at it 2 days ago, and I didn't have much time to do much than that, but it's just to show you that the quality analysis of your data is super important. Okay. So now, just looking at the number of subjects per age group, we can see that actually we have young kids until 12, and then adults. So we have this gap of age. Actually, we can plot the histogram, the distribution of age. Here's at the age, and here is the number. You have all these kids and the adults. So the idea is to predict age doing a regression task, but I'm not comfortable with doing a regression task with this gap, because what can happen is that you can have 2 clusters and just try to fit a line, and it will not be really a regression, but it will be driven by these 2 clusters, leveraging the regression coefficients. So instead, we are going to remove the adults and just try to do the regression within this group. So if we cut the age at 13, we can see we still have 122 subjects. So we'll do that. Okay. So here I take all the subjects less than 15. So our Y to predict will be the age. And we select only where people are less than 13. So it's a Boolean mask here. And we chose only the one less than 13. And we do the same mask to select our features. So we take all the features, like 2,000 of them, but we select only the subjects who are less than 13. Okay. So number of features is 2016, and number of subjects is 122. So with that number of features, you can really expect some serious overfitting. So we'll just split our data set to have round numbers, let's say 100 in train and 22 in test, and we'll shuffle. And I think it's very important because this data actually is ordered somehow by age, I think. And what's important also is to do stratification. So stratification is when you create the folds to have the same proportion of the class you want to predict in each fold. So it's typically used for classification, almost never, I mean, very rarely for regression. But in this case, in the data frame we looked at, there was this age group categories. So we'll use it to do this stratification to have in the traced, train, and test sets the same proportion of age groups. Okay, so we already know the train test split, but here you can indicate as many arrays as you want. So instead of the X and Y here, I will use the age class. And here it's just the indices going from 0 to the number of subjects to see how they are split. What's very important here is the stratify argument, age class. So it will have the same proportion of different age categories in train and test. And we ask here to have 122 subjects in the test site. So here you can either give a fraction like last time, like 0.4, or you can give an absolute number. It will automatically understand because the fraction is always less than 1. Okay. And here we just check that the stratification worked. And indeed, if we plot this distribution of age in train and test, it's the same. So we'll just look at the classic linear model. So we should have less performance in testing, obviously. So we just do things as before. Oops. So manually, remember, we just iterate over the fold. So we do a stratified k fold with a 10 fold, while stratified because it's stratified by age again. So we did this stratification for train and test. We put the test, we will never use it until the very end, and we do everything within the train. So the stratified k fold will be in the train. So as I showed in the presentation, in the training set, we split it into 10 folds. And in each fold, we are going to predict to have the performance on a train set and also on the test fold. And we save the results for R2 on mean square error. So we have train test for R2 and train test for mean square error. Okay. Yes, that it was. You don't have to worry about that. I had to create a new class which is derived from the stratified k fold, because normally you cannot use stratification in a regression because it's always based on your label y. So if your label y do not contain categories, you cannot do it. So I had to create a new class. So you don't have to worry about that. And here we use cross-validate because instead of iterating, it's so much easier to use the utility function scalar and provide. So use cross-validate with our linear model on X train and Y train. We have a special cross-validation object. On the scoring function, we want R2 on negative mean square. Why negative? Again, so that higher is better. It's just a convenience thing. Okay, that's quite fast. We can already plot the results. And again, you can see here how limited is the R squared in the testing set. And same for mean square error. You cannot even see it on training because in training, with that many features, you have a perfect fit. You can see the R2 is 1 and mean square 0 is 0, but it's so close to 0, it's not even plotted. Here, if you look at the box plot, indeed, you have 1 in R2, 0 in mean square error. But obviously, it's a perfect illustration of overfitting. When you try in the testing, the performance is much worse. So now we are going to add a feature selection process. And the thing we are going to do is we are going to look at two different types of feature selection, either with F score or a mutual info scores. So what does it do is it's going to look at the correlation with your feature on the target, in this case age, and it's going only to keep the n best. So what is n? So what is here the k best? So what is k? It's for you to choose. So you call this select k best object with, you have to choose yourself what is the criteria. So we're going to select the k best going to F score, and here according to mutual info score. So you need to create a pipeline. I mean, we'll do it for convenience. First calling this feature selection. So it's going only to keep the 10 best, and then it's going to do linear regression with this k best. Again, this pipeline is super useful in this case. So here we call the special stratified k-fold. You don't have to do it. You can just call a normal k-fold. It's fine as well. But what's very important is to shuffle because the data is ordered. So it's a critical step. We create a dictionary to keep our scores in each fold for each model. And so for each model in a loop, we just have 2 models. We will call cross-validate with a list of scoring. and save the results. Okay, and now we can, this one, I just rename the model, otherwise in the plots it's terrible, and create a data frame, and then we can plot it. Here as a plot. So in this case, you can see in the training is no longer perfect score because we only have 10 features, but in the testing, it's not that great. It's not much better. So we're going to look at another approach, but at least you saw how you can do feature selection. We're looking at the range of a hyperparameter. A hyperparameter, it means a parameter which is not part of your model. It's not the model parameters. It's a parameter which is above that. It's not within your model. It's just to even influence the model itself. So what's very convenient again is the validation curve. The validation curve is going to try many different parameters. For example, hyperparameters, many different k in this case. K is not a parameter of your model. It is to change the way the model is going to behave. And we are going to plot the score for each value of this k. So it's going to do a loop for all this k range. And the validation curve methods is going to do cross-validation. So in this case, you can give which score you want. We're going to do with R2, also with the mean square error. And for each of these k value is going to do cross-validation, and we'll be able to compare the different performance. So it may take just a bit of time. And we save the results. I created a dedicated function to transform the output of validation curve to a data frame, which is much easier to plot. So this one is a function I wrote myself. You can see in the notebook. Yes, you can see I'm doing everything twice. Once for R2, once for mean square error, using either the pipeline with the F score as feature selection or the mutual information as feature selection. Something important. If you have just a single model, the parameter name will just be K, for example. If I just wanted to do this validation curve directly with the feature selection, I will use K. But because if it's a pipeline, because it is a pipeline, you need to put the name of your model, 2 underscore, and the name of the parameter. I'm going to plot this. I need to show the code. I'm not going to show any of the code for plotting because it's not really useful. So here you can see for the parameter k what is the value of the score for R2 and mean square error, and you can see that as you tend to have many parameters, you will overfit, so that's the training in blue, but the testing performance will be very poor. And you can see that actually the best performance in this case is for up to 25 parameters. But even this best performance is not that great. It's around 0.25 for R squared. So it's not, I mean, this model in this situation doesn't work well, but at least you can really see how to do it when you need to do cross-validation of an hyperparameter. So in this case, we are going to look at the relationship between the predicted and real value with cross-val predicts. I'm not sure if I'm missing something. Let me see. Oh no, it's fine. yes. No, there is something missing. Sorry, I will just run this cell. Up. So here in this cell, we do the same as before, but we use the convenient function cross-val predict, which does everything in one go. And then we're going to plot it. So now I can put back the presentation. Here we are. So what we did here, we use crawl-val predict, which is going to take the prediction in each test fall only and keep them. So you do your k-fall, you just have one test fall, so it saves the prediction. You have the prediction on the second test fall, is going to concatenate them for each of your fold. So that's a pretty useful function, because now we have our prediction from each of the test falls, or unseen data, concatenated, and we can plot our prediction as a function of the true age. And here we can see the R-squared of 0.30. Okay. And what we can see, there seems to be a power law. So we could take the log of the age to have a more linear fit. I will do that quickly. That's not the most interesting part, but just for you to know you can do it. So there is a special object called transform target regressor, and you just have to call it with your estimator here. So we use a pipeline as estimator, and we just use it in our cross-val predict framework. So if we use it instead, you can see indeed it's more linear and you have a slightly higher R-squared. Okay, so now the most interesting part is the penalized regression. So we use lasso in this case. So we just have to call the model. Again, it's an object, and we use a random state, which will condition the way a lasso is, the parameters are computed. And in this case, we will want to look at all kind of these lambda parameters, the penalized parameter, you remember from the slides. In this case, it's called alpha in scalar. So we want to find the best penalizing parameter, which gives us the best testing fold prediction. So we look at all this range and so many different alpha. Yeah, so in this case, it may take some time to run, but what we'll be able to do with this validation curve again is to look at the performance as alpha is changed. And remember, the bigger alpha is, the bigger penalty, the fewer number of parameters we have in our model. Okay. And that's it. So here you can see the different value of alpha. You can see that with a low value, which means low penalty, we have many parameters. We are overfitting with a very high performance trades in training, but low performance in testing. And we can see that the best parameters you are always interested in the testing performance. Here, the training performance is just to know if you're overfitting or not. And it seems to be around here. So around 0.05. So actually we'll take as a choice 0.05. It will be our best model, let's say, and we'll use cross-validation to know if how is this model doing. And in this case, you can see that it's pretty good, it's 0.46. But as we mentioned earlier, it's not so good to do cross-validation to compare different hyperparameters. What is best is to do nested cross-validation. And so we can implement that. We have a special, again, utility object, lasso CV, which will do cross-validation for us. So we can just call this lasso cross-validation object. And when we are going to do this scaffold, this cross-validation with a K fold, inside the fold, we are going to call the cross-validation of lasso. If you remember the slides, within each fold, we are going to do cross-validation inside, so that for each K iteration, we are going to have an estimation of the best alpha parameters. And what will be very interesting to see if the alpha is the same for each of the K split, or if it's different, and also what is the performance all the time. So instead of talking, I should have run it. Let's go back. And I will be able to plot the results. So here again, it's just for plotting. Here we are. So we see for each of the 10-fold, we can have an estimation of the R2 on mean square error. And in this case, you can see that the lasso model is doing relatively well. Every time it's for the best alpha. So let's check if the alpha is stable. And we can see it's relatively stable, but not completely. But we are going to take, so it's important now to remember that the higher alpha, the fewer parameters in a model, because there is more penalty. So we'll take one of them, for example, this one, which is close to the median, as our final model. So to analyze the final model, we'll finally be able to test it on the testing set we put aside. So that's the only time when you can fit on your whole training datasets to have your final evaluation on the test set you kept aside the whole time. So our final choice is this one. We fit our whole training data, and then we test it on this test set we kept from the beginning, using still R2 on mean square error as a performance estimate. And actually, we have a pretty good, a reasonably good R squared with the model. So you could see the whole pipeline on how to fit, as to select the best model with cross-validation, nested cross-validation with hyperparameter tuning. Hyperparameter tuning is a choice of the best hyperparameter. So that was a quite dense, but at least you could see the whole workflow. Now, what's very important in your imaging is to be able to interpret a model. It's not always the case. It's not always easy in machine learning, but for lasso, you can look at the coefficients. So remember, we can access the attributes of our object just with a coef. So in this case, we have 2016 coefficients. Means that the length, but many will be 0 thanks to this penalty term. And actually, we can see we have, if we count the number of non-zero, we have 33 parameters remaining out of the 2000. So it really be extremely helpful to be able to interpret more easily your model. So since each parameter is associated to a brain connection, we can do a brain plot, and that's the NiLearn part. So I'm just going to check how we are doing on time. Okay, so unfortunately we are doing very badly on time. It's my fault. So we have I used all the time. So I'm just going to summarize very quickly, finishing off the section. So if you go up to section 3, what I wanted to say about NiLearn, actually, it was just to show an example on how to use it on fMRI data, but it's really specialized to fMRI, on how the vocabulary, the terminology used by NiLearn is the same as sklearn. So you still have this object you call every time you want to do something. So here is to measure connectivity. You have this fit transform method to apply. So again, there are lots of great tutorials on NiLearn, so you can really reuse it easily. and you can go through the Jupyter Notebook. There is everything in it. And just to, yes, that was the last. This section on Nylon was on how to process fMRI data. It was how to turn your fMRI data into the shape sklearn is expecting. So the shape is the one we presented at the beginning of the presentation, which is an X matrix with all your observations as rows and all your features as columns. And the main exercise was to transform the connectivity matrix, which is 64 by 64, into a vector, because this vector will be all your features. And for each subject, you have to concatenate these features to build your feature matrix. And your Y label was just the age, so there was no difficulty in this case. So I'm going to conclude, going back to the presentation. And I had a brief section on classification, but for classification, what changed is your labels, which are categories. They are no longer continuous, but they are categories. And the scores in this case is the number of good categorization, so true positive, true negative, and how bad you did when you, instead of predicting the patient didn't have a disease, you had a false negative. And if you predicted he had the disease but he didn't, it's a false positive. And all the different scores are just a function of these ones. For example, you have the true positive rate, which is the number of true positive you detected compared to the total number of positive patients, and the false positive rate, which is number of false positive among all the negative. And so either you can use any of these metrics, but you have to know that most classification algorithms output a probability of having the disease or not. So, and you can choose what probability is a threshold to say yes, he has a disease, or no, he doesn't have it. You can choose p equals 0.5, p equals 0.95, depending on what is important to you. So I will just conclude for this classification part that what's very useful is to have this ROC curve to be able to look at every time you're going to choose a different probability, you're going to have a different false positive rate and true positive rate. And by going from 0 to 1 for this probability threshold, you'll be able to trace these curves. And the closer you are to the perfect classification, the better. So typically you measure the area under the curve, AUC, to have a performance of your classifier. There was a section on SVM, I'm going to skip that. But what you can do is look at this slide and do the Nylon HAX-B dataset tutorial with use SVM for classification. And so here, so today we saw classification, regression, mostly regression, which are associated to label data. We have the dataset with both features and the label we want to predict. That's called supervised learning. But when you don't have an outcome, a label outcome, this is called unsupervised learning, which includes dimensionality reduction, which is mostly for visualization. When you have tons of features, you can actually project them only in 2 dimensions to try to understand your data. You can see there are different groups. And you also have clustering as unsupervised learning. In this case, you really try to understand if there are subgroups within your data. And it can be applied to the brain by, for example, grouping together vertices which look similar according to the MRI measures, and to have different regions. And it's often used actually to parcellate the brain clustering. But you don't have any label, so you just have your X feature matrix. So that's it. Thanks a lot for following along. It was quite dense, and I didn't even have time to finish, but hopefully it was quite useful for you to have an overview of machine learning and how to use it with sklearn. You have the same terminology in sklearn and nylearn. So if you understand the main idea, the main framework, you can really do it yourself, especially considering all the great examples and documentation in both sklearn and nylearn. It's really easy. It is made easy for the user to really try different approaches. So I would really encourage you to do so, even if you are working with EEG, with MNE, which have the same kind of tutorial. So that's it. I would just like shamelessly to also present the Brainhack we're going to have in autumn in Geneva. Hopefully it will not be remote, but everyone is invited, and you can check the website. We often have cool projects. You can also propose any project you want, as long as it's related to the brain. It can be EEG, MRI, or even 3D printing. And don't hesitate to follow us on Twitter to be aware of the next Brainhack. So thanks a lot. So, and if you have any questions, yeah, absolutely don't hesitate. I'm here in the chat. Thanks a lot.
To switch roles, and I thought it was happening later. Sorry about that. Let's have Michael just join us on stage right away. And then we'll do that bit of Q&A. So Michael, you should have an invite. You're going to click yes, and then you'll be joining us on stage, and we can have an interactive, a bit more interactive version of the Q&A. I mean, the chat is interactive. It's just not the same.
Live and interactive.
Yeah, exactly. Yeah, I'm sorry, I couldn't think of any other jokes just on the fly, so that was the only one I had. And then Selim was like, "Remy, stop telling jokes and just do what you were supposed to do 5 minutes ago, which is actually just take over from my role." So sorry about that.
Sorry for my side as well.
No, that's fine. That's fine. It was clearly me just going like, "Oh, what's going on?"
You were first, I told you.
Yeah, I arrived here first, but I did not realize I was supposed to take over and be like OSSIG on the OSSIG account. Michael, you want to join us on stage? There should be something on your screen saying
timeout error. Oh.
Timeout error. So what's fun with computers is when they work, which happens rarely, apparently.
Yeah.
But we'll make it work eventually.
Obviously, we are trying and collaborating, and it's the
exactly
main.
There's a lot of course correction happening live on these things.
Yeah.
Trying again. Maybe I should. Wait, I'm going to try again, Michael, to re-invite you. Hopefully that will work. Let's try it. So you've had another invite. If you get another error, I know that some people said that the browser you use is a bit of an issue.
Yeah. Don't pour any more. Yeah.
I'll try. I'm trying to ingest most of the coffee I brew these days, but maybe I'm actually ingesting way too much of it. It's actually not exactly a good idea. So trying another one. Yeah. Yeah, Michael, maybe you want to try on another browser. I think we've had a couple of issues there. So yeah, definitely drinking way too much coffee to make sure this runs smoothly. And this morning I was on the wrap-up call of the Asia Pacific hub, and I was sort of giving a big sort of thank you to everyone who's helped us and like joined this event. And I think that I was in the peak of the caffeine there because I was a bit hyper. So
Wow.
eventually this will calm down. Hello, Matthew. Should I just try again? Oh, I guess he's busy. He's busy switching.
Yeah.
He must be busy switching browsers and re-logging in and so on. All right, let's see how this goes. Yeah, because without Michael, I don't think I'll be able to answer machine learning questions. Like I know a little bit, but clearly not enough to just. If you go into really technical stuff, I'll go like, I don't know.
I'm just a familiar person, but just familiar because I'm using the tools that are not implemented here. But
Okay.
all the answers are here, so yeah, he answered on the questions at the section, so I can read the answers as well.
Yeah, but I guess it's a bit better to actually just. I'm not sure everyone just went during the session onto the live stream, not the live stream, into the polls just to see the answers to the question.
Yeah, and it's also another opportunity to ask questions here as well. We can just direct them as Michael tries to log in. People, you can use the button of the ask question here as well, right?
Mm-hmm.
Imo is a big. Yeah, okay. We are trying, Rahul.
Nope. I'm trying to see whether he is. Okay, I'm here. So we have. Okay, we're trying different accounts, right?
Yeah.
Okay.
It also works.
Let's try this. Sorry for the last minute stress, Michael. This has been a bit just of a roller coaster. Any luck? Accepted and connecting. I like when I see that.
Okay.
Yay!
Yes, we made it eventually.
Yes.
Sorry about that. We didn't really had time to prepare everything and crash test everything.
Yeah, no worries at all.
So, yeah. Was it just a browser issue?
Yes, it was. I was using Firefox, but Chrome works fine.
Okay.
Okay. Cool. So shall we just jump right in, and maybe you want to sort of elaborate on the answers you gave to those previous questions, if we can maybe pull them out from the little box where we hit them. You have them, Selim?
Yeah, I have them. I can remind them if you want.
Or you maybe copy paste them into the chat, because I'm not sure everyone will be some of those.
That'd be great.
That would be kind of tricky. Let's try it.
Wait, I have them.
Okay. Okay. Thank you.
There.
One thing is about optimal thresholding.
Yes. Can anyone help?
Especially on units.
Yeah. So it seems quite specific as a problem, but I would say when you try to do deep learning on brain images, it can be very important to harmonize the signal, to have the signal around the same per subject. And often there is some pre-processing steps which are not ignored, but like people specialized in machine learning are not specialized in MRI processing, and they ignore this normalization procedure. And often intensity normalization can help a lot with these kind of issues. to avoid having a threshold, subject-specific thresholds, which can be due to the intensity of the image. So your net, your neural net is going to need a subject-specific thresholds because of this not harmonized intensity. Yeah. So I would recommend looking at the pre-processing and especially intensity normalization.
Oh, it's really a nice question because it would help me. I'm one of those people who ignores all the pre-processing and just runs the network.
Hard to be specialized in everything.
Yeah.
Apart from intensity normalization, yes, there is always other pre-processing steps you can add. But in my experience, that was the one making the biggest difference for deep learning analysis of brain scans.
Okay, I have this next question lined up, the one that was after that. Oh, sorry, Raul, I think I sort of jumped the queue there.
So you already did intensity normalization. So there are different packages to do it. And some are more efficient than others compared. I mean, there's some histogram intensity normalization. As if you have different MRI modalities, there are some algorithm taking all of them into account to improve the intensity normalization. There is a great R package for that. I could try to find again. But it can also depend which software you are using to do your intensity normalization.
Okay.
And yeah, regarding the other question
about harmonization of
okay,
data.
Still on the same. Yeah, so yeah, it seems. I mean, it's hard to know without looking at the model and the data what exactly happened to this 20% of subjects.
Yeah, you can. Feel free to always give the answer that they gave in a previous session on Docker and containers. Like the short answer is it depends, and that goes for so many questions that it's like
I try to postpone this answer.
don't just embrace it. Just go with it.
Yeah, I will send you the link to the best package I found for this intensity normalization because it can vary. The quality can vary a lot.
Yeah, we have a Mattermost channel where you can keep asking questions after that. We're a bit short on time, like right now, so I think we're gonna
extend a bit.
That's fine. That's fine. It's just that I don't think that question session is going to be super long. And there's a Jitsi room. You can go there to like have a one-on-one chat if you wanna do that. So next question was what kind of method similar to redirectionization are there for nonlinear models?
Yes, actually you can add penalty a penalty term also to any kind of loss function, even for nonlinear model. So you can use a very similar approach. But we show it for linear regression because it's the easiest to conceptualize. And that shows a linear model, even if it seems not very exotic, because as we mentioned at the beginning of the chat, is very similar to some statistical model you will use linear regression. But it's a completely fine machine learning model, and it's easier to interpret and to have a feel for it. But everything else applies. So if you go to the sklearn website, there is a great documentation, and they give you tons of list of models. But as long as you understand the overall framework of fitting, predicting, evaluating with cross-validation, you will be fine. So the aim of the talk was really to present the whole framework, the way to think about it, the way to implement it. And then it's very similar per model. And after you need to spend time to understand the different hyperparameters of each model to know what they correspond to. And for example, for SVM, I didn't have time to show it, but it's quite important to understand what the C penalty parameter is. So I explain it in the slide to know how it's going to affect your model. And the aim is really to avoid overfitting by looking at the both training and testing. So once you understand this whole concepts, then you will be fine for the other models. You just need to spend time in specific models you're interested in. Yeah.
And then the last question that was just asked right now that I'm going to post in the chat. Sorry, I'm just going like, sorry, Michael, this is like fast. This is like a rapid fire question session. So that one is a bit long, so I will let you just process it, and because you haven't seen it before, so you couldn't prepare your answer. So this one is really on the fly. I will let you. Oh yeah, that's the same question.
Yeah, so it's a big topic which I didn't say. So so you want to estimate the uncertainty of your model. That's why cross-validation is great. But then in our field, compared to in physics where you studied, I don't know, cannonball, is going to be the same everywhere. So this uncertainty is quite valid. But in MRI, we have a big issue is that, or EEG, the signal really depends a lot, for example, on the scanner, on the site, and it may not, what the uncertainty you found may not apply to other sites, and it's a massive issue. And there is all this domain adaptation research really ongoing to be able to adapt our algorithm to other sites. But I mean, it will be quite difficult to adapt without having any label data from the other side. Usually you have a label data from both sides, and then you can generalize because you can learn the mapping from one side to the other. But if you have only data with one side, yes, I mean, it's going to be very challenging. You should try to have at least some label data from side 2, even a few examples, to be able to at least learn this domain adaptation, this mapping.
Good. I think I'm gonna sort of make a decision that we're gonna have to move on, and further Q&A for this session will have to go into either the Mattermost chat, but you do not hesitate to fire up a Jitsi room or another video chat where people can just keep the discussion going. I think there's a lot of people who are interested in like getting answers and talking about this. So
yes,
yeah,
and I will answer a bit more the questions.
Okay, cool,
great,
fantastic. No, thank you very much for being here and for the video. The link to the Mattermost chat for the NiLearn and Skylearn. Can I let other people take care of that, because I'm a bit busy right here. Yeah. Thank you. Cool. So see you in the next session. We have Helena and Matthew from INCF, and we're going to have a very interesting discussion how the OHBM Open Science and INCF can better collaborate together. So stay tuned. You're going to be teleported there very quickly. We just need to set a few things up. See you very soon. I'm going to end that one now.
Yes, please. Ciao.
In this rapid global development, I anticipate that INCF will be at the forefront and will be driving the development of neuroinformatics during the next decade.
The new era of neuroscience is very much about data and data-driven approaches. And this is a challenge for the field because the next generation of neuroscientists absolutely need the skills to handle this data.
Neuroscience is not anymore a biology field only. It's a biology field for sure, but it's also...
In this rapid global development, I am...
Okay.
In this rapid global development, I anticipate that INCF will be at the forefront and will be driving the development of neuroinformatics during the next decade.
The new era of neuroscience is very much about data and data-driven approaches. And this is a challenge for the field because the next generation of neuroscientists absolutely need the skills to handle this data.
Neuroscience is not anymore a biology field only. It's a biology field for sure, but it's also a computational field. And we're moving from the wet lab to the web lab.
I find it really, really frustrating when I see great graduate students wasting time reinventing the wheel. They're doing work that's already been done. They just don't have access to it.
Before, neuroscience was very closed. You produced your data, you analyzed your data, you threw it away, you published your paper. We're now asking you to do something different. We're asking you to openly share the products of your research. We're asking you to share your data. We're asking you to share your tools. Those are skills and those are practices that generally have to be taught and developed. And so an organization like INCF is part of that very important community infrastructure that allows us to develop what the norms and practices are for both open and fair neuroscience.
INCF is doing a lot of work to make the world of interoperability in neuroscience very effective, as well as bringing people together from different backgrounds that handle different kinds of data to ensure that they can speak to one another and communicate effectively.
I think INCF is unique in that it's really a champion for sort of data standards, open neuroscience.
It's all like sort of a family. We share the same problems. When we are meeting, we're actually finding solutions to these problems and working problems out. And this is great.
The thing I like most about INCF is its educational products that it's putting out to the research community for free.
So the training space is this place where the community can go and find training material developed by IBRO, FANS, HBP, OHBM, Repronim. All the training material can be indexed and characterized for people to easily find a specific training on what they need in terms of neuroscience. So the training space is key for INCF because we want to train a new generation of neuroinformaticians. The knowledge base is a little bit like a Wikipedia page. So you would go, find the term, have a description, but also have the tools and the data that are related, as well as the literature around that term.
So INCF is bringing people together to learn from each other and to actually improve the ways in which we can use the science that's already been done to innovate for better science in the future.
I think working together is important in practically all human endeavors. With regard to the nervous system and science, of course, one should strive to interact rather than compete.
And mute myself, otherwise that's not going to work. So we figured we should start actually with that video because it sort of is a good example of what INCF is doing for us. And now I'm going to bring Matthew on stage because we couldn't have him before because Crowdcast only allows 4 people on stage. It's a very small stage. Okay. And I think that we should, I think Camille also wanted to join us. So maybe, Selim, are you okay if we vacate your seat? Okay, cool. So I'm going to have Camille join us as well. There's a lot of like seat swapping on this thing. It's like a musical chairs without the music. It's really just not. I mean, we could have music playing in the background, but it'd get even more confusing for everyone. We'll get there
very
eventually.
Entertaining host, I have to admit. It's been very entertaining to watch you navigate all the issues and troubleshoot on the fly.
While telling dad jokes. It's very impressive.
Impressive. Sorry about that. That's the only kind of jokes I have.
So should I introduce us or?
Yeah. Just I think we have a lot of people here who might be new to the Brainhack community and might have never heard of INCF. So yeah, go for it. Tell us everything.
All right, great. Well, not everything, maybe because that could take a while, but my name is Helena Ledmir. I am the Director for Development and Communications at INCF, and Matthew Abrams is the Director of Science and Training. So I'm not gonna talk about history and all kinds of organizational stuff because we wanted Matthew to sort of dive right into the good stuff that's relevant to this community. So Matthew is going to talk a little bit about the science and training bit, and then we're going to talk about more how we can sort of bring the communities together and collaborate better in the future. And that's why we have Camille here, who has experience from being involved in both INCF and OHBM for a long time. So Matthew, take it away.
Okay, that was a great introduction. So I kind of have to change how I was going to do this. But I mean, so as Helena mentioned, the goal for us really is just to see how we can bring the two communities together. INCF has been a major supporter of OHBM's Open Science SIG in the hackathon since 2013, which I believe is the first year that the hackathon was held in Seattle. And it started off primarily with members of the INCF community who wanted to bring the open science, data sharing, standards hackathon sort of mentality that's part of INCF to the OHBM community. So since then, it has grown and grown and grown to what we are today. So we're very impressed with the investment that we've made every year, that it's growing the OHBM open science community. But for us, we would like to bring that back in to the fold, because we feel that OHBM is developing into a silo, and that's exactly what the open science SIG is supposed to be against, developing a silo. So we want to bring you back into the fold. And so the purpose of this primarily is just to have a discussion about what would it take, what do people perceive as the barriers or the challenges to working through INCF, how we can work together. And before we get to that part, as we mentioned before, that some people may not have heard of INCF before, but I'm certain you've heard of some of the products and services that have been developed as a result of participation in INCF. So we're going to have a little poll going on. Are you ready for that one? So if you've heard of BIDS, the Brain Imaging Data Structure.
Let me just send the poll.
Are you sending the poll? Okay.
Yep. Let's make it visible. Can you see it at the bottom of your screen? So we're going to have a quick... Yeah.
So we have, okay. So the Brain Imaging Data Structure, BIDS. So people doing that one. NIDM, the Neuroimaging Data Model. Have you heard of that one? Let us know.
You're going faster than I'm going, then I can type without making huge typos. So it's going to be very...
Yes. So
And
NIDM.
we can leave a bit of time. We only have 16 votes. Come on, people. Do you know BIDS or not?
Do you know BIDS? Come on, people. Let's see.
Oh, yeah, the poll is right next to the... Yeah, maybe people can't see the poll.
You can only see one?
It's just you have to open it, right? You have to click on polls and then you see it, because it's only 22 votes, so I think... And there are 76 people in the session, so...
Yeah, so definitely we should have more answer than this.
Yeah.
So please click on polls and...
Click on polls, yes.
Click on polls. How is that supposed to make sense? We've met, but we cannot claim friends.
Oh, NIDM is really nice. It's a good friend, I promise.
Well, yeah. Well, you would say that, Camille.
I'm pretty objective, as you can imagine.
I know.
So I'll put up the next one. It's called RRID, Research Resource Identifier.
Yeah, I mean, people have been hearing about BIDS for the past 2 days. So if we didn't have a majority of people saying yes, I'd be going like, what's going on? Like, where have you been in the past 3 days?
What's going on?
And I'm sure that the one no vote we get is maybe just a contrarian who's just going like, because we have a few in the crowd.
It was me.
We're a few people just going to take pleasures and just going the other way if just to show that they can.
And then finally, the OHBM Open Science SIG. That's an easy one. You should get 100%.
I'm curious about this one. Woo!
Mhm.
Yeah, exactly. Like if we get too many no's on that one, I'm really going to start worrying about what is going on.
Then we have a communication problem.
Yeah, then we definitely have a communication problem. On the last
Well,
one.
now that we've said that, it's not a very objective poll, I guess, because we've just shied out the people who didn't know what this was. So if you don't know what's the open science thing, yeah, just say no.
Yeah, there we go. We have the
See?
contrarians dropping in onto the OHBM open
more.
science SIG. Yeah, exactly.
Yeah.
So I guess we should advertise it even more.
Just the reason why I bring up these things, because these are things that have been supported by the INCF network. So this is where we dump resources into. Helena will speak a bit more about we've changed the model and how we operate now. So it really is important.
Maybe we should do a poll about how many has actually heard about INCF before.
Oh, that's true. Yeah,
that's a good point. That's a good point, actually.
That's a very good point.
Let me try that.
And then we have a question. I don't know if we take questions in the middle, but we have a question.
I think we could take question. So the question is, how is RRID different from Zenodo? So while you keep answering the poll, you can maybe go on that one.
Okay, so the purpose with the research of the RRIDs, we're trying to give IDs to all the units of research. So you can have an RID for your project, you can have an RID for your infrastructure, you can have an RID for your software, all sorts of things. And this is all tractable using Google Scholar. So for you as a developer, it's a good way for you to be able to say, here are the people who are using my resource. And quite a few journals are making it mandatory where you have to include the RID for these things. So if you're a developer, it's a really good thing for you to have this as a way of tracking usage and how people are working with your stuff. And also, if you've ever done, I was an experimentalist. So when I did my research, people oftentimes wrote the wrong antibody. So you would go through an entire experiment and it's like, this was completely incorrect. So using hypothesis combined with the RID, you can go back, you can annotate the web and say, no, this is the correct antibody that they meant in this. And that is all on the web and you can see it. And Camille has just put in the links to it. Or if you go to incf.org, you can see a brief tutorial on the RIDs and why you should use them and how you should use them. So that's a good thing. So that's why we advocate for the RID.
We're going to get sidetracked, but Stefano was asking right after this. So RID, would it be possible for early stage of thesis just to keep track, to use them?
Say it again, I missed it.
So I've posted it in the chat, but so RRID would be possible for early stage of thesis just to keep track. I think, Stefano, you might want to rephrase this because I'm not sure exactly how that... no, that was Celine who asked this, apparently.
Yeah. What do you mean?
I don't know, Celine, I will let you rephrase that because otherwise we're gonna... Okay, so we have quite a few people who had not heard about INCF. Most had heard about the OHBM OSSIG. RRID is fairly new, seems to the people here. NIDM a bit less, and BIDS, I think the person who voted no decided to change their vote and went for a yes instead. So we have 100%. We have 100% votes on BIDS. Good. Yeah. So sorry.
So should I just do like the 30-second intro on INCF for those who have no clue what we're doing?
That's probably we should do that, yeah.
All right, so we've been around for about 15 years by now. Our current focus is to develop and endorse standards and best practices. And the standards and best practices that we do support, they have to comply with a FAIR principle. I hope everybody are familiar with the FAIR principles.
Just in case, maybe remind people. Okay. Yes.
So FAIR is a very convenient acronym. It stands for findable, accessible, interoperable, and reusable. So it's very open science.
For your data and your metadata,
yes.
so it can be findable, accessible, interoperable, and reusable by humans and machines.
And machines, yes.
Both.
Absolutely.
It's not just yeah.
So that's one of our main activities, and in part to support the uptake of standards and best practices, we do a lot of activities in training, both in general neuroinformatics, but also specifically in how to implement these standards and best practices on your own research. In order to support all of these activities, we are doing a lot of outreach, like we're doing right now. We collaborate within a lot of different projects and initiatives. We act as sort of an intermediate between the large international brain projects, like the Human Brain Project in Europe, the US Brain Initiative, the Brain Minds Project, the Australian Brain, I forgot what it's called right now, but the big Australian project, CONP in Canada, and whatever else have you. Yeah, that's what we do. We have our own annual conference on neuroinformatics with associated training activities. We arrange the Brain Summit every year, which is also where we collect representatives from the large international brain initiatives to talk about things to do with interoperability and data sharing across those projects. So yeah, that's the very short of it.
In a nutshell.
Yes.
Okay. Because we've been dumping some acronyms on people, should we just maybe explain what those different things are a little bit, and to sort of like give examples of concrete examples people can relate to?
Maybe
I think that by now BIDS by now, I think people are aware of what it is. That's just a suggestion of how we could do this. So you give you talk about NIDM or
RIDs as well.
Yeah, you want to continue with RID?
Or we can start with NIDM because we have Camille here, who is the best person to speak about.
Amongst others, right?
Amongst others, yes. Yeah. But you're one of the core members of that group.
Of course, yeah, I'm happy to. So it sounds like people know about BIDS, so we can just say a few words to remind what BIDS is. So BIDS is a way to organize your data, to make it first, well, to organize it in a systematic way, first for yourself. So then you have the data all organized in folders with files, but you also have the metadata. So those crucial pieces of information that you need in order to make your analysis, basically. And BIDS is based on very simple tools, like just having files, having folders, and organizing them in a systematic way, and JSON files as well to store all those parameters. The way NIDM, so NIDM is similar in a way that it's also a standard that would let you share your data and your metadata, but it's based on semantic web technologies. So it's a different, it's maybe more heavy weighted solution, but it allows for more flexibility basically. So you can organize the data the way you want, but then you basically point to where your data is located on disk. So right now in NIDM, there is a model for results for functional MRI. And as I speak, we are now working jointly with BIDS to have a model that would be compatible between BIDS and NIDM, because those two are really complementary to represent your imaging pipeline. So provenance, how, when you get a data set, wouldn't it be nice if we could have all the information of how we got there, like which software we use with parameters and everything. Of course, this is a lot, and we need a structured way to share that. Is that a good short presentation of NIDM? Is there anything else you want me to cover, Matthew?
Nope, that was good.
I put some links in the chat there if people want to check it out.
I think I would just like to mention something is that NeuroVault, where we tend to share our statistical maps, also just, you want to go for it, Matthew?
No, I was going to say, no, that's also something that INCF was very instrumental in helping to establish, get off the road, working with Chris Gorgalewski with funding through INCF. So.
Yeah, I'm just going to keep mentioning things. I'm going to keep mentioning things, and you're going to keep going. Yes, we help with this. Yes, we help with that. I like that approach. Yeah, NeuroVolt, pretty much you can just upload your results directly as an IDM results, and it's usually a better practice than just uploading your just a statistical image just by themselves. There's much more metadata, and it's much more complete. And it's very easy to create an IDM results with SPM and FSL. It's like a couple, FSL, I don't remember, but SPM, I know in a couple of clicks, you're done. So I really encourage people to have a look at this, because this is a really useful tool.
Remy is our favorite user, in case you were wondering.
Okay, can we, before I start blushing?
So yeah, and the nice thing, maybe we can talk about how an IDM and bits were developed, but these were really developed as like bringing in together researchers from different institutions and discussing together. And I mean, it's amazing to see these standards being built like from different people who have different perspectives on why they want to participate to that work. But it's nice to see that coming out of the ground. And I think BIDS is really successful in that many people have joined that community and are extending this standard to go beyond just MRI. I know now there is an EEG model and IEG model and so on, and now going into more of the derivative space. So I think it's really nice to see people coming together, and I think it's actually crucial for this kind of work, because you can't really build a standard by yourself. You have to get some buy-in from different people so that it's actually used by the community, and then it becomes really useful for everyone. Yay!
Excellent. So actually, Camille, as someone who you came into OHBM's open science community from INCF, if you can speak a little bit about how that happened for you and your thoughts on that whole thing.
Wow, how that happened for me. Well, I first joined the INCF data sharing working group when I started my postdoc. So I was a PhD student in Rennes, and in 2013 I joined the University of Warwick working with Tom Nichols. And part of my work, so I was starting a brand new work, like focusing on neuroinformatics, while before I was more doing like statistical analysis of neuroimaging data. So that was a new world, but I knew I'd be interested in that one because I had a computer scientist background, and that sounded like something that was really interesting to do. And I got to meet this group from INCF with like people coming from different places who were discussing that IDM model. So initially it was more an idea, and then together we worked to actually build the model. So this was really part of my work as a postdoc. And then I got to meet the OHBM community. So first I got to meet the Brainhack community. And I think Brainhack is really close to the OHBM OS SIG community. The founding members are both are common to these groups, a few of them. And so I first got to know the Brainhack and that different way of working where people would just go somewhere, have not really defined ahead of time what they would work on, and then there was this organic discussions that would just arise and that we try to run again here. That is really our goal, like just making people meet each other and make sure that they can share this. We were talking about that this morning during the morning coffee. Like there are so many little tricks that we don't talk about when we do a paper. We don't publish about this, but if you don't know those, then doing your research is just extremely hard. And for me, brain hacks are really the kind of space where you can have these discussions. Like you meet people and really simply you can say, okay, for instance, I've tried this tool and I'm just stuck here. I don't understand what's going on. And by working with others who've had that experience earlier, you just get going much more quickly. So we can work together as a community rather than each of us separately. And so after Brainhack, I got into the OHBM conference for my first time. So there was again a Brainhack attached to it, and the OHBM hackathon. So meeting that community and then meeting the US SIG, the work of the Open Science Special Interest Group. So the Open Science Room initially was just a room where things would happen when they would happen. There was no program. And now well, I encourage everyone to go next week and see what the OSR is this week. I'm really proud of what Cassandra Goodvan-Prague and Stefan Yunis, who are Open Science Room co-chair this year, have built together. So, I mean, for me, it's really hard to talk just about INCF or just about OHBM or just about Brainhack, because there is so much things that are common between them.
And that's what we would like for everyone else to get to see, that there is this commonality between what's going on in OHBM and what's going on in INCF. And we think it would be really good for us to join together. Mm-hmm. There's nothing from INCF perspective that says that we cannot support a open science that has OHBM's name on it, as long as we have members from OHBM who are members of INCF who are supporting that and making sure that we can continue to provide financial support to the Open Science SIG. Because Helena will tell you a bit more about how our membership model has changed, and that membership model change has impacted how we can invest in different communities. Before, it was sort of a top-down, okay, we invest in this community. Now it's more of the members themselves are deciding, this is the area we should invest in, this is what we should do. And then just for you guys, the things that we have that are available for you to continue doing your open science work even after OHBM, we have NeuroStars question and answer forum that I'm certain quite a few of you are familiar with. That's something that is was built and maintained by INCF that's open for you guys to use. We have our own online repository of training materials. Everyone's invited to use them in any sort of way they want to. And some of these training exercises have, there's always going to be a video. Some of them include the lecture slide, sample data sets, Jupyter notebooks, links to the GitHub repository, and also links to the software that you should use to do that. And this is 100% open to the community. There's no charge for this sort of service. It's our membership that are paying for these services and making them open to the global community. So that's another resource that's available to guys, as well as the working groups. As Camille mentioned, the NIDM and BIDS came out of working groups. NeuroVault, to a certain extent, did benefit from having Chris being a member of a working group and the funds that INCF commits to being able to make these groups come together. So just wanted to throw that in, but Helena, I give it to you now so you can talk about.
Well, I think while we're on that, I think we should also push a little bit for the endorsement process, right? Yes. Because I mean, this is a hackathon. I'm sure there's a lot of great tools and other kinds of resources coming out of hackathons, maybe not right away, but eventually. And I mean, the benefit of having your tool endorsed by INCF is that you get a lot of help with the uptake and adoption of your tool. We do a lot of marketing, a lot of advocacy for the standards and best practices that we do endorse. So I really encourage anybody who has something like that to check out our endorsement process and see if your tool is ready for that step yet. Thank you, Camille. I see you put the link right
You're very
there
welcome.
in the chat.
Can you maybe give us an example of the type of things that INCF is looking to endorse? Like what could people would submit as a product that could be endorsed?
So in the classic sense, we have the standards and best practices. So standard would be BIDS. Best practice could be COBIDAS, if we go by this community, just so I can stay relevant to you guys. When it comes to infrastructure, things like that, when we look at for that to see, does the infrastructure have utilized standards? Does it have, just comparing it to the FAIR principles, how well does it do that? So for that, it could be the Canadian Open Neuroscience Platform. Could be one example of a platform that could be endorsed. And another aspect of the whole endorsement process, so it's not only that we put this on our website, we give people the usage scenarios, we also link it to the training materials as well. So if you don't have any tutorials and demos, we'll work with you to develop those so that you can have them, you can use them on your website. We'll have them on our training portal. We'll advertise them at every conference that we go to. So that's usually OHBM, SFN, IBRO. And so we go a lot of places throughout the world.
Not this year, but next year.
Next year. We've done a lot of virtual meetings this year. It's been really, really tough. I almost miss going to them. It's much easier.
Is neuroinformatics going to be virtual this year?
No, we've moved it to 2021.
I see.
Okay.
Yeah. Late April.
Sounds like a very reasonable choice, to be honest.
Yes. Yeah. I didn't want to get involved with the virtual thing.
I think
it's fun.
Yeah, it's fun. And moving really quickly to virtual has its struggle.
So what we've been doing a lot of helping people with in terms of helping a lot of other conferences go virtual. So we've been helping a lot of courses. So we have, for the computational neuroscience, it's something called the Neuromatch Academy. So we're leveraging our training space to be able to do this sort of pre-recorded lectures, live Q&A sessions, and leveraging NeuroStars and pulling that all together. We're doing the same thing for Neurohackademy. So that's, data science with a bend towards neuroimaging. We're going to do the same thing for their course as well. So we're pulling everything into training space so you can, no matter where you are in the world, you can watch it. You can do the live Q&A session, or you can follow up in NeuroStars, and it'll all be integrated into the training space page. And that is something that is open to, say, if OHBM's Open Science 6 said, you know what, we want to be a member of INCF. We want to be a part of this. And you would have your own sort of organizational page within training space where all of your content would be linked to. So it could be quite a good way to disseminate your information and things that are going on.
Mm-hmm. That's good to know. Yeah.
I'm always selling the products because I think it's good to have people use them.
Can I ask a question that's a bit like spontaneous, because a couple of people have told me, I'm working on this project or that project. You should maybe try to pitch it to INCF. And I think from my point of view, it was a bit of, oh my God, that's going to be so, like, it was always a bit intimidating because it feels like it's a very standardized thing. And I'm really far away from having stuff super standardized, contrary to what some people might think. So how would be the onboarding process of someone who would want to sort of contribute to what you do?
There are a few ways. You can go through the working group mechanism, or you can set up your own special interest group, and we provide support for you to get that group going. But I think a good thing with the endorsement process, it's not just about getting this INCF stamp. We've had a few projects that have come in quite early in their process, just to get the feedback from the committee to be able to say that, okay, this is what you need to work on. These are the things we should do. So it's a two-way street. It's not that we just want to say, yes, no, this is good, this is bad, but we really want to help everyone achieve this endorsement, because if you achieve the endorsement, that's fulfilling our aims about creating this open, fair neuroscience ecosystem. So that's what we try to do. We try to work with the groups as well. So the earlier you come in, the more support you can receive. We'll also help you with, we host lots of workshops, so we make sure that you're a participant in one of the workshops that we thought was applicable to your work. When you're first getting trying to get your user base and user community, at our annual conference, we have training days. So you could have a 1 to 2 day workshop to onboard more users, to have a hackathon, things like that. That's something that we've been working with a lot with Neurodata Without Borders. It's a data format for electrophysiology data. Work with them to try to get a larger user community, to make it more international, and also for them to see what the barriers are to adoption so they can start working on those to make it much easier. So we try to give you a holistic thing. We're a laid back group, as you can see, Helena and I.
Yeah.
We're both the
very
directors.
flexible.
So, and you can't get any more laid back than I am. We're very chill, but we do make sure that you get what you need to get out of us. We really are committed to open and fair neuroscience. That's
So you're totally not expecting a final product to be brought to your door. Go like, this is what we're doing. It has to be. No, you're going to guide people through the whole process.
the whole process. We can think of bids in IBM, those ideas that have fleshed out into something. NeuroVault was a concept. There was a rough prototype in the beginning that we worked with Chris and the community worked with him to get it to what it is today. So that's how we do it.
Yeah.
Okay.
I think
No, that is super
working,
useful.
sorry.
No, go for it.
Working groups are probably a good starting point. Like if it's an idea that is not fleshed out completely already, then that's a space where you can bring in people and just have these discussions within the INCF network.
So one thing, just to give a segue into Helena's speaking more about the membership, one reason before our membership was based on country membership, so countries would join. And the problem with that is that a lot of people who were living in the countries did not really realize that they were members, so didn't know how to really get involved and engaged, and we didn't know who to go out and engage with. So now we are allowing individual, institutional, lab membership sort of things. So you can come in with your whole lab, or you can come in with individual to get at least so we know who you are, and we can give you the information that you need so you can better find your way through INCF to get engaged, to get more engagement. So if you came with an idea, say, oh, I'm interested in this, we can look through our membership list and say, okay, here's some other people who are interested in that. We can send them, a message. Oh, there's someone who's interested in starting this type of working group. If you're interested, we're going to have a sort of a virtual meeting on this date. If you can join, come on in. Let's have some fun. Or we can arrange an in-person meeting at a conference as well, where you can get interested parties to come together and meet. So we do all those sorts of things. So Helena, that's you. That was
right. Yeah, I don't know where we are on time because
we are 38 minutes of live streaming. I think our session was planned for 45 minutes. So
excellent. Perfect. Right. So the membership then, yeah. So my screen was froze for a bit, so I don't know what exactly Matthew did say about the membership, but I think you said that originally it was country-based.
Yes, go for it.
Yeah. Yeah, so we had to move away from that model for a number of different reasons. One of them being that it was not really great for community growth because the history of it all was that it used to be where somebody got in touch with us through one of our events or heard from somebody else, and they rallied their lab or their institution to get engaged, and then we helped them acquire the funding. We lobbied to their funding agencies and helped them write the grants and so forth. And then they came up with the country membership fee, which was quite large. But what happened was that that sort of group of people, the local node, like we call them, they became sort of a bit of a bottleneck for us to get to the rest of the community in that country. Not their fault. We're not blaming anybody. It's just people are wearing a lot of hats and have a lot of stuff to do. So it's not really surprising. But we did realize that we needed to open up the membership to smaller entities. So we spent a lot of last year trying to figure out how that would work. And I think by SFN last year, we had the new model in place. So the membership in INCF is now open to institutions, universities, projects, other nonprofit organizations, companies, and also individuals. At, of course, much, much lower rates than the country fee ever was. So I don't know, I guess I could put up a slide. Let me try to, okay, too many videos. Never mind. We don't need slides. Slides are dull.
It's just like an old person. That's the thing.
Yeah. No, I'll put up the link in the chat and tell you about it instead. So there's a couple of different levels of membership for institutions, organizations, and companies. I'm actually just going to talk about the individual ones here because I think that's the level we're at. If you become an individual member of INCF, you get a lot of great benefits, such as a discount to our annual conference, of course. You get discounted APC if you want to submit your paper to F1000. You get a free year premium account at protocols.io. You get discounted tuition to the Force 11 summer courses. And what we're extra pleased about is that if you join INCF at the very low price of $20 for students and $50 for researchers, is that you are also automatically a member of FENS. I assume or hope that everybody knows FENS, the Federation of European Neuroscience Societies. We're happy about this, and actually FENS is very happy about this too, because this is like the first mechanism that they have to bring in people from countries outside of the EU, because anybody can be a member of INCF, whereas the FENS societies only have European members. So this is a way for FENS to get in international members, but also a way for us to offer a lot more benefits to our individual members. So the FENS membership includes like opportunity to apply for free abstract slots to SFN, subscription rates, discounts to a lot of neuroscience journals. You get access to NeuroOnline, the SFN educational platform. You get free online access to the European Journal of Neuroscience, for example. You get reduced registration fees for the FENS Forum and other meetings that they organize. So yeah, the link is right there in the chat. You get access to this, and also, of course, access to our lovely community, which is great. They've stuck with us for many years. So I can really recommend you guys getting involved. You, of course, also get, a say. You get a vote on stuff. The individual membership has elected positions to some committees, scientific one, etc. Also, I should say that about the institutional or nonprofit memberships as well. In those are included a certain amount or a certain number of individual memberships. So if anybody here thinks that their institutions or project should become that kind of member, then if you have questions, just get in touch with me and I will answer all of your questions and help you get that process going if that's of interest.
Do we have Elena's contact on our website next to the talk? Do you know, Remy?
We do. Yes, we have. Well, you're gonna get people contacting you through Twitter if that's the case.
That's fine. I conduct a lot of business via Twitter. It's okay. I put my email address there in the chat. So.
So no, just we see that there weren't so many people who had heard of us before. So I would just encourage you to take a look at our website, take a look at our training space, Neurostars. You know BIDS, you know NIBM, then you know what we're about. So we really would like to get you guys engaged, involved, and part of the process because, as I mentioned before, the sponsorship that we have provided to OHBM's open science initiatives, I will say it like that, because it started off as a hackathon and then it's just kind of grown into something that I don't even know what it is any longer, but it's this larger ecosystem of events. It really is going to be dependent on the membership votes and how the members say funds should be allocated into which areas. Just to let you guys know that the Organization for Computational Neuroscience, which is a computational neurosciences version of OHBM, they've joined as a member to be able to steer some of INCF's resources more towards the computational neuroscience side. So we need some more neuroimagers in there to keep the balance between the two sides. So that's, if you want us to continue to support, we need you to join in and let your voice be heard.
Yeah.
Okay.
No, it's also about what we were talking about earlier. Like if you come with sort of just an idea or a concept of something, our annual meeting is a really good place to sort of get informal feedback on that kind of stuff, or, submit a poster or whatever, or a demo. We have demo slots as well. It's a really good place because people, the community who comes to our conference, they're very open and they're easy to talk to and they're super happy to give you feedback on your work. So I would really recommend that for that purpose as well.
And since you brought up demos, I would like to say that INCF were the ones who brought the demo to OHBM in Singapore. We paid for that entire experience for there to be live demos at OHBM, because in our community, that is a very strong part of how you walk someone through a tool, software. A poster gives you something, but it's nothing like being able to sit there with a laptop and go through the actual thing. So that's, again,
we're much more interested in the two-way communication than somebody just standing up and talking at you kind of thing.
I like that.
Yeah, me too.
I think a lot of people here like that.
Yeah.
Definitely. Cool.
Okay.
I think we're running short on time, so we should probably wrap up.
Yeah.
Thank you all for coming.
Yeah.
And making,
well, thank you. Thank you very much for joining us. And so just remind us what would be the best way to contact you. Just we go on the website and just or we email you at the email address you just put there.
Email Helena.
Yes, email me, tweet at me,
Email Helena.
Yeah, follow me on Twitter. I make a lot of cakes that I put up there, as Isabel has just pointed out in the chat.
Oh yeah. Her Twitter, the quality of her tweets is amazing. If only just the regular cat pictures, right?
Yeah, Scully GIFs and cakes and the occasional heavy metal song.
Good. Okay, so maybe we're going to wrap it up.
Thank you all.
Yeah. Thank you all.
Thank you so much.
Thank you like a million times. It was great to have you. Definitely.
Thanks for having us.
Okie dokie. Let's wrap this up. See you soon.
Bye-bye.
Bye.
Bye.
Hello, everyone. I'm Leonardo Accarino, a postdoc at UCSF. Today, I'm very excited to give this short talk on brain visualization. And actually, very quick disclaimer to begin with, I'm not a professional programmer or graphic design expert. I'm really just a random postdoc working with neuroimaging data, and perhaps with a particular interest in visualization. As a quick outline, I'm just going to share with you some general thoughts and maybe possible tips in the very first part of the presentation, like 6 or 7 slides, and then I'll go through an actual working example. So I will introduce some analysis I've run for a paper that was recently accepted, and then share with you the actual process, get into the final figures. As for the general thoughts, I think we can all agree that visualizing neuroimaging data on brains is all about pros and cons. And really, I could come up with this as like possible groupings, like general groupings of approaches to show neuroimaging data. And they range from the single or multi-slice, which I believe is very frequently adopted all around the literature, to the 3D, three-dimensional and surface rendering approaches, also very, very frequent, and then the flat maps. And I think you can kind of see along this fictional x-axis a different degree of complexity, right? All these approaches, I do believe, have pros and cons. And just running quickly through them, if we think of the single and multi-slice approach, I think it is, like the main pro is that it's really simple. It's easy to tweak. It's flexible because it's easy to design. You can choose the slices or the views or the planes and so on. It's safe because it's reproducible. If you're actually publishing your coordinates where you actually grab the slices, especially if you're in standard space, I think it's fairly easy to reproduce. And also it's accessible. There are so many software available. As main drawbacks to this approach that I could think of, I think one, of course, is that this approach by definition is partial because you're only showing some of the data, like not the full brain, but only some slices. And I think this also takes us to the next drawback, which is that this approach is prone to cherry picking. Like users may choose slices ad hoc to make their point, which, can kind of, I guess it's also about transparency, but it's an approach that, of course, being partial kind of wants you to pick slices to make your point. As for the three-dimensional and surface renderings, I do believe they are super informative. They convey a lot of info, and they are really easy in terms that I think they also they help in understanding the anatomy and the localization of the results. And also they are very immediate, like the data is visualized literally in a glance. However, they are more complex because they require methodological choices. For instance, the mapping algorithms or also the lighting algorithms of the figures. And they could be misleading because some of these choices could actually change the final visual result of the figure. As for the flat maps, I think they are very accurate because each voxel is represented, and also they're very precise because the shape of the structures is preserved. However, they're difficult because they require expertise, I think, of the reader to be fully understood and interpreted. And also they're not that available. There are not really like many softwares actually able to generate them easily, at least. And, as always, your choice will make the whole difference in the final outcome. As a sample example that I was thinking of, I literally just generated this functional connectivity map from NeuroSynth. And this is just a functional connectivity map originating from this seed, like from this voxel I clicked in the posterior cingulate. And literally, like NeuroSynth is using this multi-slice view as a default for the positive values. So you can see 3 planes, like a single slice for the axial, the coronal, and the sagittal. And of course, this is already giving you a lot of information. What I did was just downloading this NII, so nifty image, and plot it with Brainhack. So Brainhack is one of the possible software you can use running on MATLAB to do surface renderings. And this is exactly the same image. However, we do the Viridis color scale. And this is also an image showing only the positive values, just like the one you're seeing on the left. But it's a different visualization. And of course, gives you a bit more info compared to the multi-slice. Literally, one point that I wanted to make is that all these other figures that now I'm showing, they are all coming from exactly the same nifty image. But they do look a bit different, right? They along like this y-axis going from the top to the bottom, you can see that the topography and the intensity of the signal seems to change, or the result seems to change, but actually it's exactly the same image with the same range of values. So what I'm changing here is only the mapping algorithm, which is different across the 3 figures. And I believe this is really important because some of these regions or clusters look quite similar, so that doesn't make a lot of difference. But other clusters, like these ones, they literally like their appearance, or I'm showing. Hello everyone, I'm Lardo Accarino. But they do look a bit different, right?
Hello everyone.
Along like this y-axis going from the top to the
So this talk, I'm going to tell you about how we use Brainhack.
Hello everyone, I'm Lardo Accarino, postdoc at UCSF. Today I'm very excited to give this short talk on brain visualization. And actually, very quick disclaimer to begin with, I'm not a professional programmer or graphic design expert. I'm really just a random postdoc working with neuroimaging data, and perhaps with a particular interest in visualization. As a quick outline, I'm just going to share with you some general thoughts and maybe possible tips in the very first part of the presentation, like 6 or 7 slides, and then I'll go through an actual working example. So I will introduce some analysis I've run for a paper that was recently accepted, and then share with you the actual process.
I'm going to tell you about how we use Brainhack.
Hello everyone, I'm Lardo Accarino, postdoc at UCSF. Hello everyone, I'm Lardo Accarino, postdoc at UCSF. Today I'm very excited to give this short talk on brain visualization. And actually, very quick disclaimer to begin with, I'm not a professional programmer or graphic design expert. I'm really just a random postdoc working with neuroimaging data, and perhaps with a particular interest in visualization. As a quick outline, I'm just going to share with you some general thoughts and maybe possible tips in the very first part of the presentation, like 6 or 7 slides, and then I'll go through an actual working example. So I will introduce some analysis I've run for a paper that was recently accepted, and then share with you the actual process, get into the final figures. As for the general thoughts, I think we can all agree that visualizing neuroimaging data on brain is all about pros and cons. And really, I could come up with this as like possible groupings, like general groupings of approaches to show neuroimaging data. And they range from the single or multi-slice, which I believe is very frequently adopted all around the literature, to the 3D, 3-dimensional and surface rendering approach is also very, very frequent, and then the flat maps. And I think you can kind of see along, and then I'll go through an actual working example. So I will introduce some analysis I've run for a paper that was recently accepted, and then share with you the actual process, get into the final figures. As for the general thoughts, I think we can all agree that visualizing neuroimaging data on brains is all about pros and cons. And really, I could come up with this as like possible groupings, like general groupings of approaches to show neuroimaging data. And they range from the single or multi-slice, which I believe is very frequently adopted all around the literature, to the 3D, three-dimensional and surface rendering approaches, also very, very frequent, and then the flat maps. And I think you can kind of see along, and then I'll go through an actual working example. Hello, everyone. I will introduce some analysis I've run for a paper that was recently accepted, and then share with you the actual process, get into the final figures. As for the general thoughts, I think we can all agree that visualizing neuroimaging data on brains. Hello, everyone. Hello, everyone. I'm Leonardo Accarino, a postdoc at UCSF. Today, I'm very excited to give this short talk on brain visualization. And actually, very quick disclaimer to begin with, I'm not a professional programmer or graphic design expert. I'm really just a random postdoc working with neuroimaging data, and perhaps with a particular interest in visualization. As a quick outline, I'm just going to share with you some general thoughts and maybe possible tips in the very first part of the presentation, like 6 or 7 slides, and then I'll go through an actual working example. So I will introduce some analysis I've run for a paper that was recently accepted, and then share with you the actual process, get into the final figures. As for the general thoughts, I think we can all agree that visualizing neuroimaging data on brains is all about pros and cons. And really, I could come up with this as like possible groupings, like general groupings of approaches to show neuroimaging data. And they range from the single or multi-slice, which I believe is very frequently adopted all around the literature, to the 3D, three-dimensional and surface rendering approaches, also very, very frequent, and then the flat maps. And I think you can kind of see along this fictional x-axis a different degree of complexity, right? All these approaches, I do believe, have pros and cons. And just running quickly through them, if we think of the single and multi-slice approach, I think it is, like the main pro is that it's really simple. It's easy to tweak. It's flexible because it's easy to design. You can choose the slices or the views or the planes and so on. It's safe because it's reproducible. If you're actually publishing your coordinates where you actually grab the slices, especially if you're in standard space, I think it's fairly easy to reproduce. And also it's accessible. There are so many software available. As main drawbacks to this approach that I could think of, I think one, of course, is that this approach by definition is partial because you're only showing some of the data, like not the full brain, but only some slices. And I think this also takes us to the next drawback, which is that this approach is prone to cherry picking. Like users may choose slices ad hoc to make their point, which, can kind of, I guess it's also about transparency, but it's an approach that, of course, being partial kind of wants you to pick slices to make your point. As for the three-dimensional and surface renderings, I do believe they are super informative. They convey a lot of info, and they're really easy in terms that I think they help in understanding the anatomy and the localization of the results. And also they are very immediate, like the data is visualized literally in a glance. However, they are more complex because they require methodological choices. For instance, the mapping algorithms or also the lighting algorithms of the figures. And they could be misleading because some of these choices could actually change the final visual result of the figure. As for the flat maps, I think they they are very accurate because each voxel is represented, and also they're very precise because the shape of the structures is preserved. However, they're difficult because they require expertise, I think, of the reader to be fully understood and interpreted. And also, they're not that available. There are not really like many softwares actually able to generate them easily, at least. And, you know, as always, your choice will make the whole difference in the final outcome. As a sample example that I was thinking of, I literally just generated this functional connectivity map from NeuroSynth. And this is just a functional connectivity map originating from this seed, like from this voxel I clicked in the posterior cingulate. And literally, you know, like NeuroSynth is using this multi-slice view as a default for the positive values. So you can see 3 planes, like a single slice for the axial, the coronal, and the sagittal. And of course, this is already giving you a lot of information. What I did was just downloading this NII, so Nifty image, and plot it with BrainNet. So BrainNet is one of the possible software you can use running on MATLAB to you know, do surface renderings. And this is exactly the same image. However, we do the Viridis color scale. And you know, this is also an image showing only the positive values, just the one, just like the one you're seeing on the left, but it's a different visualization. And of course, gives you a bit more info compared to the multi-slice approach. One point that I wanted to make is that, you know, all these other figures that now I'm showing, they are all coming from exactly the same Nifty image, but they do look a bit different, right? They along like this y-axis going from the top to the bottom, you can see that the topography and the intensity of the signal seems to change, of the result seems to change, but actually it's exactly the same image with the same range of values. So what I'm changing here is only the mapping algorithm, which is different across the 3 figures. And I believe this is really important because some of these regions or clusters look quite similar, so you know that doesn't make a lot of difference. But other clusters, like these ones, they literally, like their appearance or their presence in the figure is totally related and dependent on the mapping algorithm you pick. And the question, I guess, is what is the right one? And the problem is that there is not really a gold standard or a unique solution. And it's kind of up to your responsibility to provide an accurate depiction of your results. For instance, you could also try different types of visualization and kind of understand whether this cluster is really there or not, and choose accordingly the visualization. And, you know, like we are still talking about neuroimaging data, but you do not only show neuroimaging data with brains. You can also show neuroimaging data without brains, so with other types of visualization. And I just wanted to give a brief overview of some other approaches we have done in the past. And one is this paper by Renaud Lajoie, who is a colleague, another postdoc in my group. And here what you're looking at, I'm not going to go through the whole paper, of course, for the sake of time, but what you can see here is that basically he was testing the correlation between brain images, between pairs of brain images. And, you know, you could, for instance, here on this plot, I believe you can see, sorry, I'm gonna just move this a bit upwards. I believe you can actually see here on the left that he was testing the correlation, for instance, between these 2 images here and also between these 2 images here. And, you know, qualitatively, you can kind of look at these images and understand that this one is looking way more like this in terms of gradients of the signal, and this one kind of looking less alike to this one. And this is, you know, a qualitative assessment. But going to these voxel-wise scatter plots he used, of course, was bringing the point home, I think, in a way more immediate way compared to just using brains. So switching to non-brain visualization for brain data actually worked pretty well. And, you know, like an alternative to this visualization is also using hexed scatter plots instead, which are a good alternative, and they also can provide a lot of data also on the density of the different voxels in the different ranges of values. This is another example from a reused paper of mine. And here what I was showing was just the extent of the different functional networks, like in terms of how big the networks were, like literally the number of voxels. And, you know, we had a lot of course, like brains and brain renderings for these results, but there were many. And what we were doing here is just comparing the sides of these different networks across 3 different groups. So healthy controls, and then within 2 groups of patients with dementia with Lewy bodies, with or without hallucinations. And what we did at the end was using this radar plot that you can see here, because basically I think this really brought the point home that first, the healthy control networks were larger than the ones measured in the patients. And then also within the two subgroups of patients, you could kind of easily understand which ones were larger or smaller than the other, respectively. And then the third example I wanted to make is regarding this approach, which is a correlation matrix. This is a fairly common approach to show connectivity data, correlation data within brains. And you can see here, this is from an actual other paper of mine. And I'm actually also showing here the brain renderings, like the nodes and edges with visualization, to give you an idea. Like I'm providing here exactly the same type of information. But probably the correlation matrix is easier to understand and to kind of grasp what regions are correlated with what compared to a crowded nodes and edges visualization. So this was just to give you an overview of how I believe non-brain visualization can be useful with brain data. Every time I'm making a figure, I have to say I feel like I'm making executive decisions to put myself somewhere here. So while I was preparing this talk, I came up with this, and I think it's pretty good. It's showing like you have to kind of put yourself somewhere across these different quadrants, right? Between simplicity and complexity and partiality and completeness of the info. And I was trying to think of my journey so far in my academic career. This is an actual animation with myself going around in different quadrants. And I believe so far I'm kind of moving in the right direction to what I called the holy grail of visualization, which is an image that is very simple and it's complete. And I think on the way there is few things we can consider to make our figures. And these are, of course, always very humble opinions coming from me. The first, of course, is that, as always, less is more. You always hear about less is more when you are attending a talk on visualization. And really, crowded figures do cloud the interpretation. They make it harder to understand the results. The second thing that I want to say is that color scales, they are dramatically important. Changing color scale can totally alter the way you are conveying your findings. Of course, as I was mentioning before, I think it is really useful to combine brain and non-brain based visualization for neuroimaging data. I think can make things way more clear. And I think one important thing I wanted to stress is that complexity, at least to me, is not quality. When I see a complex figure, I'm always, it's not like I'm taking for granted that behind that there is a very high value, top-notch story. A figure, in my opinion, should always be self-explanatory. So a very complex figure may be not self-explanatory, which probably sometimes is not good. Another thing I wanted to say is that a good practice is always to clearly describe the methods you use to obtain the figure. For instance, especially if you're using renderings, which software you use and which parameters you use to actually create the rendering. And finally, of course, providing the actual images plotted, like the brain images, for instance, a TMAP can help. And of course, there is public repositories right now, for instance, NeuroVault, to do it. And in that case, you're just providing the brain image. So you're kind of also providing the raw data used to make the figure. So let's switch to the working example. I'm not gonna describe in like a lot of detail the paper, but this was a study on spatial extent. So basically, we studied how diffuse in the brain, so basically the percent of gray matter involved, were abnormalities measured with different modalities, including the amyloid PET, which is, if you're not familiar with, it's a neuroimaging technique that basically evaluates the amyloid plaques accumulation in the brain, and this is a signature of Alzheimer's disease. Tau PET, which is very similar to amyloid PET, but it's a different tracer, so it's actually targeting neurofibrillary tau tangles in the brain, which is another signature of Alzheimer's disease. And then finally, FDG PET, which is a neuroimaging technique investigating brain glucose metabolism. And basically, we had data for about 80 patients, and for all of them, we had these 3 scans. So just to give you an idea, this is a single case. This is an image of amyloid PET, which is PIP PET. The tracer is called PIP. And this is a tau PET image. The tracer is called FTP. And then finally, this is an FDG PET, and the tracer is FDG. What we did was comparing all these different images with a set of normal controls, and we ended up with these images that you can see here that are basically binary images, where each voxel with a 1, so appearing white here, is abnormal compared to the controls. So since we knew how big the mask was for the analysis, we could estimate what was the actual proportion. And here I'm just eyeballing them and say that, for instance, this image looks like it's 96% of the gray matter. The second one, this one, I believe, is around maybe 88, and then this one is way less, so about 4 or 5. So the story is, how do we convey this info? Like, how do we convey the spatial extent info for all these different subjects according to these 3 different modalities? Like giving this information using brains, even if this is brain data, would have been extremely difficult. So what we did was actually just go into box plots, which, it's a simple plot, but really takes the point in this case, because gives you first an immediate idea that the modality here in blue is way more extended compared to the green modality or the red modality, and also gives you the chance with individual points to understand that, for instance, in this modality, FTP, there were 2 different groups, one group here, like subgroups of patients, one group here, and one group here. So it's kind of immediate approach. And then, of course, another question was, is it always that within each subject, this is the hierarchy, right? For instance, every given subject has more amyloid, and then some tau, and then some neurodegeneration. So they kind of go one step after the other. And also in this case, would have been very hard to show brains for all these patients. That would have been hundreds of brains. So instead, we're using spaghetti plots. And also in this case, I think these spaghetti plots really give you the idea and show you what are the possible hierarchies. You show the individual hierarchies in kind of gray on the background, and then we also identified the main hierarchies, which are the colored ones you are looking at now. So also these are 2 examples of non-brain visualization of neuroimaging data that we believe were very clear. So far, I'm actually completely missing a crucial info. If you were reading my paper, then I believe one question would be, what about the overlap? Like all these voxels could be positive or abnormal in these 3 different modalities, all of them, or like many different combinations of them, like 2 pairwise combinations. So what we did was basically, starting from these 3 binary images that I was telling you about, we summed them. So it's a very simple sum with the nearest neighbor interpolation. And you would end up with an image that looks like this, right? So it's a sum. And before the actual summing of the 3 binary images, we assigned unique values. And by doing so, we could identify then, after the summing, that we could identify, yes, all the possible voxel classifications, like all the possible pairwise combination, and actually not pairwise, but all 3 of them, and how, like which one was positive and negative, and positive and negative across the whole brain. And this was done for each single subject. And this, of course, took us to the possibility of actually identifying groups of voxels that were defined according to the different 3 modality status. Once we had this, the question now was, how do we show these results, right? So there is 2 things about this story. One is where these voxels are across the group, and the other story is how many are these voxels across the patients. As for the first story, so where are those voxels? Of course, we kind of thought that the brain visualization would have been better and more informative, so we actually picked surface renderings, which is what you're looking at here. And you see, I think this really give an immediate message, that is that these different voxel classifications that you see on the bottom of the figures do have different localization across the brain. So these are frequency maps. So the story is kind of, voxels that belong to this classification tend to be here and here across the groups, while voxels that have this classification tend to be here and here, and so on. I think there is lots of info here, and it's really great to indicate what is the localization, but there is nothing about how many voxels belong to these groups across these classifications across our group. So to do so, we switch it again to non-brain data, and that's what you see here. This is like a Venn diagram, which maybe might not be the first thing you think about to show brain data, but in this case, I think it's really taking the point, because it's kind of telling you what are the different intersections across the whole group between the different voxel categories. And if we know the color, of course, and like the categories that you're seeing now on the right, we can estimate these numbers, which is the median number of voxels belonging to those different classifications for each single subject across the whole group. And also in this case, the Venn diagram is really helping us. So to wrap up, just to give you like few take-home messages, I believe that executive decisions on this visualization can really give you a completely different result with different trade-offs between partiality, reproducibility, quality, and also easiness of execution. So this also makes a lot of difference, I believe. And sometimes it's really difficult to find the balance between completeness and simplicity. And actually, this also depends on the audience and the target journal. So I believe also this is something that you should take into account. And then finally, that, and this is, I guess this is a kind of a personal take-home, effective neuroimaging data visualization does not necessarily require technical skills. I think it's more important to really think through all the possible visualization options and choose wisely to show all your data and be transparent about it. Of course, these are like very important things. Finally, I want to thank you for your attention. And of course, feel free to reach out to my email. You can see here my website and also on Twitter. And I wanted to actually thank also these amazing people that were involved in this session, Renaud Lajoie at UCSF and Valentina Borghesani at UMorel. And again, thank you for your attention. And I think I'm good with the timing. Hello, everyone. I'm Leonardo Accarino, a postdoc.
Hello, everyone. My name is Chloe Telesford. I'm a research scientist at the Nathan Klein Institute in Orangeburg, New York. I would like to thank the organizers of the Brain Hackathon for inviting me to speak. Today, I will be presenting Visualizing Networks in Gephi. Now, there are a variety of software packages that visualize networks. The reason why I like Gephi is that it's relatively easy to use and because it allows you to visualize large-scale networks. If you've ever used a package like PyEC or NodeXL, you'll quickly recognize their limitations in large-scale networks. Gephi is not without bugs, of course, but I found it quite useful. Hello, everyone. My name is Chloe Telesford. I'm a research scientist at the Nathan Klein Institute in Orangeburg, New York. I would like to thank the organizers of the Brain Hackathon for inviting me to speak. Today, I will be presenting Visualizing Networks in Gephi. Now, there are a variety of software packages that visualize networks. The reason why I like Gephi is that it's relatively easy to use and because it allows you to visualize large-scale networks. If you've ever used a package like PyEC or NodeXL, you'll quickly recognize their limitations in large-scale networks. Gephi is not without bugs, of course, but I found it quite useful for visualizing systems. Now, Gephi is a network visualization program that you may use in your presentations, posters, or papers. As you may already know, a network is a system containing two elements, nodes and edges. The nodes represent things or objects in the system. In the case of neuroimaging data, that would be likely voxels or brain regions. Then you have your edges, which represents relationships between your nodes. And for neuroimaging data, that could be correlation values or streamlines between two different regions. Now, Gephi allows us to take such data and either import it or create networks within the software package. It also allows you to analyze these networks using various graph metrics like clustering coefficient, path length, degree centrality, and a variety of other measures. The software most importantly contains various layout algorithms, which allows us to visualize the system, and that allows us to see the structure of the system. In this presentation, I'm going to show you how to import data, calculate a few basic graph metrics, and then visualize the network based on those metrics. You can find Gephi at gephi.org. It is available for Windows, Mac, and Linux. It's relatively straightforward. Download the software and install it. You'll also have to make sure that you have the most recent version of Java, as this is what it uses in its software package. Before we get started though, I want to show you some configuration tricks you'll probably need to get the most out of the software. So once you go to gephi.org, download it, install it, and then once you've installed it, you go to your Gephi etc folder in the Gephi installation, and you're going to see a file called gephi.conf, which is our configuration file. One of the problems you may run into is that the software may not load at all, or you can load the software, import a network, and then it will crash in the middle of doing anything. And this really comes down to issues within your configuration file. So you're going to want to focus on two different lines. One is the one under default options. Here it is line 7. And for this, you'll see that I have a range of 64 megabytes to 240 megabytes. I'm not sure what the default is. It's either 512 megabytes or 1024 megabytes. Regardless, the main issue is that if your memory heap size is too small, then the software will crash because it will run out of memory. And of course, this is also based on the amount of RAM that you have in your system. The next line is the JDK home. Here is line 13. And this is where you tell Gephi where your Java installation is. Now, it may not be a problem for other people, but one of the problems that I had was that because I have a 64-bit version of Windows, when I install Java, it installs a 32-bit and a 64-bit version. And if Gephi tries to go to the 32-bit version by default, it will have problems running the software. So I have to explicitly tell it, use the 64-bit version to use it properly. Of course, when you do it this way, whenever you update Java, then you'll have to update this configuration file so it is pointed to the proper Java installation. But you may not have this issue, but if you do have these issues, these are two of the main areas that you might have to play around with to get Gephi to run on your machine. And just to give you a sense of what you can do with Gephi, here is the Marvel Cinematic Universe. You may have seen this 2 years ago on the subreddit Data is Beautiful. And this is something I updated last year. And what you're looking at are all the nodes are representing characters in the system or the movies. And the size of the node tells you how much screen time a character had. And the lines or edges between the nodes tell you how much screen time these characters share with each other. You'll also notice that these nodes have different colors, and these colors represent the groupings or community structure between different nodes. And what that really shows is that characters that appear in the same movies will be grouped together, and that, of course, makes lots of sense. When you're looking at neuroimaging data, of course, you're going to be looking at either some sort of structural connections or functional connections, and you can see which nodes are grouped with each other based on function. For this tutorial, though, I will not be using any neuroimaging data or even the Marvel Cinematic Universe because they are very large networks and they also will just run very slowly on my machine. So I've chosen another network based on the HBO series The Wire, and I have fewer nodes. So let's just hop right into Gephi. So whenever you open Gephi, I've already opened it, you're going to get a welcome screen. And that welcome screen will show you the recent networks that you've opened. It will also give you the option to create a new network, or you can look at some of the sample networks that come with the software by default. I've already chosen new project, and you're going to see I have this overview screen. But let's hop right over to the data laboratory. Now, the data laboratory is the space in which you will be importing all your data, whether it's information about your nodes or information about your edges. It will also be where I can see the metrics and the values associated with my nodes. And then I can also use various tools like exporting that information to a table, and then I can use that with whatever my analyses are. But before we actually start pulling in some information into the screen, I'm first going to show you my actual data. So I have that stored in Excel right now. And so I have two different tables here. One is my nodes table. And that contains a column for ID and label. Now in this particular network, I have 90 nodes, and each of those nodes has a label which represents a specific character. Now for the ID, mine is numeric, but it doesn't have to be numeric. It can also be text. But because my data started out in an adjacency matrix in MATLAB, I just used the row for my different nodes to represent my ID. And the label would actually have my actual text label. If you're dealing with neuroimaging data, of course, you could have each of your rows representing a node, and the label can represent a brain region. So you could have visual cortex or parietal lobe. It's just however you have your network organized. The next table I have are my edges. And my edges has several columns. I have source, target, weight, type, and ID. Now the ID in this case, this represents an ID for my edges. So it's not like the ID for my nodes. The ID for my nodes are what you'll find in source and target. So you want to make sure that whatever you use for your source and target, whatever those IDs are, they need to match whatever is in your node table. But let's just start backwards from these columns. If we look at ID, this goes from 0 to the number of edges I have. You can either have IDs based on groupings of the nodes. In this case, it doesn't matter, so it's all ordinal. The next column I have is type, and that will tell me whether my network is directed or undirected. Because this is a symmetric network and undirected, everything is undirected, of course. But let's say you have a directed network where you have histology data, then you may want to have a directed network, and then you'll have to change the type of edge that you have here. Next is weight. In this case, weight represents how much shared screen time two characters have. In neuroimaging data, that can be correlation between two different regions, or they could be the number of streamlines, like in, say, DTI data. And of course, finally, we have our source and target, which is telling you what two nodes are connected to each other. In an undirected network, connecting 1 and 3 and 3 and 1 doesn't matter. But if for a directed network, it's actually critical that your source to your target is in the right direction. But now that we see the data and how it's stored, we can now import that into Gephi. Now, the data that I have here is stored as Excel files, but you can also import this data as CSV files, which is what I did when I used this software in Linux. So when I want to now pull my data into Gephi, I'll click on Import Spreadsheet right here, and then I will select my nodes table. And once I've done that, I will now have a bunch of data here. You'll see my ID, my labels, I have actor, and I also have this column called screen time. But the important thing you want to make sure of is that what you're importing your table as. I'm importing it as a nodes table. After that, I'll click next. And then I can say, what columns do I want to keep when I'm importing? In this case, I'm going to leave out the actors because I don't care about the actor column. So I'll deselect that. And then you'll see screen time. It will be imported as an integer. You can also import it as a double, but I'm going to leave it as an integer. And then I'll hit finish. Now, when I created my new workspace, you'll see I have something that says workspace 1. And when I'm importing this data, I can say, do I want to create a brand new workspace, or do I want to actually append it to my already open workspace? Now, since I already have workspace 1 already there, I'm going to say append to existing workspace. And now I have my nodes table in Gephi. Now I want to get my edges in. So I'm going to click Import Spreadsheet again. Then I'm going to select my edges and then hit Open. You're going to see I have my source, target, weight, like you saw on the Excel spreadsheet. It's critical that it says Import as Edges table. Then I'll hit Next. And in this case, I'll keep all of my columns. And you'll notice that the weight, it is under the format double. Now, I could select integer, but I'll leave it as double. But if you're looking at something like neuroimaging data, you're going to want to make sure that it is a continuous value. So you'll keep double instead of saying integer. Then I'll hit finish. and I'll append to my existing table, my existing workspace, click OK, and now I have my nodes, and I click on my edges, I have my edges. So now we have all our data in Gephi. So now let's go to our overview screen to see what that network looks like. So when it imports all your nodes, they're going to be randomly connected to each other, and they're going to be randomly, or not randomly connected, but randomly organized on the screen. So we may want to get some information out of this network. So on the right side, you're going to see we have 90 nodes, 458 edges. It's an undirected graph. But now we can start to calculate some statistics. Now there are a variety of statistics that I can choose, but I'm just going to look at degree and click on degree here. And you're going to see that it's going to calculate the number of edges for each node and also give you a distribution. And when you can save that, but in this case, I'll just click close. And the other metric I want to look at is community structure. So I'll click on modularity and have it run the modularity. So I'll keep the default, hit OK, and then it will tell me how many communities it finds and the number of nodes it finds in each community. Now, with community structure, but this particular algorithm is not deterministic. So if I run this again, I'll get a different result. So if I run again, I get a different result. 6 communities, run it again, different result. 6 communities, I got the same thing, run it again. And you can get different numbers of communities based on the number of times you've run it. So I'm just going to leave it at this one that says I have 7 communities. And I'm just going to now close these all out. And now that is stored in my system. So if I go back to my data laboratory, you'll now notice that when I click on the nodes, I now have these 2 new columns. I have one for degree, so I can see which nodes have the most connections. And I also have one for modularity class, so I can see what communities do nodes fall in. But back to my overview, again, we've seen no changes to my nodes on the screen. We see these very thick edges, but the nodes are all over the place. So one thing that we can do is start to looking at ways to change the appearance of the nodes. So if we go to the left side here, we have appearance. And we have this little palette here, so that means that we can change the colors. So one of the best ways to look at the nodes is to look at how they're partitioned. And that will group the nodes based on a certain color. So here, modularity class is perfect because we can now look at those communities that we have and then just say apply. And now we have these different colors representing the different nodes that group with each other more than the rest of the network. But this background is a little light, so we really can't see these nodes. So I can click this button over here and change the background. And now it's a little easier to see. However, how do we see what nodes are important? Well, we can change the size of the nodes and click this over here. And we can change the ranking. Now we could choose something like degree and say, if a node has more connections, it should be bigger. And I can hit apply here, and that will change the nodes based on nodes that have the most connections. In my case, you'll notice that I had a column called screen time. I think of the most important nodes, at least in this particular system, as the nodes that have the most screen time. So I'll click my screen time attribute, hit apply, and then it will change the size of the nodes based on how much screen time they actually had. You notice that I have a minimum size of 10, maximum size of 100, and this is a linear change. However, I can also click on this feature called spline and then change whatever my spline is for how these nodes grow in size. So if I use this one, I can see that the nodes now have a curved spline, but I'll stick with linear here. But of course, it still looks unorganized. You can see that some nodes are overlapping each other. And so you may want to get a sense of how does this network actually organize itself. So I will now choose a layout. And there are various layouts you choose. My favorite actually is Force Atlas 2. So if I just hit run, you'll see that the nodes kind of clump together. So to prevent that, I can click on Prevent Overlap. When I click Prevent Overlap, you'll see that these nodes now are ungrouped, are now grouped together, but it's now flying around. So I can now change my gravity and increase that. So I'm going to increase that to 100. That makes it come back to the center. And then I have my scaling, so that tells you how much these nodes repulse each other. So I'm going to choose 250. And now these nodes tend to push each other apart. And now this network is kind of organized based on how the nodes are connected to each other and how much screen time they have. So let's hit stop here. And then we can go right to preview to get a sense of how this is visualized. Now, if I were to just hit this refresh, I get this visualization of the network. But of course, I can play with the different parameters. So for instance, you can see all these edges are curved. I can go to edges and deselect that and say I want straight edges. And let's just say I want to have labels here. And so I can select my labels and hit refresh. You'll notice that these labels are now underneath my nodes. So I have to go to my renderer here, click Manage Renderers, and I'll go to my default node labels, and I will move them up so that when I hit refresh again, now they're on top of the edges. And then I can just zoom in and I can see the edges between different nodes. And we can see that the characters are representing in each of these circles. And of course, let's just say I don't like having a white background, so I'll just choose a grayscale background right here. And then if I hit that, then I actually can see the nodes more easily now. Reset my zoom, and now I can visualize my network here. And finally, I can just export this, and I can export it as a PDF, PNG, or a vector file. And in doing so, then I can now visualize my system and put that onto a poster or onto a paper, and then have a very nice visualization of my network. So with that, that is just the basic overview of using Gephi. If you have any questions, please feel free to ask. And I hope this will be helpful to you in any of the posters or presentations that you use in the future. And with that, I'd like to thank you and the organizers for inviting me.
So this talk, I'm going to tell you about how
Hello,
we use
everyone.
gradients
My
to
name is
uncover
Kwame
the organization
Telesford.
of the human
I'm a
brain.
research scientist at the Nathan Client Institute in Orangeburg, New York. I would like to thank the organizers of the Brain Hackathon for inviting me to speak. Today I will be presenting
So this talk, I'm going to tell you about how we use gradients to uncover the organization of the human brain, as well as how you can create gradients from your own datasets to use in your own research. But before I get into any of that, let me first take a moment to talk about why we use gradients in the first place. So, the human brain is a hugely complex structure. And if we want to do whole brain network analyses, we have to simplify it in order to make sense of it. One way in which we can do this is by parcellating the human brain. Now, this already dates back to at least the early 20th century with the release of the Brodmann Atlas. Brodmann defined regions of the brain based on cytoarchitecture. And we have continued with this throughout the history of neuroscience, with many neuroanatomists creating their own atlases, and once MRI became big, many neuroimagers creating their own as well. For example, the Euclidean atlas based on functional connectivity of the human brain. However, whenever we parcellate the human brain, we always make an implicit assumption, which is that we assume that there are hard boundaries in the brain, and we assume that the regions that we define are homogeneous. And this is close enough to the truth that we can generally work with it. Now, so for most of our analyses, this is fine. However, imagine that you have a hypothesis that specifically states that there are gradual changes in the cortex. And in that case, you can't really assume hard boundaries anymore. And just to illustrate that with a real hypothesis, consider the tethering hypothesis. In a nutshell, it states that the sensory regions of the human brain are very closely regulated by molecular cues during development. But the further you move away from these regions, the more the development is regulated by self-regulatory mechanisms. So this implies a gradual change along the cortex. It's a function of distance. And this is where gradient techniques can come in. So what is a gradient? Well, here on the right, you see the first and second gradients of functional connectivity of the human connectome. The first gradient describes the biggest change in functional connectivity in the connectome, here between the default mode and sensory cortices. The second gradient describes the second biggest axis of variance in the connectome, here between the sensory cortices. Now, the similarity in color denotes how similar connectivity is. So dark red colors have very similar connectivity to other regions in dark red. We don't have to define any a priori boundaries or regions. And it allows for these multiple overlapping gradients for multiple overlapping changes in functional connectivity. So what can we do with this type of analysis? Well, first of all, it simply allows for a decomposition of a whole brain connectome, as I just showed you in this image. We don't have to limit ourselves to the whole brain. We can also do this at a regional level, as was, for example, done with the cerebellar gradients of Kuhl et al. We can also compare across different groups or different cohorts. For example, in a study by Sukjun Hung et al., we calculated the gradients for healthy controls in the Abide dataset and for autism spectrum disorder in the Abide dataset. And what we found was that the default mode network in autism spectrum disorder is far less separated from the rest of the brain, as you can see from gradient 1. And this denotes a decrease in the decoupling between the default mode network and the rest of the brain in autism spectrum disorder. Now, these are all things that we can do with just the gradients alone. However, we can, of course, also compare these gradients to other markers. For example, Julia Huntenberg et al., they found that the first axis of functional connectivity, the first gradient, which describes the largest variance in functional connectivity, is related to intracortical myelination. Another example was from Charlotte Murphy et al., who stratified their findings based on a gradient. So they had a 0-back and 1-back task. And as you can see, the parameter estimates for the 0-back task are far higher in the unimodal area, and the parameter estimates for the 1-back task are higher in the higher order areas. Now, all of that is still always working with one gradient at a time. We can also work with multiple gradients at the same time, and here we start referring to what we call gradient space. So gradient space is essentially just the space encompassed by the first few gradient vectors. So here's the two-dimensional gradient space. You can see gradients 1 and gradient 2 on the y and x axis, with each point simply colored by their position in gradient space. And this provides us with a lower dimensional space for connectivity visualization and analysis. And just to show you one example of how we can use this, consider again the study I was just referring to on the differences between healthy controls and autism spectrum disorders in terms of their functional gradients. Here again, on the y-axis, we have gradient 1, on the x-axis, we have gradient 2, and at the top, we simply see these color-coded by their community membership to the EU networks. In red, default mode, in purple, the visual, in blue, the somatomotor, and in gray, everything else. Now, At the top, we can then again see the same difference I was just referring to. That the first gradient is contracted in autism spectrum disorder. You can see that in the shift in the default mode network nodes. Now, if we look at the bottom half of this image, we see an analysis of stepwise functional connectivity. Essentially what this is if you place a seed in, for example, the somatomotor cortex, and then you move from there to its connected nodes, and from there you move to its connected nodes again. You keep repeating this process without going back to the nodes where you've already been. Then you would start to travel through the connector. Now, if you do this in healthy controls and you start in any of the sensory regions, then you'll slowly move up towards the default mode, as you can see in the image in the bottom left. The visual seed in the bottom left, the somatomotor and auditory seeds in the bottom right. The stepwise connectivity moves up to the default mode network. So the signals are moving from the unimodal to transmodal areas. If we do the same thing in autism spectrum disorder, we find a very different result, in that the stepwise connectivity from the visual cortex to the bottom left just kind of stays stuck there. And the stepwise connectivities from auditory and sensory cortices initially moving toward default mode, but then veering off into another direction. So these are just some examples to illustrate the kinds of analyses that we can do with gradients. We can decompose the functional connectome and just use that decomposition itself. We can relate it to particular markers of cortical organization, and we can use it to assess other methodologies such as stepwise connectivity. So how do we actually build these gradients? How do we make them ourselves? And how could you do this with your own data set? Well, we start off with some input data. In all the examples I've shown you, this is a functional connectivity matrix, but it can be any matrix. We then compute what we call an affinity matrix. The affinity matrix is essentially a neo matrix that denotes the similarity between each of the seed regions. High values denote high similarity, low values denote low similarity. So at its simplest, you could simply take a Pearson correlation of each pair of rows, and this could be an affinity matrix. In this example, we're using the cosine similarity, which is a metric quite closely related to the Pearson correlation. Next, we apply a dimensionality reduction step. At its simplest, this could be a principal component analysis. We tend to use diffusion map embedding, which is essentially a nonlinear principal component analysis. Whichever dimensionality reduction method you use, you'll end up with a set of eigenvectors, which we call gradients. And again, we could plot those and get a very similar image to the one I've shown you before. If all of that sounded very complicated, we tried to make it very easy. We've recently published a toolbox called Brainspace. This is a toolbox that's available in both Python and in MATLAB for the computation, statistical analysis, and the visualization of gradients. Documentation for this is also available on ReadDocs. All the code is open source and available on GitHub. There will be a link to this at the end of the presentation. Before I continue, just tell you a little bit about Brainspace and what you can do with it, how it works. Let me just give a quick shout out to a few other gradient toolboxes and toolkits that are out there. There is MapAlign by Satra Ghosh, which is a diffusion map embedding package that was used by Daniel Margulies during his 2016 study. There's conic topic mapping from Koen Haak's group, which is a slightly different way of computing gradients. It's intended more to be used at a regional level than at a whole brain level. And there's the package for the cerebellum gradients that I showed you before. So what can we do with Brainspace? Well, let's start off with the code for building a simple grade. And I'm in this presentation only showing you the MATLAB code. The Python code is very similar. If you go to our online tutorials, you see very similar Python code to this there. But in MATLAB code. So on the first line, we instantiate a gradient maps object. This is sort of the core object that does all the computations for you. Next, we fit a connectivity matrix with this object. And we can extract the gradients from that. The gradients are now computed. So we extract the first two gradients, and then we plot those on the cortex using the plot hemispheres function that is included in BrainSpace. And you can see that the first gradient that's computed is the default mode, the sensory that you're now familiar with, and the second gradient is the sensory. And the second gradient is the sensory gradient that you've seen before. Now this is how you can construct a simple gradient that you can use in your analyses. However, consider for a moment that you might also want to compare different cohorts, different subjects, different populations of any kind. You'd have to compute gradients for each group or each subject separately. The problem with that is that when you run a dimensionality reduction step, the eigenvectors that are found might not be in the same space as each other. Fortunately, this is something we can very easily resolve by running an alignment after computing our gradients. This alignment most commonly is a Procrustes analysis. And this is very simple in BrainSpace. We simply instantiate a gradient maps object using the alignment parameter with the PA value, PA standing for Procrustes alignment. And then we fit it to our connectivity matrices, here providing multiple because we have two groups. And then we can plot our unaligned gradients here at the top and the aligned gradients here at the bottom. And as you can see, in the unaligned version, the first gradient flips around to something that very commonly happens in group 2. And after the alignment, both of the gradients are in the same space, and we can use these in our subsequent analyses. Now, the last point I want to talk about is null models. So, in any neuroimaging analysis that we do, but especially so with gradients, we should be wary of spatial autocorrelation in the data. What that means is if I know the value of any one voxel, then I have a pretty good idea of what the values of the voxels around it are. This is the spatial autocorrelation. The problem with that is that most statistical models assume independence of measurements. But the spatial autocorrelation means that our data points are no longer independent, and therefore our test statistics are biased. Now, BrainSpace implements two ways of resolving it, spin test and more in spectral randomization. I'll just show you spin test here. The essential idea here is that we generate 1,000 distributions with the same amount of spatial autocorrelation, but different data. And so instead of just running a statistical test and computing a p-value, we instead compute a test statistic for the true data, 1,000 test statistics for the quote-unquote random data, and then we see in what percentile of the distribution our true test statistic lies. Now in BrainSpace, we simply run the spin permutations code. We supply it with the values that we want to permute, here the T1 up T2 intensity. We provide it with spheres corresponding to the surfaces. This is provided by default by both FreeSurfer and Civet, and the number of permutations. And how this works, you can basically see at the bottom. We have our T1 over T2 intensity, and we want to compare this to gradient 1. We project the T1 over T2 intensity to the sphere. We then rotate that sphere and project the data back to the surface. You can see that the data which used to be at the somatomotor cortex then ends up, in this particular example, in the visual and parietal cortices. We do this 1,000 times, giving us 1,000 distributions. And for each of these, we run a Spearman correlation with the original gradient, and we get the distribution that we see here on the right. And then we can see the true correlation in the dashed line on the left-hand side, which falls below the 2.5th percentile, so we judge it to be significant. So this is all I wanted to show you for just the basics of what BrainSpace can do and how to run it. So just to wrap up, gradients allow us to have a low-dimensional summary of high-dimensional data. We can use this to relate connectivity to other markers, such as intercortical myelin content, cortical thickness, stepwise functional connectivity, you name it. And these are very easy and fun to build with BrainSpace. Now, with that, there are many people that I'd like to thank for helping me get BrainSpace off the ground. In particular, is to give a few shout outs to Boris and Wally, who both worked tirelessly with me to get this package up and running. And if you're currently on the European part of this brain hack, special thanks to Casey, who is currently here to answer any questions you might have, because I am not a morning person. If you have any questions, Casey will be here to answer them. If you come up with any questions after the talk, you can tweet at me at reinervostiwal. You can email me at reiner.vostiwal.com. The link to our documentation is also there, brainspace.readthedocs.org. The documentation also has links to our GitHub and to the manuscript, so you can find both of those there. And with that, I'd like to thank all of you for listening, and I'll take any questions, or Casey will take any questions.